Here we are. Because it runs out of memory if you leave it for too long. It just starts making a huger and huger video. All right, CC, we have people piling back in. I'll hand it back over to you.
Sorry. Great. Welcome back, everyone. And we're glad you're joining us again here for the continuation of the live stream. I think I'm going to just chat for a moment with Jen, since I think we want to wait another few seconds here. How's your day going, Jen?
Not too bad. I'm actually not at home. I'm attending my 30th college reunion.
Oh, wow.
Right now, which is at Swarthmore College in Pennsylvania. So I found an empty classroom. I'm just hiding out.
That sounds really fun. I hope you have a great time. Well, without any further delay, I'd like to start by welcoming everyone and say that we're in the 75th hour of this 100-hour production, almost just down to the last day. And we're really glad to have you here. And the plan of this event is to really highlight the fantastic research that goes on in the US on weather and climate, and to emphasize how important this is to society, and that we are helping protect society from potential harm, and also increase the knowledge base of our country on these really important topics that have long-lasting impacts on our future. We do all kinds of research in the realm of weather, climate, atmospheric chemistry that affects pollution. And, we make a lot of forecasts, and these forecasts are intended to anticipate things that might harm society so that we can avoid them. We do this by being funded by the American public, and we do it in service for the American public. We work very hard, and you'll hear about so many amazing efforts that have been taken on by these really creative scientists, but they're putting their whole heart in this. And yet, we're threatened by cuts in the funding that are being rolled out right now. We've seen many of our colleagues lose their jobs in the federal government, and the threat of grants being removed, as well as the future grant funding availability being restricted. So we're very concerned, and because we feel that this work is so important to benefit American society. So that's why we're doing this, and we're really grateful that you're here. And I just want to lastly say that these speakers are speaking for themselves and not for the federal government or their institutions. And with that, I'd like to introduce our next speaker, Dr. Jen Mackinnon. She's professor at Scripps Institute of Oceanography, which is part of the University of California, San Diego. She's an oceanographer who enjoys teaching and spending time at sea doing her research and being with her family. So why don't you take it away, Jen?
Okay, great. Thanks so much. Yeah, thanks for the introduction. And I enjoyed Galen's talk and a bunch of the ones that I've watched over the last few days. And so I'm an oceanographer, and what I do, amongst other things, is think about the ocean's role in climate. And you may have heard that because of the high heat capacity of water, the top few meters of the ocean hold as much heat as the entire atmosphere. So how the ocean stores heat, moves it around, and releases it is one of the things that we're really that's really important to study. And so I'm part of this group at UCSD, the Multiscale Ocean Dynamics Group. And we are a team of scientists who build a lot of our own instrumentation, and I'll show you some of that to you as well. So I'm going to talk about a few different projects that I work at, all of which are federally funded. So this first one is funded by the Office of Naval Research, and I know we've heard a lot about NOAA and NASA and NSF funding in this channel, but the Office of Naval Research also funds a ton of basic fundamental science research, and the Navy operates in the ocean, and they put a lot of effort and money historically into understanding how the ocean works in a basic science way, and that money is also in, that funding is also in jeopardy these days. So this first project I'm going to talk about is called Stratified Ocean Dynamics of the Arctic, and this is a picture I took when I had the great privilege of working in the Arctic a few times in the last decade. This is the RV Sikuliak, which is one of the research vessels in the fleet that we use. And so to motivate this work, here's a plot of the sort you've seen before. Everyone's probably heard that the Arctic sea ice is melting, and our moderator just gave a nice talk about that a little while ago, and this is a slightly older figure, but essentially it shows all these different forecast models, predictions based upon, we run a big climate simulation, how quickly the Arctic should be melting, and there are all these lines, and the gray kind of shows the spread, and in reality it's melting not only as fast as predicted, but often faster. And so the question is, what are we missing in these models? And one of the things we're missing is heat from the ocean that might be accelerating the sea ice melt from below. So how does that work? So to do that, we're going to do a little question and answer, and I'm looking at the chat. So first question, this is an interactive audience question. Cold water is denser or less dense than warm water? Is cold water dense? Is cold water light? Anybody? Denser. See in the chat, denser is correct. Okay, so but density of ocean water is controlled by two things, not only its temperature, but also its salinity. Second, oh, here's a plot. Yes, it's so a lot of parts of the ocean are warm on the top, cold on the bottom. Second question, saltier water is denser or less dense than fresh water? Anyone? Okay, saltier water also, the more salt it is, the denser it is, because the salt dissolves and these little ions are like stuck in between the water molecules, and there's cool hydrogen bonds and all sorts of things. So the more salt there is, the denser it is. So now the question is, what happens when you have water that's warm but salty and cold but fresh? Which of these is denser? Just give the audience one moment. I see, oh, crap, sorry. Give me one moment. While you're thinking about the lights in this classroom I have just gone off. Hold on. Very environmental to have lights automatically turn off. Okay, cold but fresh. I see fresh. So turns out the answer is it depends. Sometimes cold but fresh is denser because the cold wins. Sometimes warm but salty is denser because the salt wins. And so it actually gets pretty complicated. So most parts of the ocean, though, have warm water on top, cold on the bottom, which we say that they're stratified by temperature. The Arctic is a little funky. So it has water on the top that's cool but fresh. And then below that, it has water that's denser because it's saltier, but it's warmer. But it's so salty that this water can sit below. And so one of the questions we've been thinking about in the Arctic is, how does this warm but salty water get into the Arctic? And how might this heat be mixing upwards to accelerate the rate of sea ice melt? And so one of the things we looked at for this ONR sponsored project is we're looking at, there's warm salty water. It comes in through Bering Strait from the North Pacific, and it comes around and it goes through these different sort of channels and heads into the Arctic, where it meets this cool, fresh surface water, Arctic surface water. And we're wondering what happens when these different types of water masses meet. And so we made a bunch of observations, and one thing we did was looked from space. And so this top left plot shows a picture from space. This is sea surface temperature, and you can see where there's no data here when it's dark blue, there's like clouds or something, so you just can't see it. But you can see, if you look between the clouds, this jet of warm, salty water comes around the corner here and goes careening into the Arctic, and then it starts to like wobble and do this wobbly turning around thing, and then you don't see it anymore. Where did it go? It disappears from view. This is a synthetic aperture radar image, so it's a different way of looking at roughness of the sea surface, but you can see some things happening at here, and this stuff here, this is sea ice. If you look subsurface, this is what you see. And so this is a three-dimensional plot where the color is temperature, this is depth, and these are two axes of distance. And so this warm jet is coming in here, and you can see it's diving down beneath the surface. It's making these funny little scallopy shapes, which are different types of super fun, like fluid dynamics instabilities. And then it's turning into these little blobby blobs, which then swirl themselves away towards the Arctic. So I'm going to pause here and mention So these measurements are really high resolution. Like you can see, there's lots of continuous measurements in space. And so this gets to one of the novel tools that we use. And so I've labeled here, this one is labeled a wire walker. And so here's a super fun little animation. If it plays, you can see this playing, yes. And so what this is a vehicle, and it has a bunch of different components to it. And it has sensors that measure biogeochemical properties, ocean currents, temperature, salinity. It has this thing on the top, this buoy that goes up and down with surface waves. As it goes up and down, it ratchets down this instrument. It goes down, down, down with all the little critters. And when it gets down to the bottom, it lets go. It's mildly positively buoyant, and it floats up again. And so it's harnessing the power of surface waves to profile this instrument up and down. And it actually goes shockingly fast. It can go up and down every few minutes. And so this instrument was developed by my colleague. The cartoon was, the stop motion was made by these people listed below. This was developed by my colleague Rob Pinkel at Scripps and Andrew Lucas at Scripps. And so this is super fun. Here's what it actually looks like. Here's a little movie, this thing profiling up and down, and it has all these, you can clamp on all sorts of sensors. And so this fun new way of seeing the ocean lets us see all sorts of cool things. And so just a summary for this, and there's a little fun video at this QR code. Warm water comes in, it curls around, it subducts beneath the surface, it turns into these little spinny blobs. They careen into the central Arctic, slowly diffusing their heat upward and accelerating sea ice melt from below. So we're trying to understand, it's not an Argo float, no, it's a homemade, it's related technology, but it's a homemade special. And trying to understand all the physical processes involved. So I'm going to turn to a second example now. This is Katrina, which everyone will remember. And so one of the crazy things that happened with Hurricane Katrina in the Gulf of Mexico is that initially it had a track that looked like this, and the strength was going to be not so bad. But like a couple of days before landfall, it curved left. It made this crazy, surprising left turn, and it intensified really rapidly and surprisingly. People know that hurricanes draw their heat from the ocean, and the entire Gulf of Mexico, the surface temperature was really hot at this time. So it was not clear why it careened and why it accelerated, why it intensified so rapidly. Subsequent research revealed, and there's a bunch of papers about this, and here's just one from a couple of colleagues, showed that it was actually the subsurface heat content. You can see here's the Katrina track, and this color here is sort of the extra amount of more than average heat subsurface in the ocean. It was the subsurface heat that the winds were able to eat into that, release that heat, and that fueled kind of an explosive growth of Katrina, which is one of the reasons it became so utterly devastating. And so there's a large motivation to understand the structure of heat in the ocean, why heat might build up subsurface in some situations, with obvious impacts for accurate forecasting of storms like this. So we've been making measurements. This is actually a National Science Foundation funded experiment. And this plot here shows sea surface salinity. So this is how salty it is. You can see this dark blue color here. This is the Mississippi Atchafalaya River system. So it's dumping out river water, is flowing into the ocean, but it doesn't just spread out kind of simply. It's doing this crazy little dancey thing, and it's swirling, and there's these sharp edges, and you can see there's all sorts of like fun physicsy things happening here, and it's really complicated. One of the things that happens is that you can see there's these sharp changes in color here, where it goes from fresher to saltier in kind of a very abrupt way. So this is something called an ocean front. And here's a photo I took on the boat when we were measuring in this box. And you can see, I bet a bunch of you have seen stuff like this, where you see like a long line of foam or seaweed, or sometimes even garbage. We picked up some like sneakers floating in here and all sorts of things. You've probably seen this, people who go out in the ocean. And so this is where different types of water masses are coming together. And so this is important in terms of how heat can get down under the surface. So here's here's this picture again. And so we measured measurements across one of these fronts. And so each of these are colored different things that we measured as a function of depth and distance. This is in terms of latitude, but it's like a cross section. So I'll just point you to this one here, salinity, and this is made by one of our students, Kaiki Diasuko at Scripps. And salinity, you can see here, the redder colors are saltier, and then the green and purple are fresher. So there are these waves. It's sort of saltier water, and then here's a wave of river water coming out, and then here's the next wave of river water coming behind it. So there are these river water coming in waves, and at the edge of each of them, there's really sharp gradients. What happens at the edge of these gradients is that heat can actually move down, and I'll show that more clearly on the next plot. But another crazy thing that happens at these gradients is they facilitate a type of vertical circulation, so you can get top to bottom movement of water. So heat can move down. This bottom plot is dissolved oxygen, and the Gulf of Mexico has a lot of anoxia at the bottom. And so these sorts of fronts are also areas where you could exchange water with anoxic bottom waters and ventilate areas that are getting anoxic. So they're really important to understand what happens at these super sharp features. And so one way we measured this is another example of like novel ways of seeing the ocean, is that we had 4 different vessels profiling only like 500 meters to a kilometer apart. 2 of them were regular ships. These are both operated by LUMCON, by the Louisiana Marine Ocean Consortium, wonderful ships. And then 2 of them are these crazy autonomous vehicles made by my colleague, Jonathan Nash, who actually spoke in this live stream a few hours ago. And you can see, so it's like a remote control, like your little remote control car powered boat. And so these guys are towing instruments and measuring all sorts of things. And so we had all 4 of these moving in a line. And one of the things you can see here, here's 4 different sections of temperature moving over a short period of distance. You can see heat plunging beneath the surface. This is one of the mechanisms by which heat gets subsurface to be subsequently, maybe or maybe not released to storms. But you can see only over like 1 kilometer to 2 kilometer distances between these measurements, there's all sorts of different structures and how the heat is getting down there. And so these crazy physical processes that let heat go down and it swirls around. And so we're trying to understand how those physical processes work. They can have very small spatial scales, which are definitely not included in most of like the forecast or regional modeling. Okay, final example that I wanted to mention. This is again work funded by the Office of Naval Research, and this is an interesting example of funding. A lot of the work that ONR funds has to do with the general desire of predicting geopolitical stability, and DoD, the Department of Defense, understands that geopolitical stability anywhere in the world is important for us, is an issue for us as Americans, is an issue for everybody. And so much of the geopolitical stability these days has to do with climate and changing climate, that being able to understand that is of huge national interest as well as global interest. So this work is done in the Bay of Bengal. And I love this little circle, that there are more people living inside the circle than outside of it. This is a huge population density area of the world. And one of the biggest issues in this part of the world is monsoons. So monsoons are a seasonal pattern of rainfall and storms and larger scale circulation. But the timing and strength of those monsoons, like hurricanes, is very challenging to predict. And one of the reasons it's challenging to predict is because it depends on physical processes we don't fully understand yet. So this, even though this is far away from the Gulf of Mexico, it has a lot of similar, it has some similar physics. So this is a little movie of sea surface salinity. So this is how fresh or salty it is at the surface in the Bay of Bengal. So there's all these rivers like the Ganges and other rivers which are just dumping out fresh water, and it comes out of the rivers. It has a seasonal cycle. Water comes out. This fresh water swirls around with all these eddying sorts of motions. You can see it makes little sharp fronts like we had in the Gulf of Mexico and all sorts of structures. And just like in the Gulf of Mexico, similar things that can happen. So to measure those, I'm going to show one more instrument. This is another instrument made in our group at Scripps. And this is something that measures temperature and salinity and some biogeochemical properties. And it's this torpedo looking thing that has a bunch of sensors on the nose of it, and it dives down and dives up really fast. So it goes up and down about 5 meters a second, which is fast enough that you can make really high resolution measurements. If you drive along going up, down, up, really fast, you get to see all of the really delicate structures. And so the sorts of things we see with this are that, so here's a section. This is a long section going all the way through the Bay of Bengal. This is temperature, this is salinity, and this is just the top 50 meters of the ocean. And this is about 600 and some kilometers. So you can see, if you look at this movie, this is a simulation, but you can see there's all, as this freshwater swirls around, there's all these different patterns. And you can see that in salinity here. That you're going through patches of fresher water and saltier water and fresher water. And beneath some of these patches where it's really fresh at the surface, you get these pockets of warm water that have subducted and are hiding beneath the surface. And so the same thing happens here as happens in the Gulf of Mexico, that when you get cyclones or some types of monsoon oscillations passing by, they can release this heat and it will explosively fuel some of those atmospheric phenomenon. But because the models don't understand how this warm water gets brought down below and how long it stays there and at the rate at which it mixes up, it's currently very hard to predict that sort of explosive growth. So the types of things that we do are try to understand the basic physics so that we can improve those predictions in the future. Okay, so in conclusion, I think, when we talk to new graduate students, they ask you how do you choose what problems you work on? And I think the answer is usually that the types of problems we work on are things that are fun science. I mean, I think science is awesome. It's super interesting, these sorts of things. They're great problems to work on. Problems that where our types of creative development of novel ways to look at the world, new sensors, let us see something fundamentally new. And research that is useful to society, understanding monsoons, predicting sea ice melt, predicting hurricanes, these things that matter to everybody. And so I think the intersection of these things is what federally funded academic research is all about. It's those combination of things, which is really hard to find almost anywhere else than in academic research settings. But I think it's incredibly I think it's valuable what all of my colleagues do. And so that's it. Thank you.
Thanks so much, Jen. That was fantastic. Really enjoyed it. And there's a lot of comments about how cool that stop animation video was. I really enjoyed that.
Yeah, it was amazing. I mean, I did not make that one, but it's fantastic.
Sure. One question was, how deep does it measure?
Oh, so the wire walker, it depends how long of a line you put it on. So there's two issues. The one, you can put it on a longer and longer line and it will go further down. At some point, the pressure gets high enough that the sensors will crush. So you have to put them in special cases and stuff. Some colleagues of mine just deployed them on the equator to look at things related to equatorial dynamics and El Nino, and they went down 750 meters, which is pretty deep. And they made a round trip, so that's 2,000 feet or so, and they went down 2,000 feet and back every 45 minutes, which I thought was kind of amazing.
Terrific. I also wanted to compliment you for having audience participation in a virtual meeting. I don't think I've seen that before. Good job. Kudos to you. And it actually generated a really great question about density. And one person asked, how does microbiodiversity impact water density?
Yeah, so one interesting thing that happens that some of my colleagues at Scripps are looking into is a question of harmful algal blooms. And so this is an interesting that happens that so sunlight can penetrate. This especially happens in the coastal ocean. This happens off San Diego all the time, but it happens a bunch of places. you can get certain situations where you have different types of nutrients, and then the sunlight comes in and different plankton populations can grow, and you can get these blooms of things that are sometimes harmful, types of dinoflagellates or whatever else, and red tide, and it's toxic shellfish and blah blah blah. But one of the interesting physics things that happens is that once the population starts growing, it's not density per se, but it impacts light attenuation. It changes the light attenuation curve, and so then light cannot penetrate through it because it's just such a dense bloom, and that changes the physics of the water column in terms of how water masses move around and whether or not they bring up nutrients. So it can feed back on the bloom itself by changing the physical properties of water through light attenuation. So there's all sorts of crazy feedbacks.
I bet. Okay, one more question from someone who says they're non-scientists, and they asked, they were saying, I'm trying to conceptualize what a front in the ocean looks like, and I know they exist in the atmosphere, so can they fronts cause storms and winds in the atmosphere, but how does that in turn look in the ocean? Are there currents that are kind of like fronts?
Oh, yeah, absolutely. So the fronts and atmosphere, right? I mean, so two things happen when an atmospheric front passes. One is it's super windy, and two is that often the temperature drops. And that's because the front is a boundary between air masses of different densities. In the atmosphere, that's mostly due to different temperatures, and so that's why it gets colder when the thing passes. And the reason why it's super windy has to do with that difference in density combined with the Coriolis force. And so the same thing happens in the ocean. So you can see it sometimes when you have different like warmer or colder water masses piled together, because there's a confluence, and so you get like lines like this in the ocean. And so sometimes, especially this will happen like at the edges of a continental shelf or something, there'll be a continental shelf break front, and you totally get a jet that goes along the front, just like when it's like when an atmospheric front, it's super windy, you get a ocean current jet that goes right along that front, and it can absolutely make like subsurface like swirly, stormy conditions. And some, actually, my understanding is that some a lot of plankton really like those stormy conditions because they bring up food and nutrients that they need. So that's why you often see at fronts like this, you see dolphins and whales, because they're feeding on the plankton who live there, because the underwater storms bring up all the nutrients. So it's like all sorts of cool stuff in the ocean.
Wow, that really makes sense. Thank you so much for all these. Oh no, you lost your light again.
The light.
Maybe you'll have to say it was meant to be. Thanks for so many great, descriptions of this really impressive research that you do, and I think we all have a better picture of the ocean now. Thank you again.
Yeah. Okay, absolutely. Thank you.
Okay, and I'm handing the host over to the next person. At least I assume I am. Let's see if someone is arriving at the moment. Well, I'll just, while we're waiting for the next host to arrive. Oh no, I get one more hour. See, now I get it. Great, thank you. I'm so happy to be here for another hour. It's no problem. But I will wing it here because I thought I had two different speakers in my last hour, but they're coming this hour. So that'll work just fine. Anyway, I would like to begin by telling you a little message about what we're doing here today. So we are now in the 76th hour. So we're almost down to the last day. And we are, of course, showcasing the U.S. climate and weather research in our country because we want you, the public, to understand and appreciate what you have invested in. And also because you may know that we have had unprecedented cuts to our colleagues' positions in the federal government. Those are especially to the early career colleagues, which of course concerns me a great deal as an educator, because I'm seeing our recent graduates losing their positions. And these are students and recent graduates that had put their heart and soul into their PhD work. It's tremendous efforts that they go to. And this work, of course, benefits society. It's the investment that you have made in our research enterprise, and then to see it essentially being eliminated so that you can't enjoy the benefit of our investment. Yeah, we rely on, of course, taxpayer dollars to make our observations and models and gain the understanding that's essential to making predictions that help us navigate the risks associated with our weather and climate and atmospheric air quality as well. But it doesn't have to be this way. We should be telling our politicians what we think we value and what we want them to prioritize. So we want to reach out to all of you to contact your representatives and in Congress and let them know what you think. And also I want to thank everyone for asking such great questions. Keep it up. Sometimes we don't get to all of them, but we read all of them, and we'll hope that somehow we can communicate those answers back to you, since you are what we're doing this for today. With that, I'd like to say that the speakers are not representing their institutions or the federal government. They all speak for themselves. So I'm looking forward to finding out who the next speaker is. I'm guessing it's Liz Moyer, since I was expecting to see her last hour. Is that right? My director, oh no, it's maybe reversed. Phil Duffy, great, I get to introduce Phil too. And I have a bio for you. And I actually know you, Phil, I don't know if you remember, but you visited when I was a postdoc at University of Victoria. And I remember you really well, and you had a big impression on me. So thank you. That was many years ago. So Dr. Duffy is dedicated to understanding and managing the human consequences of climate change. And he's chief scientist at Spark Climate Solutions. And before joining Spark, he was at the White House in the Office of Science and Technology Policy, where he used to inform and implement President Biden's climate agenda. And prior to being in the government, he was president and executive director of the Woodwell Climate Research Center. And he served as senior policy analyst in the White House Office of Science and Policy prior to his most recent stint. And he also has been a climate scientist at Climate Central. So I think that's probably good. I don't want to take too much time away from your presentation. So why don't you take it away, Phil? Thank you.
Well, thank you. Thanks so much for the introduction. And yes, I remember very warmly a nice summer in 1998 spent in University of Victoria. Got a lot of work done, had a lot of fun, and realized how few material possessions one needs to be to have a happy and fulfilling life. So I want to spend the next 20 minutes or so making a science-based case for greater climate ambition. I'm emphasizing, as Cecilia just mentioned, that I'm here representing myself, not any present or former employers. So the thesis, my thesis is that the climate trajectory we're on poses unacceptable risks to humanity's future well-being and prosperity. And to make that case, I want to start with some of what's happening in the physical world and some of what's been happening in the physical world recently. I think a lot of you know that 2024 was the first calendar year above the 1.5 degree warming target. Now, 1.5 degree that has no particular physical significance. It's a political target that was set by the United Nations and adopted by many others. And again, 2024 was the first full calendar year where the global warming exceeded that level. It wasn't the first 12-month period, actually. And what happened in late 2023 and 2024 in terms of warmth was rather remarkable. I'm going to show you the data in a different way to indicate how unusual it was, what happened. And so this is looking at the same data, showing the data month by month, where each line on this curve represents a different year since 1940. And again, moving across horizontally is showing the temperature or the warming level month by month, starting in July and working through June. So it's not showing things based on calendar years, but more like fiscal years. The top curve, the red curve, is 2023, 2024. And what you see is that not only was that 12-month period the warmest ever, but it was the warmest on record, I shouldn't say ever, the warmest on record by a large margin. And at the time, this seemed astonishing and surprising. And in retrospect, it shouldn't have been, perhaps. And if we look at some of the drivers, and you can see that if you look at some of the drivers of this recent warmth. And I'll start with carbon dioxide. Carbon dioxide, of course, is the major driver of human-induced warming. And this is showing not the atmospheric level of CO2, but the year-on-year increases in CO2. This is relatively new data. And what it shows is that in 2024, the year-on-year increase in CO2 was larger than we had ever seen before. And that's shown in the bar on the right there. You can also see that over time for the last 60 years or so, the year-on-year increases themselves have been increasing. So we're very much moving in the wrong direction as far as accumulation of carbon dioxide in the atmosphere goes. Now, the major driver of the rapid increases in atmospheric CO2 is rising emissions from fossil fuel burning. This is shown here for the last 35 years or so. You see continuing increases in emissions, and it's also actually interesting if you look at the fine print, if you can see the fine print. This slide shows that really the only times when CO2 emissions have dipped is because of some global calamity, the dissolution of the Soviet Union, the financial crisis in the first decade of this century, or the COVID-19 pandemic. And each of those dips has been relatively small and, of course, temporary. Now, other factors contributing to the recent jump in CO2, 2024's record growth in CO2, include a drought in the tropics, may have been triggered by El Nino, but contributes to elevated CO2 through forest degradation. Wildfire emissions have increased recently, driven in part by climate change, and higher wildfire emissions are an example of what I call warming-induced greenhouse gas emissions. The scientific community sometimes calls this carbon cycle feedbacks. And I'm foreshadowing that in a few minutes I'll have more to say about warming-induced greenhouse gas emissions. So that's CO2. Now, the second biggest contributor to human-caused climate change, of course, is methane. Human sources of methane include agriculture, include the fossil fuel supply chain, include landfills. Now, some of these sources of methane can be mitigated with existing technologies, and we're getting pretty good now at detecting, for example, emissions from the fossil fuel supply chain, detecting and mitigating emissions from the fossil fuel supply chain, although that it's by no means a solved problem, but we do have the basic technologies we need to solve that problem. Agriculture, on the other hand, is more challenging. The biggest source of methane emissions in agriculture, and the biggest single source of human methane emissions, period, is ruminant animals, in particular cattle. And we have some partial solutions for cattle that live in confined environments. We don't have solutions for cattle that are not in confined environments, and they comprise 90% of the enteric methane mitigation. So in methane mitigation, there are some unsolved technical challenges. I would say good news about methane is that, unlike CO2, if we were to reduce methane emissions significantly, in principle, we could actually cool the planet in the near term on a time horizon of decades because methane has a relatively short lifetime in the atmosphere, about a decade. Okay. Now, the bad news about methane is that the amount of methane, the atmospheric methane burden, is in fact increasing. This shows the methane concentration going back to about 1980, when it was warming rapidly. It plateaued, atmospheric methane plateaued for about the first decade of this century, and then has recently accelerated. And this recent acceleration, the cause of it has been a subject of lively discussion, and it always struck me as sort of alarming that this is a first order change in a very important driver of warming, and we don't understand very well what's driving it. A consensus is emerging that one of the primary drivers of this recent uptick in the atmospheric methane concentration seems to be increasing emissions from tropical wetlands and inundated areas. And this also seems to be an early example of warming-induced greenhouse gas emissions, which again I'll mention in a few minutes. Also want to mention, of course, that the most recent warming in late 2023 was contributed to by El Nino. Climate scientists all know that El Nino is a temporary phenomenon and a natural one, and typically adds about 0.2 of a degree to the global warming level because of it causes changes in clouds in the eastern tropical Pacific. The figure here is an observed pattern of sea surface temperature anomalies in this late 2023. I think it's in December. I can't read the fine print on my own slide. And this shows the classic, or one of the classic El Nino sea surface temperature patterns, which is this bright red glob right around the equator in the eastern tropical Pacific. Okay, I want to mention another driver of warming, which is cleanup of particulate pollution. And here I'm going to oversimplify just a little bit, but this is actually interesting, and I'll just walk you through this figure on the left. And this is somewhat out of date. Okay, so this is from IPCC AR6, and the data are representing the decade 2010 to 2019. So again, it's a little bit out of date. The bar on the left is showing observed warming, which at that time was 1.1 degree. I just showed you it's now 1.5 degrees. It's not clear how permanent that is, but it's at least temporarily it's jumped a lot. Okay, so at this time, the observed warming was around 1.1 degrees. At this figure, the right panel shows that observed warming is a net of about 1.5 degrees of greenhouse warming and about 0.4 of a degree of cooling. And that cooling is from human emissions, mostly particulate pollution. And so the message is that a significant amount of latent greenhouse warming is in fact masked by other human emissions, again, mostly particulates. As we continue to clean up those particulates, this cooling, the latent warming is going to tend to be unmasked. And that's not great for climate, but it is great for humanity generally because particulate pollution is very deadly. It kills millions of people annually around the globe. Okay, I want to talk just a little bit, frame the question of warming-induced greenhouse gas emissions. And I worked for a while. Well, one of my mentors was George Woodwell, who the Woodwell Climate Research Center is now named after. And George Woodwell liked to pound the table. Well, he liked to pound the table generally. One of the things he pounded the table about was the idea that as the planet warms, natural processes like permafrost thaw, like wetland methane production, like wildfires, like soil carbon, and oceans, natural processes will tend to emit greenhouse gases, or in some cases emit more greenhouse gases into the atmosphere. And he characterized this as The warming feeds the warming. And he wrote a book, in fact, with that as a subtitle, The Warming Feeds the Warming. And actually, George testified about this, among other things, about this idea of the warming feeds the warming, testified about this in the United States Senate as early as 1986. And of course, in 1986, this was all a theoretical construct. As I've indicated, this seems to be happening now with methane emissions from tropical wetlands, with methane emissions from and CO2 emissions from permafrost, probably, and certainly wildfires, some of which are due to climate change, have become, at least periodically, a major source of greenhouse gas emissions. Okay, so why do we worry about warming-induced greenhouse gas emissions? First, because they tend to be self-reinforcing, right? Warming causes emissions, causes more warming. Okay, so that's bad. Emissions from natural systems are difficult to stop, right? There's no off button on permafrost. And these warming-induced emissions, furthermore, are not in most climate models. That's getting better. They're not accounted for in United Nations processes. They're not in the national emissions that are submitted to the United Nations. They're not accounted for in NDCs. They're not accounted for, at least not completely, in remaining carbon budgets and so forth. So they're sort of like corporate expenses, which are off the books, okay? Right now, those expenses, right now, these warming-induced emissions are probably small, but they will certainly tend to grow as the planet warms further. And so, in my view, it's urgent to not only understand these emissions better, but to think about steps we might take to try to manage them. So where does all this leave us? Assessments suggest that based on current policies, we're headed for a warming of maybe 2.5 or 3 degrees C by the end of the century. And this is a stylized figure, actually based on some work by an organization called Climate Action Tracker. The figure was actually made by the New York Times just to make it a little prettier. The top bar, and this is showing greenhouse gas emissions over time. And the top bar is an extrapolation of the trajectory we're on, which translates again to 2.5 or 3 degrees of warming. More optimistic scenarios show closer to 2 degrees of warming, and the green trajectory, the lowest curve here, is a 1.5 degree compliant scenario. And it's useful to illustrate, it's useful to look at these scenarios in this way because it shows how radically things would have to change to be on track for 1.5 or even 2 degrees of warming. Emissions would have to stop going up and really drop off a cliff. And in the case of the 1.5 degree scenario, emissions would actually have to go significantly below zero. And this shows net negative global emissions approaching 10 gigatons a year. And I want to emphasize that in these types of scenarios, what you're seeing here when the line goes below the zero line, what you're seeing is net negative emissions. And since there will always be some gross positive emissions, if you see a net negative emissions of X gigatons per year, it means you need removal capacity that's going to be substantially greater than X gigatons per year. And so this raises the issue of carbon dioxide removal. I'm going to skip this slide, actually. Raises the issue of carbon dioxide removal. Whoops, I thought I had a slide on CDR. Maybe I do. I'll just say that one of the challenges we face in managing climate risks is we need to scale carbon dioxide removal way beyond the capacity that we have now. And in my view, most likely any scenario which achieves a safe and stable climate is going to depend on lots and lots of CDR, which right now we don't know how to do. Okay, so I want to just shift gears now a little bit and talk about what a 2.5 or 3 degree world might look like. And here what I mean is what would be the human consequences of that level of warming. And I want to start by emphasizing that human consequences are inherently difficult to predict. What we can predict in principle, based on scenarios of future greenhouse gas emissions, in principle, we can predict physical effects. So an example of a physical effect might be increases in extreme heat and humidity, okay? That's a physical effect. Now, the human consequences of that, for example, heat stress mortality, for example, reduced labor productivity, are inherently more difficult to predict because they can be mitigated to some extent by adaptation actions. And we don't know, we can't predict how effectively humans will adapt to the change in physical world. So I'm emphasizing that here, and I'm showing in the left column some of the physical effects of climate change, and then in the right column, the corresponding human consequences. And so the physical effects are things like drought, which lead to water scarcity, crop failures, and food scarcity, more hot, dry weather, which exacerbates wildfires, tends to reduce crop yields, extreme precipitation, which tends to produce flooding, sea level rise, which tends to produce coastal inundation. Now, these are not, but this is by no means a comprehensive list. This is just examples. And again, the main point here is I'm making a distinction between changes in the physical world and the human consequences. Things I worry about are extreme heat, including deadly combinations of heat and humidity, which we're starting to see now in South Asia. If you look at projections, and if you look at the certain latitude regions, drought becomes the norm due to poleward expansion of the Hadley cell, which seems like a robust prediction. Drought becomes a norm in regions of Central America, North Africa. This leads to, among other things, increased food and water scarcity, probably migration pressure. Certainly, as sea level rises, we will see more coastal flooding. Certainly, we will see more inland flooding from higher extreme precipitation. Climate change will cause, and is already causing, multiple health impacts, not just heat stress mortality, but food and waterborne illness, vector-borne illness, and so forth. A lot of these things are going to contribute to migration pressure. Again, we don't know how that's going to be realized in the real world because it depends on adaptation measures. But almost certainly, in my view, all of these things are going to result in increased geopolitical tensions. The scenario that I worry about, sorry, go back, is a scenario I worry about more than any other is that the human consequences of climate change become severe enough that they create political and geopolitical conditions which make it hard to take the steps we need to manage the problem itself. Okay, and I just want to offer this thought as well, which is that the IPCC in the latest assessment report is saying that as we learn more about the risk to the human systems, as we learn more about these risks, they start to look worse. And the quotation here is that high risks are now assessed to occur at lower global warming levels. So they're not saying it's warming faster than expected, although that may be true. They're saying for a given level of warming, we now assess the risk to various human systems as higher than we previously did. And that's shown in this typically obscure IPCC figure. And I'll just mention on adaptation, we're not spending anywhere near as much as we should. The two bars on the left here are different estimates of available funding for adaptation. The much shorter red bar is how much was pledged as of 2021, $21 billion a year. This is for the developing world. That translates to about $3 per person per year. Okay, so you don't get much for $3 even in the developing world. Now, no talk about climate risk would be complete without mentioning the idea of tipping points. There's different definitions of tipping points. This figure is from a widely cited paper in 2022 by Armstrong, McKay, and others, and they define tipping points as conditions beyond which changes in a part of the climate system become self-perpetuating. IPCC has a slightly different definition of a tipping point. They call it a critical threshold that when crossed can lead to significant and potentially irreversible changes. And this is a map showing various climate tipping points that we know of. A lot of these involve ice in one form or another, or permafrost, which isn't ice exactly, but it's a frozen substance which thaws. Others involve ecosystems, forests, coral reefs. And some of the most important tipping points involve, or one of the most important tipping points involves the Atlantic overturning circulation. Now, of course, we don't know exactly where these tipping points are. We don't know at what level of global warming these will happen. And furthermore, it's possible that that we've already crossed tipping points and we don't know it. There's no alarm goes off when one of these tipping points is crossed. This is from the same paper, and this is just illustrating for each of the tipping points on the map in the previous slide, illustrating the range of temperatures where we think that tipping point might be in comparison to the 1.1 degree of warming that was the official level of warming when this paper was published, and also the United Nations goal of 1.5 or 2 degrees. So you can see that we may be close to or even past some of these very important tipping points. Okay, I'm going to wind up.
Oh, good.
Just
sorry, down to the last minute.
Yep, this is the last minute.
Okay, perfect.
I'm just these are science talks and not policy talks, but I just want to close with my personal view of what we should be doing, and I'm just going to make 3 categories of actions. One is there's things we already know how to do, mitigation actions we already know how to take, where we have the solutions, we have the technologies, we need to deploy those more aggressively. There are unsolved problems in mitigation, in carbon dioxide removal, and in adaptation. We need to accelerate the development of the solutions we don't have. And finally, again, in my personal view, we should be investigating, researching possible insurance policy options, various sorts of interventions, including, for example, solar radiation modification. So that's all. Thank you. Really appreciate the chance to participate in this event, and happy to answer any questions.
Thanks so much, Phil. That was really terrific to hear such a great layout of the emissions challenges and the past and what we need to do. But I think I'm going to give just one question to you, so we try to get Liz up pretty quickly here. But the question was, well, there were quite a few really good ones, but I chose this one. Just did we just launch a satellite to measure methane, and how's that going to help us sort this out?
Great question. There's several methane monitoring satellites which are relatively new. There's Methane Sat, Carbon Mapper, GHG Sat. Now, these are really powerful tools. They can measure, they're good at measuring strong point sources of methane, and many of the emissions from the fossil fuel supply chain are these strong point sources. So they're great for that, and they can provide data with very, very low latency so that the emitter can be notified and shut off the source of emissions. So these satellites are super powerful tools for mitigating some methane emissions. They don't have the sensitivity generally to see cows, to measure emissions from permafrost, which are very diffuse. Similarly, they don't have the sensitivity yet to measure methane from wetlands. At least we think this is true. And because those emissions, although in some are substantial, they tend to be more diffuse.
Great. Well, thank you again. Really appreciate it. And it's good to see you. Keep up the good work.
Well, thanks so much. I really appreciate the opportunity to be here.
Great. Take care. So I will read a very abbreviated version of the transfer here so that we can get a little closer to being on schedule again. But just like I want to say hi to everyone who's just joined, and thank you so much for being with us today as we showcase the EOS science and our research that's so important to the country for safekeeping of society from the risks from climate, weather, and air quality. And here we are in almost the last day. We're at hour 75, and that's a tremendous effort that and tremendous outpouring of incredible research that we've been hearing about. And thank you to the organizers so much for putting this together. But I also really want to thank you, the American public, for supporting our research. We do it for you, and it just shows the commitment to this program that you're seeing from everyone today, and the research, of course, they're reporting on illustrates just the tremendous devotion that U.S. scientists have to our science and to protecting the public. We would hope that you'd be willing to contact your congressperson to tell them how much you value what we do and are concerned about the threat of reducing funding for scientists, especially those early career scientists who have so much talent and really deserve a chance to give back to society what they paid for from their education and the commitment they made to learning their research, their field. So with that, I'll say that the speakers are speaking for themselves. They don't represent the federal government or their institutions. So I'm really happy to introduce the next speaker. This is Liz Moyer, good friend, and her research interests kind of fall into two threads. The first includes use of isotopic composition of atmospheric water vapor as a tracer of convective processes, and she studies cirrus, formation, patterns of cirrus. She's done that in a number of international research programs, fieldwork. And she also studies stratosphere-tropospheric exchange. So with that, I'm really excited to hand it over to her so you can hear directly from her about her work.
Hi, just checking that everyone can hear me. I want to talk to you about, I do a lot of different kinds of work, like Cecilia said, but I want to talk to you about my primary core research, which is measurements made of water vapor in the atmosphere. And most of you understand how important water vapor is. It's the most important gas besides CO2 in our climate system. And I just want to say that a lot of the work that I'm going to show you was funded, at least in part, by an NSF program called the International Partnership for Cirrus Studies, which funded researchers at 5 different US universities and multiple partner universities in Europe. And the idea was to produce a rich research environment for young people. So we did high quality science, but also provided mentorship for young people and international connections, because this work that I'm talking about really is international in origin. Okay, so I just want to go to the core of why we do this work in the first place. And I'm showing you here an animation. This is not the real world. This is a model simulation of the real world, but model simulations are getting pretty good these days. So this is showing you a very high resolution simulation of current climate in a numerical simulation, similar to what you'd use for weather forecasting. And it shows you the diversity of cloud formations on the planet. And this simulation is so good. If you look carefully, you can see some things that aren't quite realistic, but from your perspective, it probably looks pretty much like the real world. You can see hurricanes forming, you can see low stratocumulus decks over the ocean, you can see atmospheric rivers coming and hitting the West Coast. So all of these clouds, these are the reasons we don't have a very certain climate projection. The dominant source of uncertainty in climate projections are these clouds. So why is that? Almost everything else about climate is pretty generic, pretty basic stuff. But what we don't know is how these change under future conditions. And clouds are incredibly important features of the climate system. They provide, actually right now, a net cooling. And that cooling is mostly provided by the low clouds. You see how shiny the Earth is, mostly because of white clouds. Those clouds reflect away sunlight and keep the Earth cooler. Those low clouds are what I call the most important uncertainty in the climate system. What I study is actually not the most, sometimes I say I study the second most important uncertainty in the climate system, and that's the high clouds, which actually do the opposite of low clouds. The high clouds actually warm, so more high clouds keep you warmer. So why is that? It's because they're so thin and wispy, they don't do much reflection, but what they do is they trap a lot of infrared radiation. They're kind of like super greenhouse gases. So these thin wispy clouds that you see at altitude, those are actually doing a substantial amount of warming of the climate. We don't know in the future if those are going to increase or decrease. We actually have huge uncertainties even in the sign of how they might change. Okay, so here is a graph that just wants to remind you of the scale of the atmosphere and why we care about these high clouds and what matters, why it's hard to actually study them. So the atmosphere to a planetary scientist, the Earth's atmosphere is minute. It's a tiny little skin, right? If you had the Earth the size of an orange, you couldn't feel Mount Everest as a bump on the orange. The atmosphere would be something just inconsequential. But our atmosphere, we care about even those tenuous parts of it that reach above Mount Everest. So my study area is really about 2 Mount Everest high. So that's how the easy way to think about it. And that altitude is the altitude where the very, very highest storms reach. That kind of sets that altitude. It's the barrier, the absolute transition region between where clouds can reach, where big convective storms can get up to, and the very stable region above, which we call the stratosphere. And those of you who are listening who know about the ozone layer, the ozone sits up in the stable stratosphere, and that's why it is able to form there. So our protective sunscreen of our ozone layer is at very high altitudes between 20 and 40 kilometers high. The area that I'm most interested in is the very top region where clouds can reach on Earth, because that's where they have the biggest radiative effect. They also can impact stratospheric chemistry by pumping water up there. And that's a region that's really, really difficult to access because it's about twice as high as commercial aircraft go. So a commercial aircraft can more or less fly to the top of Mount Everest. We want to go twice as high. It's also a very tricky region for satellites to study because everything is changing so quickly there. We're in a transition between 2 totally different regimes of the atmosphere. So it's very hard for a down-looking satellite to make good measurements. So in general, it's one of these few parts of the Earth system where it's really tough to get even the most basic measurements. It's hard to go there. So it feels a lot like exploring this kind of work that we do. Okay, so what are some of the basic questions? I'm interested in water and the formation of clouds, and especially the formation of these high, thin cirrus clouds that help warm the Earth. Who might warm the Earth more or less in the future? We don't even know that. So I'm interested in how much water do these really strong, deep tropical convective storms that boil up to 18 kilometers high, how much water do they bring up there as water vapor? That's my first bullet point here. How much water do they bring up there as ice? That can be 1,000 times more than the vapor. They're just big, all the white that you see in a big, deep thunderstorm, those are little particles of ice. And when the storm dissipates and disappears, it's because that ice has sublimated, it has become vapor. So these giant storms are like an elevator that pumps water vapor up to these very high altitudes. I'm interested in the size distribution of the ice particles that are carried up, because that also affects how long they stay, what their radiative properties are, how easily they fall out. We know that eventually we have to strip water out. So the other thing about this region that I'm interested in is that it's also the coldest region on the Earth, in any sort of region, until you're very, very high in the tenuous bits, almost out to space. This is the coldest place. It's colder than the coldest parts of Antarctica. So the temperatures here are like minus 100 degrees Fahrenheit, about 200 degrees Kelvin. Sorry, my cat is trying to get in the picture, so we'll see if we can get him. I did not remove him, so you'll have a little bit of visitor, I'm afraid. Yeah, he loves science too, so he wants to be part of this talk. Anyway, so this is a region very hard to study, very cold. The atmosphere, the temperature goes down with altitude, so does the pressure. So we're about 1/10 of the pressure at the Earth's surface, and about 100 degrees, minus 100 degrees Fahrenheit. So a tough environment to study, tough environment to get to. So how do we get there? We get there partly in aircraft, but we can't use a commercial aircraft. So I'm going to show you some of the tools that scientists use to study this region, and they're generally military cast-offs because the aircraft are complicated and expensive to develop. there's no scientific infrastructure that is developing new aircraft. So what we use are hand-me-downs from the military, generally remnants from the Cold War when both the US and Russia were spying on each other. So I'm going to show you 2 campaigns I participated in under this wonderful NSF program. One of them is a European campaign. That one's on the right. It uses a Russian-designed plane called the M55 Geophysica. The US campaign uses the United States design, or actually it's an Australian bomber that's been converted for science use to a high altitude plane called the WB-57 that was intended, again, both of these are Cold War planes. The B-57 was originally intended to carry cameras over Russia. So these two campaigns happened within 4 years of each other. They were the first ever campaigns where scientists could access the very top of the Asian monsoon system, like actually sample air from the top of the monsoon. And as many of you probably know, the Asian monsoon is the single largest weather phenomenon on the Earth. It feeds about 1 billion people, are dependent on the rain from the monsoon for rain-fed agriculture. So it's the biggest and most socially impactful weather feature we have. We also have very little understanding of how it might change under a future climate. Okay, so both of these planes are high altitude. They offered us sampling all the way up to 20 kilometers, so well into the stratosphere proper. We were able to access cirrus that's both in situ formed, like ice that forms just when the air runs through a cold patch and you've crystallized little ice crystals out of the background air. We also see these boiling tropical storms that come up from the ocean and carry big chunks of ice way up that high. We wanted to get measurements of particle size distributions, the ice nuclei, the aerosols in the background atmosphere, the little particles that help the ice nucleate. And then my particular specialty is the isotopic composition of water. So not just the amount of water, but the very tiny amounts of stable, heavy water that are naturally present. They have no implication chemically for the Earth, but they are a very sensitive tracer of phase changes. So phase changes are exquisitely sensitive. The isotopic composition is exquisitely sensitive to phase changes because every time you condense ice or liquid out of a background vapor, you strip out the heavy isotopes. So these big convective storm systems are like fountains of heavy water up to the top of the atmosphere. We have a huge signature that we can measure. So what did we get from Stratified? We got vigorous convection at the monsoon center. It was based out of Kathmandu, right in the heart of the monsoon. Some days we couldn't fly because there was too much convection. We could fly directly through these incredibly strong convective systems that were coming up within hours. ACLIP, the second campaign, we started out of Korea. We're not in the heart of the monsoon. We're not even in the center of the monsoon at all. We're way off to the eastern edge. But what we're looking at is outflow. It's an easier location to stage out of, and we got age-polluted outflow coming out of the monsoon. So if you have seen a picture of the monsoon, you see a big circle that sits, a big stationary weather system that sits over Asia. That stationary system also traps all the pollutants that are emitted from the surface below. So the center of the Asian monsoon, it not only is a system of a tremendous rainfall, tremendous water transport to the upper parts of the atmosphere, but also it just cooks in whatever pollutants have been emitted at surface level. So you have very high levels of carbon monoxide, other easy tracers of human effects. So we could see all that from Korea. Okay, just in the interest of time, I'm going to zoom through some pictures just to show you kind of the level of care that's required and the level of work, of joint effort that's required to get any samples from these altitudes. So here are some pictures of Stratified, the Asian monsoon. We went through all of this effort to get 8 flights, years of preparation, years of diplomacy to get permissions, flight permissions, to get the plane. We almost couldn't get the plane in. It got stuck in Afghanistan and couldn't get out for a while. It's this international work is very, very difficult. It requires the cooperation of large teams of people. In addition, the plane is also carrying instruments. Nobody's instrument solves a problem or gives you a complete picture by yourself. So you need instruments from multiple teams that measure different things. And because each measurement is so hard, each instrument that makes one particular measurement of one species in the atmosphere or radiation or particle sizes, it will have its own little dedicated team of like a principal investigator, a postdoc, several graduate students, a technician or engineer. Like it's like a movie set when you go out here, with all of these different people, each of them playing their unique role. So you see just some of them here. These are some of the aircraft crew who are working on the plane and the scientists who are installing air instruments in the plane, in the nose of the plane here. This is the US plane we use for American missions. This is a workhorse of the NASA high altitude airborne fleet. It's the WB-57. Again, the basic design is very old. It's from the 50s. It was refitted in the 60s to be a high altitude military craft, and then it was turned over to science use. So this particular instrument flies only for science. The Air Force has one as well. Typical team size for one of these campaigns, again, over a dozen groups. This particular campaign also had a lower altitude plane, a Gulfstream 5, which is just an executive jet. So more than 100 people sitting there in Korea for, I think it was 6 total weeks, with, of course, the lead logistics people going out for months beforehand. So that's what it takes just to get, again, a handful of flights, you know, a dozen flights of air that no one sampled before, because none of this stuff is easy. Some quick pictures of our own instrument. Just again, I'm going to zoom through it, but I'll leave time for questions. So if you have any questions, you can ask. This is us on the top of the Russian aircraft. Again, this is not something that's allowable by NASA standards, but it's different organizations with different standards. So we were permitted to walk all over the plane. In fact, they preferred us to do all of our work up there. So our instrument is mounted on the top of the plane. Remember, this plane is going up to Mount Everest high. It's going to experience temperatures of -100 Fahrenheit surrounding it. So our instrument lives under that dome there. It samples air through a tube that extends backwards so it can pull in air with no particles in it, process it through the instrument, flushes the air out the other side. Here's what's underneath the dome. This is our instrument. Probably cost about $500,000 in development, not including all the labor. It's the most sensitive instrument for measuring water isotope logs ever created for these high altitude conditions. They've made better measurements in lab, but nothing better has ever gone out where it has to be bouncing around on the top of an airplane. This is my former postdoc, now my research scientist, Ben Clauser, who's up there adjusting the inlet flow. We had to flush it to dry it out before every single campaign. So why are we so sensitive? This particular instrument works by a very standard technique of tunable diode laser spectroscopy, where we tune a near-infrared laser across the spectral feature of the molecules of interest, where the particular molecules will absorb light. So you can see on the bottom a sample spectrum where you can see several different features where there's a dip in the amount of light. So what I'm showing you on the graph is the light on the detector, and every time there's a dip, it's because the molecule that we care about has absorbed some of that light. So we're tuning the color of the laser across these features, and the depth of the feature, of course, fitting the whole shape, will tell us how much of the substance there is. So the bigger features here in blue are regular water. The green feature there, you see that tiny little dip that's marked HDO in green? That's what we're looking for, the tiny amounts of naturally occurring deuterated water. And just to let you know that this little dip that you're seeing, that's about 10 times more than our signal when we're at altitude. This is just a laboratory test or an easy example to show you where you can actually even see it. So we're picking out something which is less than 1% of a drop in our signal, and then we're trying to get an accuracy of the fractional of change in that, less than 1% signal to itself only about 1%. And we're measuring something which is only a few parts per billion in the background atmosphere. So how do we do that at all? We have to increase what they call our optical path. So if we're trying to measure how these tiny, very scarce species absorb light, we need to give them lots of opportunities to interact with our laser light. So we bounce our laser light back and forth between two mirrors. Now that's also a pretty standard technique, but what we do is an amplified version of that, where we use very high reflectivity mirrors, 99.98% reflective at this wavelength. We shoot the light into the cell and we let it bounce back and forth until it gradually bleeds out the backside of the mirror. And by the time it is able to exit from this super high reflectivity cell, it's gone about 6 kilometers in path length on average. So that's what gives us our signal, that we're giving the laser light 6 kilometers of opportunity to find one of the molecules we want to measure and interact with it. Okay, again, back to pictures, because again, we have to go pretty quick. This is the aircraft. You'll notice it has very long wings. All the aircraft, again, we can't use commercial aircraft for this purpose. We have to use something specialized. The pressure, like I said, is 10 times less than the pressure at the Earth's surface. We can fly in it, but in order to fly, you need lift. in order to get lift when the pressures are so low, you need long wings. So all of these planes look weirdly spindly compared to the commercial aircraft that you're used to. Single pilot, this plane carries only one person. He wears a pressure suit because he's high enough that if you lose pressure, if you lose your canopy up there, you would be dead without it. So it's a single guy, single engine, parachute, and a bunch of scientific instruments. That's basically what you are. All right, I wanted to show you, I don't have time to discuss in detail, but just to give you an example of the kind of summary that we get after multiple campaigns. So this is from a series of campaigns. There's 2 results that summarize kind of everything we learned. The very leftmost figure is everything we learned from our Asian campaign, and the center figure is for Asian campaign over Kathmandu, and the center figure is what we learned from all of our test flights out of Houston, because we fly out of NASA Johnson. And these figures, the x-axis here is water vapor. The y-axis, you just think of it as altitude. It's given in a different unit, but just consider that as a proxy for altitude. So the higher up vertically on that figure you are, the higher in altitude. The further on the right, the wetter you are. So you'll notice that water falls off quite dramatically. We're down at 5 parts per million, about 1,000 times less water than you would have at the Earth's surface, more than 1,000 times less. It's the coldest place on Earth. It's also the driest place on Earth. The color code is by its average isotopic composition. Again, the ratio of these very otherwise not important deuterated water molecules. And you'll notice the red color. Whenever you have a wet excursion, you have a red color, and especially for the North American monsoon samples over Houston. So you can see that every time you have one of these red excursions, that is the mark of a convective system, one of these enormous storms that has boiled up and has dumped out ice. So from those colors, from this map, we can quantitatively determine the contribution of deep storms to bringing water to these very high altitudes. Okay. I want to go through a few extra points before and then still leave some time for questions. So the last point I want to make, and again, I'll zoom through this. I just don't want to give you the impression that aircraft are the only way to study this region. We are, I think, an incredibly important part because we can get very high resolution samples. We're measuring the air actually in situ. So we measure the air that we fly through. So our vertical resolution is, meters, and our horizontal resolution is however fast we can measure, conditioned on the speed the aircraft is traveling, which is about 200 meters a second. So we get measurements. We make a measurement every second. So we have about 200 meters horizontal resolution. On the flip side, we have satellites, which have global coverage. They're not getting just 8 flights every 4 years. They're covering every day all over the globe, but their resolution is hundreds of kilometers. So the combination of having sort of a coarse measurement everywhere all the time and then very fine scale measurements occasionally is really how we do science. So everybody depends in the aircraft community, depends on these satellites. And I just want to show you some fairly horrifying figures about both the changes that are happening up in this very hard to measure atmosphere and worries that we have over future decommissioning of these satellites. Again, encouraging you to call your congressman and say that science must continue. So this figure here, I'm just seeing how much time I have. I'll do a few more minutes and then that should be time for questions because I think we were a little bit over. This figure here, the x-axis is time. There's 4 columns, four different strips here. Each strip is a different species. These are measurements from the microwave limb sounder, a NASA satellite that has been making wonderful measurements for many years. The top strip is water. The second one is nitrogen, is N2O, nitrous oxide. We have hydrogen chloride, and then we have ozone is the bottom one. And the color code marks anomalies, so changes from the background. And then, of course, we've got latitude. Each strip is going from the poles to the equator to the other pole. And the color marks an anomaly, a change, positive or negative, a difference from normal background. And what we've colored in, anything that gets brightly colored is something that's what we call a 3 sigma anomaly, like really rare. Something really weird has happened. And what we showed here is from 2005 to the present, we've had 7 different occasions where we've had significant 3 sigma anomalies in one of these species. And one of this example on the top is a Hunga-Tonga volcano that exploded, put a lot of water up there. That's not a human created problem, but it obviously made a big change in the composition of the stratosphere. Everything below that is something that could potentially relate to human changes. There's times when the ozone hole persisted for abnormally long, when the temperatures were remarkably different. We have the Australian wildfires in 2020 that were at least plausibly exacerbated by climate change. Much hotter conditions produce more dramatic wildfires. Those wildfires sent smoke plumes into the stratosphere proper. We have a rare sudden stratospheric warming. There are some of these that we understand very well why they happen. Some of them we don't understand. But the point of all this is that this is a dynamic region. This is a region where things are changing. Some of these changes we don't understand. More of these changes we expect in the future. It's important that we monitor it. So aircraft are part of the way we monitor it. The other way we monitor it is with satellites. There are 3 major types of satellites. And I'm going to just show you this cartoon. And again, we can stop and do questions. The absolute maximum coverage you can get is from a satellite that does what we call limb emission, that looks at the atmosphere sideways and measures the microwaves emitted by that atmosphere itself. So long wavelength emission from the atmosphere itself, just because the atmosphere is warm. And we can see in that, we can measure, we have get quantitative measurements of species, and we have coverage pretty much all the time. The second option is limb scattering, where we only get daytime coverage. And the third option, we get wonderful measurements, but we do it by pointing the satellite instruments at the sun and then measuring the different slant paths through the atmosphere as the sun sets. And those will only get you what you see here, the very limited coverage. Okay, so right now we are blessed with the beautiful, wonderful array of satellites up there that were in part the result of incredible longevity of things that were put up there with 5-year lifetimes that ended up lasting for 20 years. So we've had incredible luck with great hardware that's lived up there. But what we're facing in the future is the end of the design lifetime of most of our current fleet without necessarily a plan for the future. And this has nothing to do with current politics. This was a problem. This has been a problem for 10 years. So people have been worried about this for 10 years, that we may be currently in the time when we have the best view of our planet, and that view will decrease in the future as we lose our satellite observations. So just looking at this graph here, where we show you all the options we have now, and that black line is the present, and those lines fading out are our loss of current satellites and the potential increase in new satellites, but these are uncertain plans. So again, it's just a reminder that this data is incredibly important. It's expensive. It's hard. It takes a long time to build these things. It takes a long design lifetime. We depend for our view of the planet on having an existing infrastructure, a community of people who work together for years to make sure that we have reliable instruments that are taking measurements and monitoring the planet. And without that continuity, we don't know what's happening, right? You think that you can turn on your internet, see anything, get a snapshot of the Earth. We couldn't do that 20 years ago, and we may not be able to do that 20 years of the future. So just a little picture here. Remember I told you the Hunga-Tonga volcano, incredibly strong volcanic eruption. The top strip here, again, the time is on the x-axis. The y-axis here is altitude, not latitude. This is actually out higher up in the atmosphere. The color code is water. You see the seasonal variation in water. The winters are dry and the summers are wet. So you have more water. It's actually red in this picture. So red is wetter. And you see the seasonal pattern. And then you see the slant going up is because that air is gradually traveling upwards. And so when you plot it against time, it makes this slant. We call this the tape recorder, so that you see this pattern of the seasonal change moving upwards over time. And then you see this enormous red influx of water from this abrupt function, it's like a stripe. That's the volcanic explosion. So we can see this with our modern satellites. We see it really well. We have a great view of that water being added. We can watch how it disappears. The bottom strip is how we would see this same phenomenon if we have the satellites that we expect to have 5 years from now. That's the difference in the view that we'll get under our current plan.
Oh, thanks
So-
so much, Liz. This has been really
So,
astonishing.
anyway.
Yeah.
So there's those lessons. High clouds are important. Deep convective storms bring water. Lower stratosphere is critical but poorly studied. And both in situ and satellite observations are needed for monitoring. And we desperately need to continue. And hopefully there's time for questions.
Well, there are quite a few questions. However, you actually answered a lot of them before the end of your talk. But maybe just really quickly on one was, what would happen without the U.S. participating in, I think the question was really about field programs. How would that play out? Like if, especially we drop out of some that are currently planned, could they go on without U.S. participation?
It's very hard. One of the problems is the Europeans actually don't have, so the Russian plane they were using is gone back to Russia. It's not accessible anymore. The Europeans do not have a heavy payload, high altitude plane of their own. So they've actually been talking to NASA to see if they could borrow, pay for, obviously rent the US plane.
Yeah.
We are really an international, typically these aircraft campaigns have been separate by continent, but the expertise goes back and forth. The reason I was on a European campaign is because they didn't have anyone who had that instrument. And on the ACLIP campaign, we also brought Europeans over to make particle measurements because we didn't have the appropriate people here. And so losing either Europe or the US would be devastating. Satellites also, again, the EU has satellites, Japan has some satellites, but the US is still the workhorse. And the US isn't even replacing its own satellites, and the EU, can't step in for that purpose. So would be pretty devastating.
Yeah. Thank you again. We do need to switch over. So people loved your cat, by the way. Take care.
Sorry, sorry about him.
Oh,
I should have locked him up.
Great. So at this point, we're switching hosts. So it's been a real pleasure to be with you today, and I'll stay tuned as a participant. Graduate student from my program is up next, Lily Zhang. Take it away. Really looking forward to.
Everyone say thank you to Cece and Liz in the chat. Yeah, thanks so much, Cece. I'll see you again later. Okay, hi everyone, it's Lily. I'm a graduate student, as Cece said, in atmospheric and climate sciences, and I'll be your host for the next 2 hours. So really quickly, before we get into this next segment, I want to remind you why we're all here for this 100-hour streamathon. We're here to save America's forecasts. As Liz just showed us, US scientists have been world leaders in weather and climate prediction for a long time. We have this amazing unparalleled network of observations, satellites, weather stations, etc. And all of this progress wouldn't be possible without investment in these areas from the public. So we have all of you to thank for that. And unfortunately, there are these recent funding cuts that are affecting all areas of weather and climate research, putting this great scientific miracle at risk. We just learned that the administration's most recently proposed budget cuts NSF and NASA Earth Science budgets in half. It completely eliminates NOAA's research arm. So even if even if the National Weather Service is not affected and the research arm is affected, as we just saw, you need those observations and you need that support for our forecasts. And it also ends these foundational programs for young scientists, like the NSF Graduate Research Fellowship Program, which actually supports my PhD. So if you've been enjoying our stream and you want to help save our forecasts, we ask that you please share what you're learning with your friends, family, and representatives. If you haven't called your representatives before, thank you so much for being willing to call for our cause. And we've made it really easy for you by putting together a nice call script. And you can go to this website, wclivestream.com/act, and all you have to do is put in your zip code and it'll give you a call script and all these phone numbers. So I have the app open on my phone. It's maybe hard to see, but it has my location. And then you just click on Fund US Weather and Climate Science, and it pops up all your representatives' phone numbers. So can we see a show of hands in chat if you've already called your reps? Would love to see how many of you have already gone to this link and called your representatives. And yeah, so keep calling. And join me in welcoming our next speaker, Kayla Mitchell, who is a climate scientist and PhD candidate at UC Irvine. So as a final reminder, please remember that our speakers are all appearing in their personal capacities, and any views they express are their own, which may not be those of other participants or their affiliated institutions. Okay, take it away, Kayla.
All right. Is it, everyone can see the slides?
Yes, we can see your slides.
Okay, I'm sorry about that. We're seeing the transition from the first slide to the second slide right now, right? I had some issues with the app.
Oh, it's not flipping back and forth if that's what you're doing on your end.
Gotcha. All right, now we're great. Thanks, everyone, and thanks for that introduction. Yeah, today I'm going to be talking about the focus of my research, the ocean carbon sink, how the ocean stores carbon, and what effect that has on the climate. But first, I'm going to give a little bit of background on carbon, specifically CO2, how it causes warming and how it kind of behaves in the entire Earth system. So if you've been watching the live stream, then you've definitely seen this graph a few times. This is the Keeling curve, named for Charles Keeling, who founded the Mauna Loa Observatory in Hawaii. And it is documenting the rise starting in 1958 of atmospheric CO2. You can kind of think of our CO2 emissions as a long-term commitment because carbon dioxide has a long atmospheric lifetime. So it kind of hangs around in the atmosphere for hundreds of years. So even if we stopped all of our emissions altogether today, the warming effect that we're experiencing would persist and even continue to increase for decades. As long as atmospheric CO2 continues to rise, so will global temperatures. So you probably know CO2 is a greenhouse gas, but what really are greenhouse gases? Pretty much everything emits radiation, even humans. That's why infrared goggles, show up, humans show up. The Earth emits radiation too, and it also emits infrared radiation. So this diagram here is showing both solar radiation that's coming into the Earth system and then the Earth's radiation that tries to radiate out to space. What greenhouse gases do is they allow the incoming solar radiation to pass through the atmosphere, and they prevent the outgoing radiation from the Earth, the thermal, specifically infrared radiation, from leaving to the atmosphere. So kind of like a greenhouse that traps heat within the Earth system. On their own, greenhouse gases aren't a problem. If we didn't have any in our atmosphere, the Earth's average temperature would be about -18 degrees Celsius, so 0 degrees Fahrenheit, and that's uninhabitable. The problem is we've just emitted too much of them and the rise is too rapid. The other thing about CO2 is that it's far traveling. So this is a screenshot from NASA Goddard's GEOS 5 simulation showing atmospheric CO2 concentrations in the atmosphere. This is during the month of May. Unlike other kinds of emissions that create smog and linger locally in the area that they're emitted, like nitrogen oxides or volatile organic compounds, the CO2 emissions from our country and other countries will all mix together pretty rapidly in the atmosphere and smear out globally. So it affects everyone. And so now we know, we've emitted a lot of CO2, it traps heat because it's a greenhouse gas and it travels around in the atmosphere. What else is going on? Basically, another part of the story is that less than half of the CO2 emissions, the additional CO2 that we've added to the atmosphere, has actually remained there. What happened to the rest of it? I'm going to get around to the answer, but first I'm going to direct your attention to these maps. This is from a paper that I wrote that I started in my master's using NASA's Orbiting Carbon Observatory 2, a satellite that collects measurements of atmospheric CO2. These maps are showing the anomalies, so by season, of carbon dioxide over the United States. For the Northern Hemisphere winter, that's like the top left, and then spring, the bottom left is summer, the bottom right is fall. The pink values are showing that CO2 during that season and in that place, the CO2 levels are relatively enhanced according to the annual mean of the domain. And then the green colors are indicating that CO2 in the atmosphere is relatively depleted during that time and in that location. So you'll see that the most pink values are in that top right panel, and that's the spring months. CO2 has accumulated, the most CO2 is accumulated over the annual cycle then. And then when we transition to the summer months, the pink flips to green. So that's showing that CO2 is depleted and something has taken it out of the atmosphere. And this drawdown is in line with the growing season. And that's because of the biosphere. In the Northern Hemisphere, when plants start photosynthesizing more, they remove that CO2 from the atmosphere. So this is like one of the mechanisms that, you know, the natural land and ocean carbon sinks have to remove carbon dioxide. So to answer the question, what happened to the rest of the CO2? Over 25% has been absorbed by the land biosphere, and another about quarter by the ocean. And so the land biosphere and the ocean in almost equal amounts serve as natural carbon sinks. And so they're our most powerful buffer against global warming. If the carbon sinks didn't operate, then we'd have twice the additional CO2 that we've emitted to the atmosphere. So the effects that we're experiencing now are mitigated like far less than if these sinks weren't operational. And so carbon cycle scientists like myself are really interested in monitoring these sinks if their strength is changing over time and understanding the processes by which they store the carbon. To clarify a carbon sink versus a carbon source, a source is something that adds CO2 to the atmosphere. So fossil fuel combustion, for example, and a sink is something that removes CO2 from the atmosphere. So like trees in a forest performing photosynthesis. I study the ocean carbon sink, and it's one of Earth's most essential climate regulators for storing carbon as well as heat. So these sinks are important, the land and ocean sink, but this figure here is showing different IPCC climate scenarios. SSPs are shared socioeconomic pathways. They're basically making different assumptions about how much CO2 we're going to emit into the future. When we're looking into the future at the higher SSPs, so more CO2 is emitted. SSP 8.5 on the right is the highest emission scenario. The land and ocean, the natural land and ocean sinks decrease more. So these are the projections. We don't want them to weaken a lot, and we don't know the exact amount that's going to happen. We're trying to constrain that. So again, how do the land and ocean sinks take up CO2? One of the main biological mechanisms that I mentioned earlier is photosynthesis. So that's kind of nature's CO2 converter, where plants take in carbon dioxide and they release oxygen. But they don't just produce oxygen during photosynthesis. Photosynthesizing organisms are also called primary producers because they produce organic matter. In the equation here, next to oxygen, it says glucose, but this encompasses a lot of organic matter. All of it is an organic form of carbon. So production refers to the biomass that's produced during photosynthesis. It's all the stuff that the plants produce. It's their bodies, it's the roots, it's the leaves, everything like that. And you can even measure, production's measured in like grams of carbon. So you can think you could weigh a tree. And you could even measure production in kilocalories, which is like the metric unit for calories, because it's essentially energy for higher trophic levels like us consumers. So it's converting inorganic carbon, carbon dioxide into forms of organic carbon. And photosynthesis, we know, occurs with land plants, and we're pretty familiar with that, but does it occur in the ocean? It super does. And that is performed by phytoplankton. So they're microscopic they're like the tiny plants of the ocean. And what's really impressive is that they take up pretty much the same amount of carbon dioxide as all the plants on land. And like land plants, they require sunlight and CO2 and nutrients, and they perform photosynthesis and produce oxygen and organic matter. So because this talk is mostly about the ocean carbon sink, phytoplankton are a crucial component of it. They are converting CO2 into organic carbon. So they drive the ocean's biological carbon pump, which essentially pumps carbon into the ocean away from the atmosphere. Like the equation, they take up inorganic carbon in the ocean, CO2, during photosynthesis, and they transform it into organic matter, forms of organic carbon. That essentially traps the carbon in like a solid form that can't be exchanged with the atmosphere. Some of it will aggregate, so stick together, and then sink to deeper ocean layers. The deeper that it can sink before being decomposed back into CO2, the longer it remains in the ocean. So in the water column, most of the organic carbon that is produced by the photosynthesizing organisms gets respired by microbes. So the ingredients that go into photosynthesis, it basically spits out the opposite when that organic matter is broken down for energy. So the organic carbon gets broken down, decomposed by microbes back into CO2. But depending on the depth that happens, deeper ocean layers, it takes longer for the water to return to the surface. So between like 100 and 1,000 years, basically, is how long that carbon can be stored in the ocean if it falls below the depth of the thermocline, if it escapes where remineralization happens by microbes. Okay, so this is the wrong PowerPoint, and that's why I got confused in the beginning. We're gonna just keep chugging along. In addition to the biological carbon pump, the ocean carbon sink has another component that is more physical and chemical. The main other pump that we talk about in the ocean carbon sink is called the solubility pump. And this is when CO2 actually dissolves into the ocean. That happens when surface ocean PCO2 is less than atmospheric PCO2. PCO2 is saying kind of like the partial pressure of a gas in air or in a liquid. Things want to move from high to low pressure. So when the atmosphere is higher in like a higher pressure of CO2, it wants to move into the surface ocean if it's lower in CO2, and vice versa. CO2 is also more soluble in cold water, so it preferentially, the solubility pump is enhanced in high latitudes because the water is colder. And the reason that the ocean carbon sink has been growing is the solubility pump. The biological pump removes carbon, but that was already happening. That's kind of like the equilibrium state. Since we've been emitting so much extra CO2, atmospheric CO2 is rising. So the atmospheric PCO2 is really great, and more wants to diffuse into the ocean because of that big gradient. And basically, there are different biological, physical, and chemical mechanisms that drive the ocean carbon cycle and regulates the climate. And as a marine biogeochemist, I've studied the interaction of these processes. A lot of uncertainty in the ocean carbon sink revolves around the biological aspect because living things are diverse and have diverse responses to different environmental changes that we're experiencing in climate change. There's like thousands of different kinds of phytoplankton. They live in different environments. They respond to acidification or warming more. Some of them are more efficient at like creating and exporting carbon. I basically use computer modeling to quantify the relative influence of the biological pump on ocean carbon storage. So I can kind of tease out which mechanism the ocean carbon sink is operating by. Like, is it the invasion of anthropogenic CO2 because of solubility effects, or is the carbon storage due to the biological aspect, the biological carbon pump? So the biological carbon pump, I might just abbreviate it from now on as the BCP for a bit so I don't stumble, has a really incredible potential to influence atmospheric CO2 and climate. And it has, through geologic history, a really strengthened biological carbon pump has been suggested as like one of the possible triggers or driving force behind snowball Earth events, which is like extreme glaciations. And then on the other side, just theoretically using like an atmosphere ocean equilibrium like assumption, if all of the carbon stocks stored by the BCP and were removed from the ocean, atmospheric CO2 levels would be over 100 parts per million higher. And to remind us the context, like atmospheric CO2 was about like 320 before industrial era. Now it's like risen to 420. A difference of 100 is huge. And out of the proportion of the concentration in the atmosphere right now, 420, that's huge. So my overarching research questions is like, how much carbon does the biological carbon pump store right now? What processes affect its strength? And is it going to strengthen or weaken in the future? In our recent paper, we compared observational estimates and also an ensemble of different global ocean biogeochemical models, their estimates of like key parameters measuring the ocean carbon, the biological carbon pump. And so the box plots are showing all these different models and the spread that we have in like the average amount and petagrams of carbon per year that the BCP is acting. Okay, that one's captioned correctly. So these are examples of biological carbon pump metrics. Net primary productivity is like how much carbon is produced at the surface by the biological carbon pump. Carbon export to 100 meters depth is how much of that actually reaches like the base of the euphotic zone, like kind of a relevant depth, because that's the kind of carbon that can be stored for longer. If it doesn't really reach that depth, then it can be remineralized and escape back into the atmosphere. You know, we look at carbon export to 1,000 meters depth. We look at ratios, so the amount that reaches a depth out of the total amount that was produced at the surface. That's kind of a measure of BCP efficiency. And so, yeah, there's a large spread in just the magnitude of this carbon pump and spatial patterns. But what's really uncertain is the temporal trends. So has it changed? Has its strength changed? And will it change over time? And I just want to point out that some of these models are from other countries. A lot of them are operated out of the US by federally funded universities and government agencies. And so my contribution, my current work is I'm adding a new model of the biological carbon pump, and it's kind of a data-informed approach. The abbreviation is OXCAR because we're using oxygen observations to infer stuff about the carbon cycle, export, and fluxes. And what it's adding to the ensemble is a little relatively underrepresented. It's an inverse model. Most of the others are forward models, which mean they're like process-based, where they explicitly, they'll have a variable. They'll be like, here's small phytoplankton, here's large phytoplankton. We are going to mimic these processes and try to simulate data. And inverse is like you take the data and then try to find a model, like a mathematical representation of it that explains the data. So inverse models are strong, and they're great in theory because we can be more true to data, but like the complication is that Earth data coverage can be kind of sparse and have its own observational errors. My model, OXCAR, relies heavily on mostly oxygen data, and it's collected from ocean observation campaigns, including GLODAP. This is showing some ship tracks from GLODAP. There's almost global coverage and like 100 observations per month that makes this possible. And like the forward models as well as mine rely on data, and these are just some I'm pointing out that I rely on heavily. GLODAP is the Global Ocean Data Analysis Project, which is funded through NOAA, the Department of Energy, and the NSF. The World Ocean Atlas, the NCEI branch NOAA, GeoTraces. It's international, but it was supported in large part by the NSF. And these things, they're like research expeditions. That's what the funding goes to. They collect data. It funds the scientific analysis of the data, and they foster a lot of international collaboration. So I think I'm running out of time, and I expected this to happen, but I'm going to see. All right. I'm just going to explain a little bit how this particular model works, because modeling is a little like, how does that work? It seems like weird math magic, and it kind of is. One of the ways that my model works is like from these observations, I know what processes are going on. And so in the oxygen data, you'll see a decrease with depth. And that's because, like I was saying, microbes consume organic matter when they perform respiration. And so that produces the products that go into photosynthesis and takes up the things that photosynthesis would do. You can think about the photosynthesis equation going back and forth. So oxygen is consumed when decomposition happens. And so for a model grid that's like 3D, we can see this vertical gradient, and it kind of follows a power law curve. And, I put some adjustable parameters there, and I optimize my mathematical expression of this to best match the observations. And that gives us the term for respiration. And then there are other terms. In the end, we get carbon export. I know the timing has been difficult today. I think I need to probably conclude and have time for questions. But the main points here are that the ocean carbon sink is projected to decline because the solubility pump, we're getting way too saturated in CO2. So it's not going to be able to help us as much, and that could be catastrophic. We don't know what's going to happen with the biological pump. Most models agree that it's going to weaken because of stratification, because of ocean warming, but we don't know the extent, and we don't know what ocean regions and what phytoplankton communities are going to be affected. And we also don't know for sure that it will weaken because, life finds a way. In the ocean, especially, phytoplankton groups, they can adapt and evolve so rapidly. So monitoring this is kind of my deal, and I just wanted to bring attention to that and thank everyone that has tuned in and helped organize and spoken today. Thanks. I'll take questions.
Thank you so much, Kayla. So cool that you're developing this new model, and also thanks for explaining how observations factor into model development as well. We have time for one quick question from Empress Ariana. So if a place full of carbon, like the Dogger Bank in the North Sea, which I'm not familiar with, but you might know, if a place full of carbon is submerged, then does the new makeup of the ocean floor impact the carbon levels in the water above it?
The bathymetry, can you repeat that question?
Yeah, so if there's a part of a piece of land that's full of carbon, then it becomes submerged, like Doggerland in the North Sea.
Oh.
Does the makeup of the ocean floor, the new ocean floor, now impact the carbon in the water above it?
Yeah, it would depend on, I'm not familiar with that area in particular, but it depends what kind of land is being submerged. It's a little out of my area, but when land gets submerged, if we think about most coastal areas, that sediment is, it's made up of quartz, and if there's any biological material there, like in the soil, then it could be potentially, it might be, I don't know, it really just depends on the land cover type. I wish I knew what land surrounded that part of the North Sea, but I'm not sure, and that is a very complicated question.
Thank you for your time. There's like a bunch more questions that people are putting in the chat, so I think I'll have you sign off now, but then maybe continue answering questions in the chat. Everyone say thank you to Kayla for joining us today.
Thank you.
Okay, so next up we have Gretchen Keppel-Aleks, who's a associate professor and will be talking to us, I think, about more carbon cycle related things.
Hi, all right, I'm excited to be giving another talk on carbon cycle. It's a privilege to follow Kayla, who I actually got to advise when she was a master's student. I'll be talking about terrestrial carbon cycling, although so it'll be slightly different. Again, we've got to start with this Keeling curve. This is almost 70 years of nearly uninterrupted observations of atmospheric CO2. And I'm an atmospheric scientist, and what I do is to try to understand what we can learn about carbon exchange between the atmosphere, oceans, and terrestrial ecosystems based on the temporal patterns we see in time series such as these. So the longer the time series, the broader the scientific questions, the more interesting research that we can do to try to understand our planet. And it's always worth saying that that long-term increase that you see is unambiguously driven by human activities. So this is a time series of anthropogenic emissions of CO2. Time is on the x-axis, emissions are on the y-axis. You can see this increase since 1960, even during COVID, when we were all stuck in our houses, people weren't driving, people weren't flying. We had a small reduction and emissions came roaring back the following year higher than ever. So humans are driving the long-term increase, but I think as Kayla mentioned in her talk, that increase in the atmosphere is being buffered by the natural carbon cycle. So on this figure, above this zero line here, you can see sources of carbon to the atmosphere from fossil fuel combustion and land use change. If we go in and deforest ecosystems, that releases carbon back to the atmosphere. But you can see the sinks. So the stuff that ends up in the atmosphere is the cause of greenhouse warming that we're unambiguously experiencing. But you can see that 55% of the carbon that we emit goes either into the ocean or into the land. And those sinks are about 2.5 to 3 petagrams carbon per year at present. So we're emitting about 40 gigatons of CO2. That's roughly 10 gigatons of carbon. And so we've got these nice big sinks that have increased even as emissions have exponentially increased. So that long-term trend being mitigated by these processes in terrestrial ecosystems and in the ocean, we need to understand what mechanisms are driving that so we can make predictions about how the carbon cycle will change in the future as it gets warmer and as the concentration of CO2 potentially increases if we continue on a business as usual path with increasing emissions. So I said that the terrestrial sink was about 2.5 to 3 petagrams carbon per year. It's worth noting that terrestrial ecosystems worldwide, that's forests, croplands, grasslands, you name it, are taking up about 150 petagrams of carbon per year. So 50 times as much through photosynthesis. And that is, if you live in the Northern Hemisphere, it's got a distinct temporal pattern. So on this figure here on the right, you can see months of the year, and you can see that that flux is going to peak in the summer when it's nice and warm and there's a lot of sun. Now, plants have to use some of the carbon that they fix, and by fix, I mean they convert CO2 into sugars via photosynthesis. They burn some of those sugars themselves in a process called autotrophic respiration so that they have energy to grow or repair their tissues. But the rest of that carbon is available for the rest of life on Earth. So heterotrophs, you and I are heterotrophs. We have to eat other things for the energy that we need to support our metabolism. But things like bacteria and fungi that decompose dead organic matter are also responsible for the bulk of the work that returns carbon that is fixed by photosynthesis back to the atmosphere as respiration. That also has a pretty distinct seasonal pattern in the Northern Hemisphere. It's not light limited, so you can see that it is possible for heterotrophs to be respiring year round. And the imbalance between these processes caused the seasonal patterns that you saw in the Keeling curve. So it's worth noting that these processes are extremely sensitive to climate. So higher temperatures can affect the uptake of CO2 from plants because plants have to balance taking in carbon from the atmosphere with losing water. So CO2 goes into plants through holes called stomata on the underside of leaves. And the width that those stomata are open is variable. So you can see in this figure on the right, there's an open stomata on top and a closed stomata on the bottom. So if it's really hot or really dry and a plant wants to maintain its water, it will shut those stomata because there's this trade-off that needs to be maintained. So this has a big effect on climate. So plants are not just affected by the climate, but they also drive climate. So if you think about a forest as vast as the Amazon, plants are transpiring water through their stomata into the atmosphere. That water can condense and form clouds. When the winds transport that moisture to the east across the Amazon, that drives precipitation further to the west. Sorry, I might have got my signs wrong. So the Amazon actually recycles 50% of the rain that falls in the Amazon is created by the forest itself. It's not water that's coming off the ocean like it is in most of the continental US. It is water that is actually coming from ecosystems. So if we change this region, for instance, we decide we all need to eat hamburgers all the time and we convert the rainforest into pasture land so we can raise cows, that is going to reduce transpiration and that's going to reduce precipitation in the Amazon. And I don't know if you can see this very well, but this is a tree in the Amazon. You can see a water line that's about 12 meters off the current water line. So the Amazon has been experiencing drying, some of which is attributable to climate change and some of which is attributable to human activities. So there's this two-directional coupling between the climate and ecosystems. So another way that climate can affect carbon cycling is that depending on the base climate, so if you're in a cold place, higher temperatures can speed up the rate of photosynthesis. So photosynthesis occurs when CO2 binds with an enzyme called rubisco and an existing carbon intermediary within the plant to kick off the chemical reactions that create sugars. So this is a pretty amazing process. Rubisco, this enzyme that helps facilitate photosynthesis, is the most abundant protein on planet Earth. And photosynthesis, as I said before, is the basis for all of the food chains of which we also are a part. So if you're in cold latitudes up north, this process speeds up under climate change with warming temperatures. But if you're someplace like tropical forests where it's already quite warm, if temperatures increase further, then the selectivity of rubisco, which has this sort of special key structure where only CO2 is supposed to be able to bind to it, it actually becomes less selective. And so oxygen can start to bind with rubisco and slow down the rate of photosynthesis. So depending on where you are, photosynthesis can be affected by temperature in that way. So as I mentioned, the patterns in photosynthesis in green and these respiration processes that you can see here set the patterns in atmospheric CO2. So you can see that when photosynthesis first outpaces respiration in the year, CO2 starts to decline. And then at the end of the growing season, when photosynthesis declines and respiration becomes higher, CO2 increases. And we saw those patterns in the Keeling curve, this sawtooth that you can see here in red. And I said, as an atmospheric scientist, I'm really interested in how those temporal patterns and the spatial patterns that we have from being able to measure CO2 in multiple places give us insights about whether vegetation is becoming temperature stressed or whether it's becoming water stressed. And those patterns of fluxes are changing in response to our changing climate. So this figure was created with data that comes from NOAA's Global Monitoring Lab. They have maintained a global network of CO2 observations. These data are publicly available, freely downloadable by anyone, anywhere. And in terms of what we might lose under the current threats to federal funding of climate data, it's not just the record in Hawaii, it's all of these sites around the globe that are supported by federal funding in part. Look at this dense network over the United States. That is your tax dollars at work for those of you who are here in the US. So that seasonal cycle is something that I find particularly interesting to study. It has been a topic of interest since we started collecting those observations in Hawaii, and especially as we expanded them over the globe. You'll notice on this diagram that shows month of the year and latitude that the seasonal cycle, shown as this transition from red to blue, is most pronounced in the northern hemisphere. And the reason for that is because we have this boreal forest up here, and there's no austral forest if you look at the same latitudes in the southern hemisphere. So in the boreal forest, those are places that tend to be pretty cold. There's not a lot of sunlight during the winter and even in the shoulder season surrounding winter. So plants have a pretty short amount of time during peak summer to photosynthesize all of the carbon into sugar that they need to meet their energetic requirements for the whole year. So that rapid drawdown is thought to drive the seasonal cycle. And quantifying how much carbon is taken up by vegetation in the northern hemisphere has been one of the earliest questions that carbon cycle scientists have tried to answer. So these are some really cool figures from a paper in 1983 that show some of the earliest computer simulations where we tried to fuse atmospheric CO2 observations together with our understanding of ecosystems to quantify CO2 going in. So we've seen a lot of beautiful color figures that are generated with the contemporary models and observations we have. Here we've got like essentially an ASCII map of the globe with numbers indicating what we think net ecosystem exchange could be. But even in the 80s, we were pioneering, and this is work from Inez Fung, we were pioneering these methods that have grown today to the types of models, if you watched the last talk, that Kayla is using to better quantify ocean exchange. So of course, quantifying the amount of carbon going into the biosphere during the growing season is not a static number. One of the things that we've observed, thanks to these long-term observations of CO2, is that the amplitude of the seasonal cycle, so if you look at this difference from the peak to the trough of the seasonal cycle, that's growing with time. So here are two long-term observing locations, Barrow in northern Alaska and Mauna Loa in Hawaii. Time is on the x-axis and the seasonal amplitude is on the y-axis. And you can see that at both of those locations, the amplitude has been increasing over the last 50 years by as much as 0.6% per year in Alaska. And if you look on this bottom row of figures, these are showing aircraft observations made in the middle of the atmosphere, so at 500 millibar. The purple data are from around 2010, the black data are from around 1960, and you can see that amplitude increasing as you go from south to north. So clearly, northern high latitudes are seeing increased amplification relative to what we see in the subtropics. So why is that? One of the things that we've observed is that high latitudes are changing rapidly. So this is a map that shows the temperature trend across boreal and Arctic ecosystems. And you can see that in many locations, temperatures are increasing by around 0.5 to 1 degree Celsius per decade. That's a huge amount of warming. And Arctic amplification is probably something that if you've been watching this live stream, you've heard about before. So temperatures are increasing. And what can that do? Well, this is a cold region, so we might expect that photosynthesis will increase, as you can see in this dashed line. But it also might increase rates of respiration because metabolism of dead organic matter is also temperature dependent. So those processes being altered by changing temperatures would lead to an increase in this amplitude. But you can see from this map that temperatures are changing differently in different parts of the Arctic. So there might be a spatial signature that we can detect from our atmospheric CO2 observations. Another thing that could be happening to drive this increase in CO2 amplitude is called CO2 fertilization. So as I said before, there's a trade-off in taking up CO2 from plants and losing water. And so if there's more CO2 in the atmosphere, plants could close these stomata and still get the same amount of CO2 through their stomata while losing less water. So that would possibly have an impact only on photosynthesis, and it would lead to a slightly different pattern of increase in the resulting CO2 amplitude. So as I get to be sort of a carbon detective and figure out how to use very subtle changes in these CO2 time series to understand which of these processes seem to be at play. One of the ways that we've done this is using these atmospheric inverse models. That's where we optimize fluxes in different parts of the globe by trying to match the ensemble of CO2 observations that we have. So we use a weather forecasting model with a first guess at what terrestrial photosynthesis and respiration looks like. And we ask, like, how do we need to nudge those fluxes to match the observations that we have shown here on these dots? And what we did after we had those optimized fluxes is then we reran them through an atmospheric transport model, and we tagged them from regions. So we could say, how much does this yellow region, so Arctic Boreal North America, contribute to the amplitude compared to this sort of tan region? How much does Siberia contribute to that amplitude? So you can sort of see each of these tracers in different colors, some to create an overall tracer, and we're comparing the peak to trough for any individual tracer compared to the peak to trough for the overall tracer. And what we found when we did this is that for boreal ecosystems here, North America and Siberia contribute about the same amount to the mean CO2 amplitude. And together they contribute about as much as mid-latitude ecosystems, most of continental US, contribute to ecosystems. But if you look at the difference in amplitude, so how much has it changed over 40 years, you can see that Siberia contributes about a factor of 3 to 4 more to the amplification that we're seeing in the amplitude compared to North America. And that it's pretty comparable to what mid-latitude ecosystems are contributing to that amplification. So one of the cool things about this is that using atmospheric CO2, we're able to sort of verify results that are coming from satellites that are measuring greening, that show that there is more browning occurring in boreal North America than there is in Eurasia. So it's really great in climate science, given all the variability, that you can use 2 different techniques to arrive at a similar result. And we're going to further use space-based observations from satellite to try to understand why ecosystems are responding so differently in Siberia compared to North America. So one of the amazing things that has been developed in about the last 15 years is the capability to observe plants fluorescing from space. So if you mash up chlorophyll and put it in a beaker and pulse a light at it, you can see it glowing. And we can see that from some of the satellite assets that NASA has launched. So these are maps of what's called solar-induced chlorophyll fluorescence. This is December, so Northern Hemisphere winter, June, July, August, Northern Hemisphere summer, and you can see plants are fluorescing in the places where growth is happening. So we're going to use those patterns to try to understand what's different between North America and Siberia. And this is a brand new paper that just came out a couple weeks ago from a graduate student, Dan Muccio, who looked at the temperature sensitivity of Western North American, Eastern North American boreal forest, European boreal forests, and Siberian boreal forests. And so the y-axis is the regression between the strength of that fluorescence signal and temperature variations. And if you look at this green bar, that's Siberia, you can see that Siberia is much more sensitive to these temperature variations than any of these other regions. And if you look at across the growing season, most of the regions only show a strong temperature sensitivity in the spring, whereas Siberian forests are showing strong temperature sensitivities throughout the growing season. So this means that under current warming, given that this is a cold location, it seems like Siberian boreal forests have been able to sort of take advantage of warming to increase their growth, which increases the amplitude of CO2 in the atmosphere. But there's no free lunch. There's always some caveat. If we look here at Western North America, on the x-axis, we're showing temperature trends, and on the y-axis, we're showing the SIF trend. And all of these black dots are pixels within North America, Western North America. And you can see there's a slight negative relationship. And what that means is that the pixels in Western North America that are warming the fastest are actually seeing the smallest increases in SIF, or the smallest increases in photosynthesis. So as it gets warmer, especially in North America, we would actually expect productivity to start to decline. We don't yet see that in Siberia, and that's work that we have underway. We think that region it's probably less sensitive to moisture stress compared to what we see in Western North America. We've also recently have a paper come out that shows that in temperate ecosystems, the amplification that they're contributing to CO2 is due to fertilization of agricultural systems. So here in black, we have observations. Again, we're looking at Hawaii and Alaska. And we have two different flavors of model. In purple, this is a model that includes agriculture, fertilization, the impacts that we have on land management. And in yellow, we don't have those processes. And you can see that when we don't include that, the amplitude of CO2 is smaller and the trend isn't as striking. And you can see that these patterns of CO2 crop fertilization that we see in croplands and climate change in high northern latitudes leave very distinct spatial patterns. So that means we need to be able to observe the carbon cycle every place as rapidly as possible. So a lot of the insights that we have from SIF are from NASA's OCO2 satellite. You can see in red tracks what we can see from that instrument. We're covering most of the globe, and we can observe the whole globe every 2 weeks. If you have been on for a while and saw Liz's talk, you know that these satellites are starting to sunset. The US led the development of the first CO2 observing satellites, and we don't have anything planned to replace OCO2 when it expires. So to sum up, there's a lot of interesting things happening in the carbon cycle. The long-term observations we have from the surface and the spatially explicit observations we have from space are something that need to be protected. And I will close there.
Thank you so much, Gretchen. We have lots of plant lovers in chat right now, and some great questions. So question from Sarah. I think this is about some of the relationships between like plant productivity, like stomata functioning, and all these like atmospheric conditions. So when it comes to the trade-off between water and carbon dioxide absorption, is there a worry that this trade-off, and like maybe if we think that plants are optimized to live in certain climatic conditions, is this going to lead to change in ecosystem species composition, like with anthropogenic climate changes?
Yeah, absolutely. There are definitely some species of plants that are better adapted to drought stress. And in fact, for you plant lovers out there, there are different types of photosynthesis that occur. There's C3 photosynthesis, which is what plants use. There's C4 photosynthesis, which a lot of grasses use and like corn uses. And then there's CAM photosynthesis, which succulents in deserts use. And C4 is adapted more to higher temperatures. CAM exists as an adaptation to water stress. So there might be changes, just based on the type of photosynthesis that the plant is using, but also the sort of timing of when plants put leaves out might mean that certain plants can adapt better to certain ecosystems, especially as like the timing of temperature changes and moisture changes relative to having adequate sunlight change. So we have seen shifts in ecosystem composition, and we'll probably see a lot more going forward.
On a similar note, we have a question about like specific ecosystems. So what is the boreal tundra contribution to transpiration? And are there any thoughts about how like changes in high latitude plant transpiration may impact cloud cover and in turn albedo?
Yeah, great.
Question, by the way.
Yep. So, the tundra ecosystems are certainly extremely vulnerable to global change. They contain much smaller plants that overall fix a lot less carbon and therefore transpire a lot less. There's a thought that as warming occurs, forests might move further north. So that would impact the albedo because these forests tend to be darker than the tundra plants that exist. But the big carbon cycle risk from the tundra is that region contains a lot of soil carbon in what's called permafrost. So buried in the subsurface, there is like roughly a factor of 2 to 3 times the amount of carbon that's currently in the atmosphere that's frozen in soils. So if temperatures increase too much and that those soils start to thaw, I mean, it's the same thing that you could imagine, like if you unplugged your freezer and just let the food in it stick out, all of that would start to decay. It would be vulnerable to microbial decomposition, and that could put a ton of CO2 into the atmosphere. So that's one of the big carbon cycle uncertainties about tundra ecosystems.
We're still waiting on our next speaker, so if you don't mind, we're just going to keep going with all the plant questions. Like literally the chat is flooding right now. So question from G. I'm going to try my best to understand the question you're asking, but feel free to clarify in chat. So I think this is a question about how, like, with modern biotechnology, we're selectively growing these plants to be resilient to certain things like heat and also for maybe biodiversity, but does that lead to like a reduction in their CO2 uptake, and does that have an impact on CO2 composition of the atmosphere? And like, is that something that's a concern for the carbon cycle community?
So like if I understand, it's sort of asking about whether we could potentially manage ecosystems to try to get them to store more carbon. And this is sort of an area of research, but something that could be done in areas that are already managed. So croplands, for instance, there are certain types of plants that allocate more biomass to their roots. And so if you're growing like a perennial wheat as opposed to an annual wheat, and you don't till your agricultural field, then you can promote greater carbon sequestration into the soils. People are looking into, developing crops that could be grown in that way to try to facilitate more carbon storage. But it's worth noting, and one of the reasons that I put in the talk that plants are photosynthesizing and respiring almost 150 petagrams carbon per year, and that leads to like a 2 to 3 petagram sink. So in general, ecosystems want to be in balance, right? Like in the same way that your body wants to be metabolically in balance, right? Like you eat the amount of food that you need based on the amount of energy that you're burning in your daily life. If you ate too little or if you ate too much, you would start to have issues. Like in general, ecosystems are in balance. And so some of these strategies to try to promote greater carbon uptake in managed lands, they might be short to medium term solutions, but over long timescales, what goes into ecosystems is going to come back out. So we need to keep in mind that ultimately what we need to do is to stop burning fossil fuels.
Thank you so much, Gretchen. There's still a bunch of questions in chat, but we do have to move on to our next speaker. So if you could stay online and answer those questions in chat, I think our viewers would super appreciate it. Everyone say thank you to Gretchen.
Thank you.
Okay, so up next, some of you earlier were saying that you really liked this cool term biogeochemistry that was introduced during some of our talks. And now we have Professor Dennis Baldocchi, who's a professor of biometeorology, which is a very new term to me, but sounds super cool. So let's have Dennis talk to us about the breeding of the biosphere.
Well, hi, everybody. This is really a great series. I really have enjoyed all the talks and learned so much. And this talk here will really dovetail very nicely with the past two talks we've been listening to, essentially. So yes, I'm going to talk about breeding of the biosphere as a biometeorologist. And you might want to try and understand why, and we'll talk about it. My background comes from really being a farm kid in California, and spent a lot of time driving tractor through orchards and pulling irrigation pipes. So I was always somewhat interested in how weather and climate affect our vegetation and our water use. And I was able to actually go to 4-H as a youth and got exposed to the atmospheric science program at UC Davis. And there we actually had a lot of crop courses. So there's a nice blend of agriculture and meteorology. And from there, I was able to go to the University of Nebraska for my PhD to really study this in more detail. And as you may see, I'm a former proud NOAA employee. And so I've really been happy this whole enterprise is going on to really support NOAA. I was at the Atmospheric Turbulence Diffusion Lab in Oak Ridge, Tennessee. We were part of the Ocean and Atmospheric Research Unit of NOAA. That's going to be zeroed out in the next budget if that goes forward. So yes, we got a lot to show you here, essentially. So breathing the biosphere. I'm a biometeorologist, but I'm also a micrometeorologist and an ecosystem ecologist. And from that, we kind of bring these skills together to really understand how plants absorb carbon dioxide and how they produce oxygen, and then how their components will decompose by microbes and produce carbon dioxide and other greenhouse gases. And so really the question gets back to what is breathing the biosphere and why should we care as ecosystem ecologists and biogeochemists? We often hear a lot about in the previous talks about the photosynthesis equations, but what really happens is plants have to capture sunlight. They're solar collectors, and they essentially use that energy to split water to release electrons. So effectively, we're like little batteries. And it's those electrons that are transferred through the various reactions that Professor Gretchen showed a few moments ago to form chemical compounds like carbohydrates. We then use that, and that releases electrons to drive our metabolism. And often oxygen is the key electron acceptor for this. But once you get into these other sediments and there's less and less oxygen around, different microbes take over. And they can actually produce a whole other set of greenhouse gases, nitrous oxide, N2O, methane. These are some of the ones that people like me worry about, essentially. Now, why do we worry about greenhouse gases? Well, I think over this 100 hours, you've seen many explanations, but this is the one I kind of like. We have two types of energy in our world. One is from the sun, and the sun is almost 6,000 degrees Kelvin. And if you follow Planck's law of the probability distribution of this light, it peaks at about 0.4, 0.5 microns. Well, that's the wavelengths we see. That's the visible light. That's also the wavelengths of energy that drive photosynthesis. So plants, cyanobacteria, have evolved over 2 billion years to actually capture light energy in those wavelengths to do the things they do. Now, all this energy heats the ground, evaporates, creates sensible heat, and it now makes our Earth about 298 degrees Kelvin on a sunny day, 30 degrees Celsius, 70, 80 degrees Fahrenheit. That radiation now, according to Planck's law, emits energy in the order of about 4, 5, 10 microns. Now, why is that important? Well, if you look at the spectroscopy of elements of greenhouse gases like carbon dioxide or nitrous oxide or methane, they absorb and re-radiate energy at these long wave radiation levels. This is what keeps the Earth warm enough for life. It keeps us above freezing, as the student said earlier in the talk. Without this atmosphere and these greenhouse gases, our surface would be about minus 18 degrees Celsius, and everything would be frozen, and we wouldn't be giving you this talk. So it gets back to what shall we do? What are some of the evidence of the breathing of the biosphere? Well, again, you've seen this Keeling curve many times. What's really eye-opening to a person like me is I was born in 1955 before the record started, so my bones had CO2 around there about 310 parts per million. As a grad student, I was making measurements when it was about 310, 320 parts per million. And I was out in the field 2 days ago, and we're measuring 420 parts per million, over 100 parts per million. Change in our lifetime. What I'm interested in is the breathing of the biosphere, which is these wiggles here. And other scientists will be interested more in these trends with climate. But again, to give you perspective, the world for the last 800,000 years, when the human species evolved, has just oscillated back and forth between about minus 180 parts per million and 280 parts per million. So in essence, 100 parts per million changed over maybe 100,000 years, several times between ice ages and interglacial periods. And now I go back and we've changed this in my lifetime. This is kind of a wake-up call for us to think about the breathing of the biosphere. One of the biggest proofs of this coming from fossil fuel combustion gets back to this idea of stable isotopes. It's a complex idea, but it's funny when I actually teach my Berkeley freshmen, sophomores students about it, they really get it. Most of carbon dioxide is based on CO2, with carbon having 6 protons and 6 neutrons. But there's a small fraction that has C13 with 6 protons and 7 neutrons. It's a little bit heavier, and photosynthesis favors the lighter versus the heavier. So when you think of what fossil fuels is, it's coal, it's old plants. And so when we're burning that material, it has an isotopic signal of minus 25 per mil. So if you look at the ice core before the industrial age, we were about minus 6 per mil. And all of a sudden we start burning more and more carbon dioxide from fossil fuel from plants, and we're making this negative and negative and negative. So it really is showing that the combustion of fossil fuels causing this rise in CO2. So the work I want to do is on fluxes. And it's interesting, when we study the biosphere, it's very complex. It has many degrees of freedom of size and space and time. And there's no one easy, perfect way to study it. So you need a bunch of methods, and you got to see them converge. People like the last talk use the so-called top-down method, which is fantastic and gives us these big constrained budgets. But we also want to know what's going on at the smaller patches using a bottom-up approach. So what we'll concentrate here in the rest of this talk is about fluxes. We'll talk about what fluxes are, why measure fluxes, how do we measure fluxes, and of course, what are we discovering? So fluxes in simple terms is just the number of moles of a gas like CO2, or we could even think of joules of energy that are passing across a unit area for a unit time. And often in our studies, we're actually looking at the flux density across an ecosystem between the atmosphere and biosphere. Why we measure them? Well, I like to say we start with the conservation budget of the atmosphere. We can start with the bathtub, except the atmosphere is a leaky bathtub. But the bottom line is the level of water in your bathtub depends on the flux going in and going out. If you have the faucet on and the plug off, that water is going to rise up. And that's going to be related to that flux into that reservoir. And so this is why we as micrometeorologists, biometeorologists are trying to measure fluxes at the land surface interface. Another way to get example of this is just measuring some concentrations of carbon dioxide over the course of a day over a alfalfa field. And here, again, you can kind of see the breathing of the biosphere. At night, you're seeing concentrations increasing. They're going up to about 450 parts per million. Sun comes up, CO2 starts dropping down to about 400 parts per million. And then it increases again. Well, what's happening? It's due to the fluxes. So at night, we have what's called ecosystem respiration. The plants are respiring because they're consuming that carbon that had been stored to do their metabolism. The stems are respiring, the roots are respiring, the plants are exudating carbohydrates to the microbes. The microbes are breaking down carbon and they're respiring. As the sun comes up, you start seeing this drop in CO2 exchange. So the positive signs means the atmosphere is gaining carbon dioxide and the land's losing it. And the negative signs mean we're pulling CO2 out of the atmosphere and the land vegetation is gaining it. And so by midday, when the sun's up the highest, we have our highest CO2 peaks. If we can separate our respiration from our net flux, we can actually measure now photosynthesis of whole ecosystems, which is really amazing. So this gets back to how do we measure fluxes, and especially of a collection of plants and trees and the underlying soil. Historically, ecologists would use what you can really call a brute force method. They might have put a couple chambers over a leaf and measure the change in gas exchange as that leaf is photosynthesizing. They may have put a chamber on the soil, and as the soil liberates gases, they can see the changes. But this is our manual. They take a lot of time, really small footprints. Historically, other ecologists might have on an annual basis used chainsaws, shovels, measuring tapes, and scales, and just looked at the incremental change of the biosphere. A bit destructive, and it doesn't show you how and why you got there. As a micrometeorologist, we've been trying to use models, somewhat like the oceans talk you saw maybe earlier, but we break up the whole ecosystem into many, many layers and look at the sunlit shaded fractions of the ecosystem and try to model the photosynthesis, transpiration, temperatures of these leaves and add them up. And then finally, us as micrometeorologists use what's called this eddy covariance technique. And I'll talk a lot about this in the remainder of the talk. The eddy covariance technique is the direct measurement of net flux between the atmosphere and biosphere. You'll hear a lot of other methods, but often they're inferential. They're making some assumptions. What we're essentially doing is with a sonic anemometer, we're measuring 10, 20 times a second every updraft and downdraft that's occurring with this set of sensors. Within those updrafts and downdrafts will be changes in carbon dioxide, temperature, methane, CO2. By looking at the differences in the fluctuations and multiplying them together and averaging them, that gives us a flux density over the half hour of what's been going on. It's really kind of cool. What's also kind of nice about it is that we can actually measure the flux over a pretty big footprint. We don't have as much of a sampling problem because we're actually measuring the population of plants in tens of hectares, maybe 100, 200, 300 meters upwind. The sensors have gotten so reliable, we're making measurements 24 hours a day, 7 days a week, not only for years, but for decades now. My lab has collected over 130 site years of data right now because of the high quality and the reliability of these sensors. We can put them out in the middle of nowhere on solar panels without pumps, and it's just revolutionized how we study the breathing of the biosphere. But a lot of this really comes back to NOAA. When I was at NOAA, I had a great colleague, Tilden Myers, and our lab director, Bruce Hicks, was really one of the pioneers of the eddy covariance method. And they essentially developed this early prototype of this open path CO2 water vapor sensor. And so I was able to go to Boreas with Sue Trumbore and others to make some of the first transpiration and CO2 flux measurements over a boreal forest in the 1990s. And we were able to build on this going forward. Commercial companies like Lycor have actually now commercialized these. So thousands of scientists around the world are able to make these types of measurements continuously. So let's get to the science. So we can make these measurements. What are we learning? What are we doing? Well, I think the first key is if we're studying the biosphere and its breathing, we really have to think of the carbon, water, nutrient, and energy fluxes as a coupled system, essentially. Obviously, we want to know how much sunlight's absorbed, and that's going to be a function of the leaf area index of the landscape. That itself will be different in different parts of the world based on climate, length of growing season, whether the plants are dormant or not. Once that energy is absorbed, there's a cost for photosynthesis. Those stomata that you just heard about will open for carbon uptake, but they also lose water vapor. So there's a tight coupling for that. How fast these things work depends on how well the leaves will drop into the soil and decompose and release nitrogen that drives the photosynthetic capacity and the amount of nitrogen that drives rubisco. And then this all kind of affects clouds and rain and droughts. And it's really a neat story, but it's really has to be studied in a coupled system. So here's some of our data. Just for convenience, I took 22 years of data. I binned them by 2-week periods, and I looked at it every half hour over the course of the day. So what we can kind of see is at night and the peak of the summertime is when we have the highest respiration rates with the highest photosynthesis rates. This is kind of in the spring. This is California, so we have our wettest seasons around April or so. Now we have this wonderful natural experiment because it quits raining. And so the landscape's getting drier and drier and drier. So you see this families of curves as how the ecosystem responds as the ecosystem gets drier and drier. So we can actually see these things real time. And this actually can form the basis for doing budgets and for validating models, validating remote sensing models. A lot of the remote sensing models will look at light interception and try to calculate photosynthesis, and then they're validated with these flux measurements. The other cool thing is because we can collect so much data, we can now use modern machine learning statistical techniques. One of my former students at NASA GISS, Nancy Kiang, was using this alternating conditional expectation method. And we're able to actually use this by essentially holding one variable constant, or holding all the other variables constant that are affecting photosynthesis in the field: light, humidity, soil moisture, time of year. And then we can look at response curves about how light is affecting photosynthesis, or given constant light, how vapor pressure deficit is, or soil moisture, or temperature. This temperature one's important because we do have an optimum temperature for photosynthesis, but with global warming, the thing that worries us a lot is as you get warmer, this curve bowls over and just crashes. So really quantifying these response curves is really critical to understanding the breathing of the biosphere. By taking long-term measurements, we can also help inform natural climate solutions. So how much carbon does this oak savanna in California take up? Well, I throw discus, and Olympic discus weighs 2 kilograms each. I'm old, so I get to throw the 1 kilogram one. But effectively, we've been taking up about 2 Olympic-sized discuses every meter for over the last 20-something years. So that's a lot of carbon, essentially, that's being taken out of the atmosphere and stayed there for a good time, essentially. As we start making these measurements over many other sites, we kind of come up with these generalities that I think are important for us to think about. I like to talk about these rules of physics that biology has to live by. Clearly, we have to have photosynthesis exceeding respiration, otherwise the plants die. There is a cost of photosynthesis, which is evaporation, but that evaporation has to be less than the precipitation of that region. And so there's various ways that can happen. You can have gradual closure of the stomata, which we often see in our California sites. You could have either reduced leaf area index, which we see with our savannas, these widely spaced trees, or you could have actually drought deciduousness, as we may be seeing in the tropics where the leaves drop out earlier. Some plants can be clever and they can have deep roots and access groundwater. And so by having these measurements on the ground like us, we can see things that you may not study and observe with remote methods, essentially. So it's really key that we get our feet dirty and our hands dirty. But ultimately, we want to say, what's the big question? And the big picture question for all of us is ultimately understanding the breathing of the biosphere everywhere, all the time. And this is really, it is a big challenge, and not just one person can do it, or even one team. It really takes a community. Within the Flex community itself, we have what's called FlexNet. It's a global community of flux measurement sites. I was a PI in the early days for this, but we work a lot with the different regional networks, like in Ameriflux in the Americas, ICOS in Europe, Asian groups. There's hundreds of sites. And what's really key is that we collaborate, we share data, and therefore that data can go to you all as students, as modelers, as other policymakers. And so this is really what's so wonderful about our community, to be honest with you. I saw the talk this morning with Sue Trumberg and Nikki Gruber, et cetera, and it was really inspiring about how we work as a community. How much carbon is taken up across the world? Well, the central tendency is about 150 grams of carbon per meter squared per year taken up. What's that mean? Well, I'm in Marin County right now, and it's a nice little wheel of our local cheese, I'm sorry. What can be used for solutions? Well, I'm now working in the Sacramento Delta with restored wetlands. And we actually have a field site literally across the street where I grew up on Dutch Slough. And we're taking up 850 grams of carbon. These tidal wetlands are amazing because by having flooded landscapes, oxygen doesn't get into the sediments for the microbes and peat builds up. And so you're not decomposing. Because normally with the flux world, about 85% of the photosynthesis that we build on the ecosystem scale on a year is returned back to the atmosphere. Huge cost of respiration to photosynthesis. And wetlands are able to actually bury this stuff long term. Now, clearly, if we want to do this stuff globally, we have to think about these feedbacks. We have to think about the various processes that are physiological, micrometeorological, biogeochemical, stand dynamics, and tying these things together. I like to joke to my students, this might be as complicated as rocket science. These are complex systems very nonlinear with so many, and this is why you have 200 scientists talking to you and trying to think about this and make better models here. And so this is my attempt to come up with a global model. I use what's called natural neural networks. These simple schemes I talked about earlier were used and with gridded climate numbers, and these aren't too bad from the other fancier approaches. I think I calculated about 120 petagrams of global photosynthesis just with a simple approach like this. So yeah, our research has been funded by all these federal agencies. We couldn't have done this without the support of National Science Foundation, Department of Energy, NOAA, NASA, USDA, and the people that came before us. They provided the foundations from which we all are building. So going back to Darwin saying, "I've seen further because I stand on the shoulders of giants." It really scares the heck out of me that as we cut back on funding, all this will fall apart and it won't come together so fast. A colleague, Kristina Dahl, said it very eloquently. You can't turn science on and off like a faucet. It's more like a pearl where you have layer by layer by layer that builds up essentially. And so talk to your politicians, tell them not to be stupid and not cut off science. We depend on it so much. So my wife gave me hell. She says, talk to the people, make them care. So she has really stressed about the so what question. And since I have a PhD, I like to be a little philosophical, and we're civilized. And so obviously we need to be curious about the world about us, obviously. But more directly with our research, we want to understand the breathing of the biosphere to improve the coupled climate models. Some talks earlier talked about what's not happening in the Amazon. Big feedbacks between rain and clouds and forests dying, all because of the processes that we talk about here. And I'll skip this here because we've been covering it quite a bit here. So you asked me to end in hope and the future. Well, the problem of global warming and air pollution are not going away. These are clearly nonpartisan, and they won't go away until we choose to do something with it. Science, technology provide the best solutions for this. I really say we owe it to the next generation and humanity to do something as fast as possible. I'm a big fan that it's more effective not to put the carbon into the atmosphere than to try to remove it. Scale is such a big, big problem, essentially. And ultimately, as they also said this morning, truth and facts will defeat lies in the long run. A lot of damage might be happening in the meantime, but we got to be courageous and we got to work together. So I will stop. Looks like I have 4 minutes. So thanks for letting me yak at you. And it's been really a pleasure and an honor to contribute to this. And thank everybody for doing this, and y'all again. So.
Thank you so much, Dennis. What a great talk to cap off this unintentional carbon cycle session that we've organized for our live stream.
Good job on that.
We got lots of great questions. I know you're a biometeorologist, but I'm going to throw an atmospheric chemistry question at you. I think you can definitely answer. And someone asked, what is the role of atmospheric chemistry in estimating these fluxes that you talked about? And I'm actually going to add a question of my own on here, which is that you showed a lot of these flux tower sites, and talking about eddy covariance flux measurements. So could you also explain why we can't just use satellites to measure the fluxes? Is there a reason we're using these in situ sites?
Yeah, no, earlier in my career, I did collaborative work with people doing isoprene. So many plant species give off isoprene, which is a hydrocarbon that contributes in photochemical ozone production. And in fact, we were trying to use the models that we have for carbon and water and energy to actually come up with better isoprene models, essentially. My colleague, Alan Goldstein, when he was a graduate student at Harvard, took some of the first year-round isoprene measurements. And then I've worked with Russ Monson on that, and the NCAR fellows, Alex Gunther and stuff. So isoprene's harder because certain species give it off and others don't. I can kind of treat the biosphere where I work, irregardless of species, as kind of this green slime. And as long as I know my functional and structural traits, the model works really well. If I go into working with isoprene, I really need to know what species are in certain edges of the footprint. Methane, we've been measuring methane fluxes with our CO2 fluxes in our wetlands. And this is the big unintended consequences. So wetlands are a great opportunity to take carbon dioxide out of the atmosphere, but they're anaerobic. They don't have oxygen. They produce methane. Our ecosystems have long growing seasons and have some of the highest carbon uptake in the world. We also have some of the highest methane fluxes in the world. So there's no free lunch. And so again, this is where I get back, gotta just not put CO2 in the atmosphere. The Earth will heal itself over time because of all these processes, et cetera. But it's a complex system, and don't whack it around. In fact, that's the other problem. I mean, complex systems have a lot of feedbacks that when you beat them up, they don't do much until you hit them so far and they jump to the next state. And we shouldn't have that. We shouldn't do that. So, next question.
Okay, great. Yeah, one last question. So Silver asks, what are the easiest and most difficult biomes to model? Is it the biodiverse ones because there's lots of data, or is it the ones that have less data?
Yeah, I still think, trying to understand the roles of water deficits and open canopies. So a lot of the global models actually make shortcuts in how light's intercepted by forests, and they do it wrong, and they get photosynthesis wrong. And when you go to a savanna, you essentially have this three-dimensional situation of plants and open spots. And so to really capture the three-dimensionality of that light photosynthesis, you've got to go into that. And then the problem is these trees will have soil moisture deficits, and then their photosynthetic capacity decreases over the season. We measure it, but we don't model it in a systematic way yet. So yeah, I think these stress systems water deficit systems are some of the harder ones. Modeling methane fluxes is really tight too. I mean, I showed you my little equations, and we can model that with the given conditions pretty well, like R squared of 0.9 or so. We don't get the high fluxes with methane. The microbes are different. They're living in spots we don't measure well, and so that's a problem. So I guess I'm going long here. So.
Thank you so much, Dennis. Yeah, we unfortunately have to say goodbye to you now, but I want to highlight some comments in the chat that said, I want to be a biometeorologist when I grow up. Lots of love for you. So please head to the chat, continue.
I hope that's not my niece.
Okay, great. So for anyone who's just tuning in now, we are in prime time hours, and I'm your host, Lily Zhang. I'm a PhD student in atmospheric and climate science. And since we're about to kick off our keynote panels, I want to quickly remind you all why we're here for this 100-hour streamathon. We're here to save America's forecasts because we believe that all Americans deserve good weather and climate forecasts. Historically, US scientists have been at the forefront of this. Like, we made the first computerized weather forecasts. We had the first computer models of CO2 warming, and we have this awesome unparalleled network of observations that we heard a lot of our previous speakers talk about. And the important thing is that this progress wouldn't have been possible without all the investment by the public, so by all of you. And unfortunately, recent funding cuts are affecting all areas of weather and climate research, which is putting this great scientific miracle at risk. We just learned that the most recent budget cuts proposed by the administration sort of slash NSF and NASA's Earth Science budgets in half. They completely eliminate NOAA's research arm, which supports our forecasts and models. And it also ends these foundational programs for young scientists like the NSF Graduate Research Fellowship, which supports my PhD. So if you've been enjoying our stream and want to help save our forecasts, we ask that you share what you're learning with your friends, family, and representatives. And I know some of you, maybe this is your first time calling your representatives, so we've made it easy for you by putting together a call script and collecting their numbers at this link. So just visit wclivestream.com/act, and I'll show you what that looks like on my phone on the 5 Calls app. So I just put in my location, and then I scroll down to the fun weather and climate science issue, and it gives me a script, and it gives me the numbers for my senators and representatives. So thank you so much to everyone who's already called on our behalf. We're at, I think, almost 7,000 calls, which is super awesome. And now I'm excited to introduce our next speaker, Dr. Kim Cobb. So we're going to take a little bit of a trip to the past. I know a lot of you have been asking for paleo content, and Kim's going to be talking to us about ancient Pacific corals. Take it away, Kim.
Thanks so much. It's really an honor to be here today. I'm going to be talking about corals and climate extremes and what's happening then today, at least in a very remote part of the world that I've been studying for the last 20 or 30 years. Before I proceed, I want to thank some of my longtime collaborators and past and current students who will come up during this talk for all of the wealth of information and support and data that they have provided over the years. And before I go any further, I need to state that I am presenting here in my own auspices, not on behalf of any institution. And I want to say a big thank you, first of all. Thank you to all of these early career scholars and rock stars who are showing us the way. So they say that you guys are the trainees of old people like me, but today and over the last 78 hours, we have been the trainees of you, showing us how to get it done and the importance of communicating our science to the public through any means and all means possible. So thank you very much. So then the nut of what I'm going to discuss today is my work as a climate scientist. And as I'll discuss, I reconstruct past climate so that we might be able to better understand present and future climate change projections. And so I'm going to talk about what that means. But first, I wanted to bring you to the part of the world that I study and introduce you to the phenomenon that I've spent the better part of almost 3 decades reconstructing at this point. This is the tropical Pacific. This is a part of an ocean basin that covers over 50% of our planet's surface. And this is the largest climate cycle on our planet outside the seasonal cycle. A seasonal cycle is a lot more predictable, by the way. This is called the El Nino Southern Oscillation. And this is a NASA satellite image of the last, well, actually not the last, of course, one of the couple largest events of the last 100 years. And it's characterized by a broad scale warming from the central to the eastern tropical Pacific, which disrupts weather patterns all around the world. And in this case, you can see the tiny little dot in the middle there, almost in the geographic middle of the Pacific, is the research sites that I've been working on over this time to chase this phenomenon down in the paleoclimate record, which is the record of climate changes that we recover from lakes, ice cores, sediments, and in my case, corals. So this is also a reminder about, how important this cycle is for the rest of the planet because of the size and scale of the Pacific Ocean, because when you warm waters in this region, because of the atmospheric reorganization that occurs during these warm extremes and their sister La Nina events on the cool side, we actually see a perturbation of weather and climate patterns around the world, stretching from pole to pole, if you will. I've put some of the more notable impacts for the United States here, kind of depicted in pictures. These events have really strong impacts on Western United States precipitation patterns and drought patterns, and also they're linked to wildfires. By creating kind of a boom bust cycles for fuel, if you will, that you may have seen in some headlines of late. They have a strong statistical tie to North Atlantic hurricane cycles. We're entering into a relatively active season right now in the Northern Hemisphere, in part because we have relatively cool conditions in the tropical Pacific right now. And last but not least, if you're a skier like me, you care about their impacts on snowpack, and temperatures across the northern United States. And it's not just me who's saying that this is an important thing for the United States. Goldman Sachs tips their investment portfolio every single time the El Nino or La Nina rears its ugly head every few years. So this swings back every few years, kind of whipsawing the global climate system. And I'll discuss about what we know about it to date and why we're working to extend the record and what we found. The main question that we're driving at in my research, as in many other weather and climate researchers across the United States and across the world, is this central question. is this powerful natural climate cycle changing in response to greenhouse gases and continued global warming. And this is important because, again, it maps onto so many different classes of weather and climate extremes that if it is getting more erratic, if you will, it's really important to bake that into our risk assessments of what we can expect in the next decades. And that's really why this is a fundamental question in climate science and a very tricky one to answer, as I'll discuss. So first, I wanted to talk a little bit about me and why I find myself talking about corals in the middle of the Pacific Ocean and obsessed with El Nino. It all started very fortuitously with a high school summer camp on marine science that was based at Woods Hole, which is, of course, one of the premier oceanographic institutes in the entire world. I had no idea at the time, being a sophomore in high school. And this was my first brush with NSF funding. This was an NSF-funded program. As an undergraduate, several years later, I would attend an NSF-funded REU program, Research Experience for Undergraduates, at the other premier institution for oceanography in the world, the Scripps Institution of Oceanography in La Jolla, California, where I had my first taste of working on the El Nino Southern Oscillation, which is this powerful climate cycle I've been talking about, and working on it for my undergraduate thesis. As a graduate student, then again, back to Scripps Institution of Oceanography, where I was an NSF graduate research fellow. So you can see NSF funding featuring prominently in my trajectory. And then for many, many years, of course, now working as a principal investigator on NSF and NOAA-funded grants focused on this climate cycle, how it's changing, and everything about it, basically, as far as we can go back, pushing these records and working with the Coral Archive. So over this time period, I think it's important to note that I have funded many different kinds of students, postdocs, master's students, PhD students, and mentored over 50 undergraduates in my lab, all of whom have a piece of that federal funding that have supported their journey through science. The other thing that I am that's important to mention, I'm a mother to four, which really does shape much of my perspective about science and inclusion and what we're aiming for when we talk about access to science training. I'm also a transplanted Southerner. I spent 18 years at Georgia Tech before joining Brown 2 years ago. So I have that kind of purple state mentality focused into how I conduct myself as a scientist, the importance of communication and the importance of nonpartisan efforts, exactly like this. And last but not least, I'm a carbon obsessive. I'll come back to that a little bit later. So first, I want to ground us in what I think is the most important temperature record, of course, of all, which is the global temperature record. And this is one that stretches back about 150 years, and it shows you the reconstructions, because that's what they are, of temperatures back in time from different kinds of expert centers for climate, including ones in the United States from NASA and NOAA and Berkeley, ERA, as well as the Hadley Center in this case. And so what we're showing here is kind of this sawtooth pattern going up in time, punctuated by these sharp spikes. Each of those sharp spikes is a new record, warmest year ever on record, and those are all El Nino years. So that's how powerful this climate cycle is. And of course, last year we broke a new record. We breached 1.5 degrees Celsius above pre-industrial temperatures for the first time. And that's something that we know will continue going forward. But that's an important line in the sand from the policy perspective. Of course, that's the target that was laid out in the Paris framework for mitigating the continued rise of emissions and the minimizing the damages associated with those emissions. So we just had a World Meteorological Organization report come out in the last few days. I'm talking about the statistics of the next few years to come and just reminding people how quickly warming is happening right now. 80% chance that at least one of the next 5 years will exceed 2024 as the warmest on record. 86% chance that at least one of those 5 years will be more than 1.5 degrees above the late 19th century average. And of course, what I'm here to tell you is that that year will certainly be an El Nino year. It may not be a strong one, it may be a relatively weak one, but it will be an El Nino year. And as this cycle occurs every few years, that's one of the reasons why this projection can be so confident that we'll be breaching the 2024 El Nino event as we go forward in the next few years. So when we go back in time, we have to recognize that whereas this graph looks like it's showing us a very strong warming, and it has all these jagged peaks in it, which are El Nino events. Once we start to get prior to about 1950, the certainty of these reconstructions of global temperatures drop off significantly. We don't have as much data. And the data that we do have is somewhat biased in some cases and mostly just lacking. And so if we go back to even the large El Nino event in 1940 that you see there, it certainly looked like a big event. It's definitely a multi-year event. How big it is relative to other events is a little bit more fuzzy. We're already seeing some divergence in the different reconstructions. That's one measure of uncertainty that I wanted to highlight today. If we go back in time into the 1880s, 1860s, we're seeing significant divergence of those curves back through time. Certainly there's one of the largest events ever recorded in the instrumental record is the El Nino event of 1877, which called widespread drought and massive mortality across the Indian subcontinent, for example, in addition to many other global impacts that are well recorded. But prior to that, we're getting really fuzzy. We can barely see an El Nino event. We really can't understand what the relative size of these are. Of course, pre-1850, it's anybody's guess. And so that's where paleoclimate comes in, trying to recognize that we have archives that are sensitive to El Ninos and La Ninas that can help us reconstruct this climate cycle back in time and add a better statistical pool of that pre-industrial climate, which was, of course, the baseline for present day changes, and the baseline against which, if we wanted to detect changes in El Nino today, we would have to measure against. And that's where the corals come in. So this is a picture of me doing my best Indiana Jones impersonation. That will certainly date me among a good portion of the viewers, I recognize. And this is in the Central Pacific. And this is a large hydraulic drill that my trusty drilling assistant, Jordan Watson, is holding while I pull a coral core out of a living coral colony. So these are corals that are growing roughly 1 centimeter per year. So kind of stack your fingers up. That's about how fast they grow. And they grow radially. And so when we drill down, a core like that, which is roughly a foot long or so, is probably about 20 years, 25 years of information in that capsule. And then we're going to push that back in time, as I'm going to show you. We're going to get many decades off of the living reef systems and many centuries off of older corals that are scattered around beaches at these same exact sites. So this is some pictures just summarizing what the archive is that I'm going to use today in my talk. You can see the living corals there. We drill those via scuba. Those go back several decades to a kind of a century at maximum at these sites that I'm working at. And then we have the fossil corals, which are much older usually. They're range from about 50 years to 7,000 years old, and they are present on beaches across these islands. And so here's one that's roughly 500 years old, and you can see some drill holes in the middle of it. This is going back roughly 90 years or so from 500 years ago. So again, a time capsule of temperature information from that time period. How do we know it was that old? Because we use uranium to thorium radioactive dating decay series to find out exactly when this coral grew. And that's an extremely precise chronometer that we use. How are those corals deposited on the beach? Nobody knows. I wasn't there. I wouldn't want to be there when a 2-ton boulder rolled up on the beach. It's obviously from maybe a large storm event or tsunami, some kind of wave deposited on the beach. And so how do oxygen isotopes work for corals? You drill the coral down, you slab it into cross sections. I'm showing here an X-ray where we're looking at the growth morphology of those corals. You can see the kind of the annual accretion of that skeletal material through time. And the chemistry that we're using is actually based on the oxygen isotopic composition of the coral skeleton, which is, of course, calcium carbonate. And these oxygen isotopes are 2 flavors that we're looking at. One is oxygen 16, which is the one that is on the periodic table. It's the vast majority of oxygen on our planet. The other one is oxygen 18. It has 2 more neutrons than oxygen 16. And it is present in much rare abundance. But the ratio of these 2 oxygen isotopes in carbonate skeletons like corals is laid down as a function of temperature of the ambient seawater and the oxygen isotopic composition of the seawater that it's growing from. So that's why we're able to make a climate proxy out of these coral oxygen isotopes. And as I'll show you for El Nino at the sites that I work at, it's a great match. The coral powders are drilled 1 every millimeter to resolve monthly scale changes related to the El Nino oscillation, El Nino Southern Oscillation coming and going. So how does this work at our sites, and why is it so good? Because it's so good. I'll show you in a second. But this is a map of sea surface temperatures on the top. So again, we see that broad warming from the central to the eastern Pacific, and my sites are in that black circle in the middle. And during an El Nino, obviously it gets very warm, as we've seen before. What is new here is the bottom plot, which is reminding us that it gets also very wet at these places in the tropic where it gets warm during El Ninos. It gets very wet. So it gets warm and wet at the site. Now, corals respond to temperature and they go in one direction when it gets warmer. And when it gets fresher like that, they also have a compound signal that helps bring out the El Nino relative to non-El Nino conditions in the coral skeleton. So, we might conclude from this last little bit that coral oxygen isotopes are an ideal proxy right at the right place, and they afford the right kind of time resolution to resolve the coming and going of El Nino events at our sites. So now we get to the hard part, because that all sounds really good and like the perfect story. And, you know, nothing's first of all perfect, but this is particularly difficult to chase down these records. And I figured this incredible lyric from, of course, the song called The Scientist by Coldplay. Nobody said it was easy. No one ever said it would be this hard. So what do I mean by that? Why is this hard? This is hard because we are really needing to look at a large number of corals. We're needing to resolve many different cycles of El Ninos and La Nina events across these different islands. They're very remote. They're very hard to work in, hard to get permitting, hard to not die, hard to ship things back and forth, the whole 9 yards, hard to take a warm shower. So over 3 islands, 13 expeditions, 20 tons of coral shipped back and stored on site, many dates, both radiocarbon and uranium thorium dating. And this is where it gets really hard, which is we have generated about 100,000 different oxygen isotopic measurements of coral skeleton material. And that at 30 samples a day takes a really long time if you do that math, okay? So that's why it has taken me the better part of 3 decades to amass the data that I'm gonna show you today. So we have a total of over 2,000 individual years of El Nino and La Nina activity at these very sensitive sites in the Central Pacific. And all of that data is generated at monthly resolution. So that's where it gets hard. That's why it takes kind of some terrible stubbornness, I would say, tenacity, when I would also say, I suppose, to show you a plot like this, which took about 10 years to generate in my lab over successive students working over entire dissertations. And this is a record of coral oxygen isotopes in the colors, and then sea surface temperature is in the gray. You can hardly see it because it is actually overlain by the colors so clearly. And you can see that the corals are tracking the up and down of the El Nino events in the warm phase and La Nina events in the cold phase quite nicely. And we can play this game back in time. This is from the 12th century to the 15th century. We're talking the Magna Carta, the Mongol invasions. We're talking about the Black Death. And these are 300 years of monthly resolved coral information. Each color is a different coral that we picked up off the beach and dated it. This was published by Sylvia D a couple of years ago. So this is the kind of rich archive that we can use as a baseline to compare modern day El Ninos and La Ninas to in terms of their frequency and severity. So this is what we're doing right now. We are taking all of the corals that I've ever generated in my lab, and this is published by my former student, Pam Groth, several years ago. And this plot takes a little bit to get used to. So just remember that we are inverting the time axis so that it goes from present day at the 0 mark on the right, all the way back to 7,000 years ago on the left. On the vertical is the measure of El Nino Southern Oscillation strength. So when you go above 0, it's stronger. And when you go below 0, it's weaker. And that 0 line is kind of pegged to the last 50 years of the instrumental record of El Nino Southern Oscillation strength. So that's really the work of many decades. All of these records are multiple decades. All of them are present in monthly resolution. I've kind of collapsed them on this plot so we could just pick out that metric of interest, which is El Nino Southern Oscillation strength. So again, I refer you to the paper if you're interested, but we're going to push forward here and make the keen observation, which is pretty simple to make on this plot, which is most of the fossil corals on this plot are falling below that late 20th century baseline, right? So almost every single one of them, including many records that are almost a century long or more, are falling below that level, okay? So if that's the observation, then how significant is that? What does that mean for our present day El Nino Southern Oscillation strength? And of course, our future with climate extremes. So again, this is the core observation. There is a 30% difference between all of the pre-industrial baseline of El Nino activity implied by all of those coral records versus the late 20th century, okay? Now, the question is, what are the odds that this kind of shift could have occurred with only natural climate forcings in play? Right? So, because this just happened naturally, because this is a highly variable system and we have a very short record of it. So maybe this is consistent with natural variability, the shift that we're seeing into the 20th century. So the approach that we took here, and I'm not going to get into this, but I just point it out here to illustrate the deep ties that exist between the paleoclimate community, somebody like me working almost exclusively in coral reconstructions, and the modern day climate dynamics community that is trying to push the envelope with respect to their simulations of El Nino Southern Oscillation events. They're pushing these models because they want to provide better projections of the next 6 to 9 to 12 months of global climate variability. And they're pushing these projections because they want to know what's going to happen, not just this decade, but next decade with this system. So I'm using 2 different numerical climate models that are some of the world's best at the time for simulating this phenomenon in a numerical system. One is coming out of the GFDL, the Geophysical Fluid Dynamics Laboratory. And I have to say that this entire laboratory is funded by the research arm of NOAA that is under threat with the current administration's proposed budget. It would be zeroed out completely in that budget. The National Center for Atmospheric Research is also entirely funded by the National Science Foundation, also one of the premier modeling centers in the country. I've used their products and services repeatedly throughout my entire career, and this is one example of how they were utilized here that you might be able to tie into the story today. So the result of this comparison is that the observed intensification of late 20th century El Nino Southern Oscillation is not consistent with our best estimates of natural variability. Okay, so if you believe these corals are correct, and there are many different sites that this kind of study has been reproduced at with different kinds of archives like tree rings or other coral reconstructions, but the jury's still out. This is remains a somewhat controversial result because there are just no other record quite like it on the planet. So we'll really need to get a lot more records to be able to robustly test this. But this does stand, this result, and it's something that helps us see that if natural variability may not have caused this recent shift, then maybe anthropogenic greenhouse forcing related to global warming was something that is already having an impact on the characteristics of recent El Nino events, in our case, leading to this 30% intensification over the recent decades. Okay, so I want to come back to something that I think has a bit of nuance here, because I want to bring you to the fuzzy front lines of where we are working right now to try to dig into this question more, which is to remember that the corals are sensitive to both temperature and this seawater oxygen isotopic variability. And the seawater oxygen isotope varies in lockstep with salinity in the ocean. That's the best way to think about it. And that's actually what we see in the real world. So precipitation affects it, evaporation affects it, almost the same way as you would think about salinity. So if the corals are very sensitive to the salinity variable, well, we may need to understand a lot more about that variable as we think about what's driving this intensification in the coral signature of El Nino Southern Oscillation at these sites, right? Now, we might ask ourselves, it could be important to understand how this variable changes across El Nino and La Nina scales today. We definitely like to understand how it changed in the pre-industrial, and we definitely probably like to understand how it might change in the future as a powerful tracer of water processes on the planet. Unfortunately, nobody knows this question right now. So that's where science comes in. That's where my curiosity kicks in with applications to the research that I'm working on, as well as hundreds, if not thousands of other climate scientists around the world. And our approach is to look at this variable, this exact variable, seawater oxygen isotopes, across the modern day in a whole handful of sites across the tropical Pacific. And I have an amazing undergrad working on that right now, where anybody's looking for a graduate student in the near term. We are a proposal funded, pending actually, to try to get this work supported. And we're also looking at this in numerical climate models that track oxygen isotopes through the climate system. And this is work that my graduate student Chandler Morris is going to be traveling to NCAR, the National Center for Atmospheric Research, this summer to collaborate with people there to see how she can advance this question. And this work is already NSF funded with a grant. And so where are these sites that we're collecting seawaters from? These are in the red circles here from across the entire Pacific. Many of these sites go back to 2006. Some of them just go back to 2 or 3 years ago. So this is something that we are committed to maintaining even without funding. And we hope that it might be valuable, not just for our research, but as an observational data set for models to compare to as they try to incorporate this tracer into their water cycle. And they'll need this kind of data to ground truth, things like mixing, things like fluxes out of the ocean to the atmosphere, atmospheric mixing, cloud processes that lead to rainfall. All of those things are things that are imprinted upon with water isotopes. And this is why I keep doing this, even if it's not funded. The other reason why I'm really excited about this work is that if we are able to answer these questions about seawater oxygen isotopes and how they vary with climate extremes today and droughts and extreme precipitation today, then we will actually be able to unlock the full potential of the 120 existing coral reconstruction sites across the entire tropics that I'm plotting here. All of this is there's a database that was gathered painstakingly dating back to the 1960s in many cases. And all of these records are archived. They've been funded by multinational, including the United States, but many records coming out of many other countries' science foundations that have been archived. And our ability to stitch them together and use them to answer some of these pressing questions in climate science is in part hampered by our lack of understanding about seawater oxygen isotopes. So I'm going to think that that's the linchpin. I'm going to keep poking at that as long as my graduate students and former postdocs are as well. So this is an enterprise I'm really excited about. This brings me towards the end of my talk, and I just wanted to kind of drop in another aspect of corals and climate that cannot go unmentioned right now, which is the impact that ocean warming is having on coral ecosystems across the entire tropics. And this is a picture close to home. This is from Christmas Island, where I've been working since 1997. And you can see on the right, a very beautiful, full color, full cover reef. And then after 10 long months of bleaching and mortality level temperatures during the last major El Nino event at this site, over 90% of those corals succumbed to heat-related stress and they died during this event. A very small number, about 5% or so, were able to limp through, and maybe they hold some keys to coral reef resilience in a warming world. But for me personally, this was a big wake-up call. This was an impact that I personally had thought was many decades, several decades in the future. And here it was, something that I had the fortune and misfortune of witnessing in living color as an eyewitness on repeated expeditions to these sites during these years. So that stuck with me, and it's something that has shaped and changed the way that I approach my science, and this sense of urgency that I have about how fast the clock is ticking and what we need to do to work together to not just try to protect ecosystems like this, and this one obviously coming too late for this particular ecosystem, but many different communities all around the world that are going to reach their respective tipping points. When that occurs, I don't know. For some, it has already occurred, and we can only hope that by leaning into science, we might be able to harness extra levels of resilience and try to make sure that we protect as many lives, as many livelihoods, our economy, our national security, and as many ecosystems as possible, many of which we depend on critically, of course. So after 2016, I started instituting a wholesale pivot. It's not quite over yet. I'm still really passionate about the climate science work that my lab is doing with the current NSF funding. But I've been exploring newer projects related to coastal flooding, urban heat islands, local hydrology efforts. I'm trying to apply my skills and training as a climate scientist to these very real world backyard problems, trying to support risk and resilience science and bringing the next generation along with me. So this is about thinking about how we're partnering with policymakers, how we're partnering with emergency planners, and other kinds of partners all around the space who are keen on protecting our economy, protecting our health, and protecting our national security. Those are the things we all care about. And those are the things that I'm very keen to advance in partnership with whoever will work with me and whoever could use my specific skills. And I'm, of course, retraining on the fly as well. It's like being a graduate student all over again. And the last thing I would say is that since 2016, I've been kind of marching on a path towards lower carbon living for myself and my family, but also thinking about the ways in which I could reach for other scales of action with that work at the local scale, at the state scale, and wherever I can at the national, international scale. So those have been some passion projects, and many of them have translated into what I consider to be extremely exciting, cutting edge work, never alone, always in large teams, advancing the work. So to end on a really critical note about the pending cuts, these are some of the many people who are part of my lab currently, and these are incredible early career scientists and people who have all of them had some access to NSF and federal sponsored research over their time in my lab. And on the bottom, you'll see some high schoolers at the K through 12 level that I am extremely excited to be engaging in my work in Providence, where we are working on urban flooding and risk resilience for these local communities that are very flood prone in Rhode Island. And so to end on a very hopeful note, I'm confident that this generation is going to continue to want to be working in these spaces because this is what they want to be doing. This is where they see their impact and the meaning for their work professionally. And so I will be right there with them. I hope that our federal government continues to invest in their futures. And I also recognize that, as I just said in my last slide, so many climate scientists are retooling and redeploying and bringing these students along with them to connect the dots between their training and expertise into resilience today, right now, which is what we so desperately need. So we need to be building out this science infrastructure. I'm happy to be a part of it. We're going to need support from the federal government to make it happen. But this is a train that will not stop because the opportunities and the opportunities to make a real difference are so tangible and they're so close. I can taste them. In fact, I've already seen many of them occurring. So I'm just very excited about the work that we're doing and motivated and inspired by the early career scientists that I have in my lab and the ones who are hosting this amazing event today. So I'll leave it there and hope that we have a lot of time for questions.
Yes, we have lots of time for questions. Thank you so much, Kim. So interesting to hear about how you're using these past changes to like study the future. And I think it's neat that that sort of theme is like paralleled in your career trajectory as well. Like you started off with these paleoclimate science records and now you've pivoted to climate solutions. So speaking of using the past to study the future, we have this question from Nevitz, which is, are there records of coral bleaching in the past that show some form of restoration can help us understand what's happening now?
Yeah, that's a really good question. So there actually are quite a few scientists who are trying to pursue basically, kind of like biomarkers of past bleaching events in coral skeletons. Now, remember, the coral skeleton is kind of devoid of tissue. The tissue stays on the top layer, but the premise is that they leave behind these telltale signs that are remnant tissue, pretty much. And in some cases, people looking at the skeletal archive as well and wondering if the chemistry of the skeletal archive itself has changed in terms of the lattice chemistry. So that's something that, for example, my former postdoc, Alyssa Atwood, is investigating with some work that I know she's either gotten NSF funding or is applying for that kind of funding. So that's going on. I think it's a very promising area. It's not one that I've seen extremely robustly applied across multiple records at this point.
Great. We also have a few questions about modeling and predicting ENSOs of the El Nino Southern Oscillation. And some people were asking, if ENSO is semi-periodic, how do we model it and predict it with any sort of accuracy? And then someone else asked, does the relationship between our coral proxies and ENSO change with time?
Yeah. So, to the second question first, we assume it's definitely an assumption of kind of linearity as we go back in time. So we're assuming that whatever has occurred today in terms of the many different flavors of this phenomenon and how it's laid down in the coral, that we're able to capture those in the present day archive. It's one site. So if the spatial footprint changes of El Nino, we may get a stronger signal or a weaker signal depending on where that maximum has landed, right? So that's always a caveat with working with one site. But if we assume some kind of linearity, then we can take the calibration interval of the modern day with a SST, a sea surface temperature index that is very broadly applied to track the severity of El Nino Southern Oscillations. It's a large box across the equator, and we calibrate to that because if we can, that's the most important target in terms of global climate teleconnections. That's where when you put heat there, really kicks up the atmosphere. So when we calibrate to that, we have a relationship as a very high correlation coefficient. We apply that back in time, and we're basically doing the inverse of that, right? We're trying to extract this broad scale temperature information from the single site with a very old coral, which is basically our only evidence of El Ninos at that particular time, right? It's otherwise unseen. And so that is an assumption that we make going back through time. And that's why it's so important to try to work with multiple sites across the Pacific as best we can, from tree rings. There are people working in Peru with mollusk data and there's tiny shells that grow in the surface ocean that record these things. So with this whole basket, I believe there is some emerging evidence that our intensification that we find in the coral records is supported by these other archives. But again, this is not something you're going to read in the Intergovernmental Panel on Climate Change Assessment Report just yet. So we'll see where the next one lands, but it certainly wasn't ready for a robust multiple lines of evidence threshold for the 6th assessment report published in 2021. So stay tuned. And what was the first question? I forgot.
The first question was, no worries. It was about how we can answer some of those questions you're asking about predicting ENSO if it's semi-periodic.
Yes. So there are a couple of things to keep in mind here. One is the difference between an actual forecast and a projection. So when we talk about an ENSO forecast, you can go look at the we have many different centers that are forecasting El Nino all the time. I personally like the IRI, was it Interdisciplinary Research Institute at Columbia, at Lamont. I love their homepage. But at any rate, they give a forecast that's actually looking to document where surface temperatures are going to be in the tropical Pacific in the next 1 month, 2 months, 3 months. They go out a year, generally speaking. And they are trying to incorporate as much as they can the statistical character of the phenomenon, including all its irregularities through history. And many times they're relying on numerical models of full physics to try to take the moment that we are in right now and spin it forward in time. And then that's a dynamical forecast. And you can see them use statistical and dynamical forecasting, and sometimes they agree and sometimes they don't. There's generally a large spread when you get out to about 6 months. That's kind of the fuzzy edge of where we can forecast El Nino, okay? So then we get to projections. That's another matter. So the projections are really about what is the overall character of this phenomenon going to look like in a decade. We don't really want to know whether it's going to occur in 2035 or 2036 or 2037, but we want to know what it's going to look like between 2035 and 2045, for example. And that's where my work comes in, where we're trying to push go on our best available full physics models, the ones that do El Nino the best. How do we know they're the best? In part because they look like the coral data that I just showed you, in fact. So that's a key part of benchmarking and testing that the community is always doing with each other and with the best available models and the best available data, and on it goes, trying to get a better representation of the irregularity of the system, the different spatial footprints, the different severities, the different impacts globally, which also change event to event. So it's complex, but the models that we have right now are doing so much, incredibly much better than they were 10 years ago. And so we really are getting to the point that we can look ahead and see some robust signals emerging from these models, in particular, looking at the fact that the atmospheric response to these events on the surface seems to be getting larger. So that's something that has global implications in terms of rainfall extremes, floods and droughts, for example, that's worth keeping an eye on. But that's coming out of our best available models with a pretty strong signal right now, something that may be borne out by the data that I showed you today, which is also consistent with an intensification of the hydrological cycle related to the El Niños and La Niñas.
Yeah, great explanation of distinguishing between climate projections and weather predictions. So I'm going to try to squeeze in 2 more questions. There's so many great ones. So we have someone in chat who seems to be familiar with paleoclimate data, and they ask, how does the coral record compare to the ice core data? They also have isotopes from ice cores.
Yes. So ice cores are great archives of climate. When you're looking at El Nino Southern Oscillation, the polar ones are only going to get you so far. Those are maybe really good for looking at how El Nino events impact polar climate, which is a kind of a separate question. But it's going to be hard to get back to a robust estimate of tropical temperatures from the poles because of that translation factor, right? So what we can do is look at tropical glaciers. And I want to bring in the work of Lonnie Thompson, one of my heroes and long-term collaborators at Ohio State. And he's been working on tropical glaciers, and he does use oxygen isotopes across these tropical glaciers to reconstruct the El Nino Southern Oscillation. And so when we put all that together, we can get a more comprehensive picture of how this phenomenon has evolved through time. When you compare it with my coral data, there are some similarities, there are some differences. Again, I'm sitting in the water. He's up on a glacier mountain and in the Andes. So some of that is related to how these signals are transmitted through the atmosphere. Great question.
Okay. And finally, there are a few early career scientists in chat asking if you have any words of advice for what young scientists should be doing for their careers with the challenges of the funding situation, and should they be considering going to foreign universities, going to different countries? If you could just end with some advice for all of us.
Yeah, I mean, the pending funding crisis is very, very severe, and I don't want to whitewash that, and it would not be responsible to do so. I tried to tell the people who count me as a mentor that I really hope that institutions find a way to continue to support graduate students as a primary stakeholder here. And some of the most vulnerable stakeholders here as the science infrastructure comes under attack and funding is lost. So that's my hope. That's certainly how I tend to approach this as a PI myself. And I think there are alternative ways to fund some of this work, not at the scope and scale that we might have liked, but with a kind of a people first strategy where we try to recognize that, helping people through this next critical phase must be a community-wide priority. And that's my sense from so many folks. That said, I have to say that there are a lot of opportunities to get training on the job right now in climate spaces. So there are opportunities out there in the private sector. There are still many opportunities at the local and state levels to engage in climate science training that can be quite applied, right? There are data science openings and physical climate, science type openings and everything in between. A lot of it is like gearing towards this resilience work that I talked about already. There's a lot of appetite there. There's funding there. Not all of it comes from federal sources. We wish that more of it would, but keep in mind those opportunities because year by year, that landscape is really changing. And then I also have to say, please don't sleep on climate communication and science communication. This is a great way to hone incredible skill sets in our moment. We just see how impactful it is right now. And this will continue to be, I think, a drumbeat for your entire rest of your careers. So lean into that opportunity right now as you can to try to lift up the core messages from our community and make sure that people are understanding the value that we're delivering. And thanks for that great yet very difficult question.
Thank you, Kim, so much. That was such a great note to end on. Thank you for your amazing presentation as well and for answering my question.
I hope I did a good job.
A great job.
Thanks for the opportunity, y'all.
Take care. And thank you also to Lily, who did an amazing job hosting for those hours. Some love for Lily in the chat, please. My name is Andrew. I'm a postdoctoral researcher at a NOAA lab in Princeton, where I study climate science. And I'm going to be your host for the next couple of hours. I'm super excited because the lineup of speakers we have is pretty amazing. But before we get there, I just want to remind people why we're here, why we're doing this live stream, and why we are 79 hours into this live stream, which is incredible. And it's incredible to still see almost 800 people on the call with us right now. But I think it's important to just remember exactly why we're here. And if you've been here for 79 hours, which I know some of you Tumblr gang have been, we know how important weather and climate forecasts are to every American and everyone in the country. Luckily, the United States has been a world leader in weather and climate prediction for decades now. We developed the first computerized weather forecasts to help know what to expect, whether it's going to rain tomorrow or rain next week. We also made the first computer models of the climate in order to understand how CO2 and other ways we're polluting the planet will impact Earth for decades to come. And to make these forecasts work and to ground our models in reality, we have created an unparalleled network of observations. Everything from weather stations and satellites. We've got planes flying through hurricanes. If you remember Jeff Masters yesterday, that story had me on the edge of my seat. We've got places launching weather balloons. We've got boats. We've got floats like the Argo array or robots, which I think Britney will talk about. And this mesh of models and weather forecasts and observations is a true scientific miracle. And I think it's pushed the boundaries of what humanity even thought possible. And that's really why we're here today, is we're here to share with you some of that miracle, some of the science that we've been able to do, and explain to you how we've been able to get that funded. And this miracle has been funded by decades of investment by the federal government, and that's paid for by the American taxpayer, by the American public. But sadly, in recent weeks, these funding cuts have put this miracle at risk. Already, we have weather stations that are so short-staffed that we're losing observational coverage. We heard earlier that places in Omaha, Nebraska are not able to launch weather balloons anymore, which severely hurts the forecasts. We also started off this live stream in NASA GISS, which is a laboratory dedicated to understanding our climate's future, and they're being kicked out of their building. And funding more broadly for our basic understanding of weather and climate is already disappearing. This has already happened, But what's coming up potentially soon is way, way worse. What you see on the screen now are QR codes to the proposed budgets for NOAA, NSF, and NASA, which are way worse than any of the cuts we've seen so far. For example, the proposed cuts would cut NSF and NASA's Earth science budgets in half and completely eliminate the research arm of NOAA, which funds the lab, for example, that I'm at. And this would also end foundational programs for young scientists like the NSF Research Experience for undergrads and graduate research fellowships, which funded our last speaker, Cobb, as she made her way into our field. But it doesn't have to be this way. If you like what you see here, if you think that it's worth funding, which we hope that you do, we ask you to please use the link on your screen right now, which will come up around the bottom of the screen, wclivestream.com/act, to contact your representatives and tell them to save our forecasts, to vote no on the proposed cuts that you see within these QR codes, and to tell them to spread the word, to join this live stream, to promote it to their friends and family. And we hope that you learn something about weather and climate along the way. Just a little anecdote for me. I had never contacted my representatives in this way by actually calling them up on the phone. And this link on the bottom made that super easy. I was a bit nervous about it, but you go to the link, it tells you exactly what to do, what to say. And I was amazed at how excited that staffing office was when they had someone passionate come on the phone and talk about these issues. So yeah, do it. I believe in you. We can all do this. And yeah, just great to remind people why we're here. So our first speaker, which I'm super excited about, is Professor Britney Schmidt, who is an associate professor of astronomy and earth sciences at Cornell University. Britney specializes in planetary science and astrobiology with a focus on studying Earth's ice shelves and Jupiter's moon Europa. She develops robotic tools to explore these ice shelves and glaciers and the oceans beneath them, while also researching potential life on other icy worlds. And excitingly, Professor Schmidt was also named the Times, in 2023, Time Magazine's one of their list of the 100 most influential people for her work on the Thwaites Glacier. So I hope I've embarrassed you with all that list of glorious things. We're super excited to have you here. So take it away, Britney.
Thanks so much. Really appreciate the introduction, Andrew. It's lovely to be here. I wish we were all here under so much better circumstances, but hopefully you've gotten a sense from the amazing speakers and panelists so far about how important climate work is to the country and how foundational actually the work here in the United States has been to the entire globe. And so that's kind of the perspective I'm going to bring it into, is kind of looking at the entire globe and looking at the kind of the most remote regions of it with these new perspectives and how that's helping predict what's going to happen in the future and perhaps help humanity kind of save itself in some ways. So this is the work shown here, which is our underwater vehicle ice fin, which we use in the Antarctic and in the Arctic to understand what's happening under the ice. It's one of the hardest places to measure what's going on in our climate system. And it's also one of these places that we want to be able to explore in other places. So this whole idea about seeing ice with the new eyes is a little bit inspired by Proust's words here, right? That the real voyage of discovery consists not in seeking new landscapes, but in having new eyes. And I'm going to talk to you about the new eyes that we've been able to bring to this perspective and to these places, and that's these robotic eyes. So my work actually in the climate side was originally inspired by trying to understand this world that I would argue isn't so different from ours. This is Jupiter's moon Europa. In fact, we've got a mission heading out there with NASA using ice penetrating radars to study this ice shell that you can see in the background. As you look at this, that's an icy moon. It's about the size of our Earth's moon, but has about a 30-kilometer, maybe 50-kilometer ice shell on the outside with a huge ocean, about 3 times as much water as on the Earth, in fact. And so I kind of came to this from outer space, if you will, trying to understand what's going on in the interactions between ices and oceans. And that inspired me to get involved. And then my first trips to Antarctica to try to support this work became why I got involved in climate science more directly. So I'm going to talk to you about Antarctica as well as Greenland. And this is work that has been funded by the National Science Foundation, the United States Antarctic Program, and NASA in Antarctica. Those are the U.S. agencies, but we've also worked with the Norwegians, the New Zealand community, as well as a lot with the British Antarctic Survey to make this work happen. So we're going to talk mostly about ice shelves, which are these large floating pieces of the continent. In fact, the Ross Ice Shelf that I'm showing here, which is just outside the kind of home of the United States Antarctic Program, McMurdo, that is about the size of France. So it's a giant floating piece of ice made from glaciers stitching themselves together and floating out over the ocean. So kind of this huge shelf of ice that's about the size of France. I'm going to focus today on the Thwaites Glacier as part of the Antarctic story, which is the fastest changing part of West Antarctica, highly dynamic place. And I mentioned we've worked with other countries as well. We've also been to the other side of the continent, looking at ice shelf called Fimboleisen with our Norwegian colleagues. We also get to do some of this work in Greenland, and this work in Greenland is also kind of funded by National Science Foundation, by NASA, I'll show in a minute, also by private industries. But this is a place where we're also doing science, all kinds of scientists working in this environment and getting the opportunity to work in Greenlandic lands as well. So back to these new eyes. So IceFin is the robot that we've built to address this. And so IceFin is an ROV. It was funded originally. I started as a faculty member at Georgia Tech. So we kind of came up with the idea for that before I became a professor there, then started building it there. And now we've moved it to Cornell University. But the hugest part of the funding and the development of this vehicle, which has turned out to be a great climate robot, was actually inspired by getting to Europa one day and funded through NASA through the astrobiology program. So IceFin is an underwater robotic oceanographer, and it's similar to if you've seen some of the larger autonomous underwater vehicles or ROVs, that's a remotely operated vehicle that are used in the open ocean. So IceFin is kind of this weird shape and size so that we can take it to Antarctica and to Greenland and take less fuel to do so. So it's kind of long and thin. So in this picture, you're seeing IceFin, which is about 23 centimeters or a little bit more than 9 inches wide. But it's almost, it's over 12 feet long. It's 3.9 meters long. So it's incredibly long because we're going to drill narrow holes through the ice and put the robot down underneath. So we built IceFin to be able to take the same kinds of measurements that we would take on these big vehicles, but do so in a vehicle that only weighs about 250 pounds. So up front, what we have are the science sensors that interact directly with the ocean. So we have that red sensor at the front is called a CTD, a conductivity, temperature, and depth instrument, and it's giving us the salinity of the water column and its temperature. On the other side, right beside it, is a sensor that measures how much oxygen is in the water. And what that does for us is it's basically like a fingerprint of the water column. It tells us where it's been, what it's doing, and what it's interacted with. We also have cameras and a forward-looking sonar up front. Then in the modules behind that, we have thrusters. We have a flexible science package that we can point towards the seafloor or up against the ice, followed by our custom electronics. And then in the back, more science and navigation centers. And of course, like every vehicle needs, we've got a backup cam. And so at the back of this vehicle, we would then connect to it through a data tether that also allows us to kind of drop the vehicle through the ice. So this is a video of our team working in Antarctica, and this is a kind of a typical day. We drive up to the environment, we drill a hole in the ice, we build up the robot, we lift it, and we put it down through the ice. And so we're doing this to be able to get the robot and get data in places we've never been able to measure ocean temperatures, ocean salinity, and the ice conditions deep underneath the ice in Antarctica and in Greenland. So this is what that deployment looks like in kind of a slower motion. So we build the vehicle up on what we call the strong back here. So this is actually from our recent work just this season in Greenland. Get the robot, we lift it into the air, kind of get it vertical, and then we drop it down through a hole that we bore into in this case, in the sea ice. What we're showing here is sea ice. So sea ice on the Earth can be anywhere from tens of centimeters to several meters thick. And it's the kind of ice that forms each year from freezing of the top of the ocean. So it's a little bit salty and it's pretty dynamic. We've also taken ice fin and put it through up to 750 meters of ice. And in those conditions, we would use what's called a hot water drill, which is kind of like a high pressure hot water hose that we use to then bore through the ice and put the hole through there, put science instruments down so that we can then go out and swim around underneath and see what's going on. So during a typical mission, this might be what it looks like. So I'm usually driving the vehicle. We actually even use a PlayStation controller. So it's very much like playing a video game. This is a picture also from Greenland. So I'm on the right here. Frances Bryson, who is a robotics engineer, is on the left. So Frances is co-piloting, and you can see in front of her the screen that's kind of showing us all of the sensor data coming back from the vehicle and the live path of the vehicle as it's traversing underneath the ice. On the right-hand side, the stuff that's right in front of me is the forward-looking sonar is kind of that blue sensor on the right-hand side, and then 2 camera feeds that allow us to kind of see the ice when we get up close to it. So together, we're kind of figuring out where the vehicle is, how to get it in and out of the environments we want to measure, and we can do this for 4 to 6 hours and traverse distances now over 5 kilometers of total track length. And so on the left-hand side, you can actually kind of see the bathymetric sonar and another science computer that our kind of science officers using also inside the tent. And all of this is inside a tent with a blackout curtain that my mom and I sewed for the inside of the tent so that we can keep as much light out of the tent, let us see the sensors and drive the vehicle. And then part of the team is actually outside live managing the tether, letting us know, communicating with the folks in the tent, telling us how the vehicle seems to be going from their perspective. So it's this really dynamic thing that involves anywhere between 4 and 6 people, even more sometimes, to do such missions. So this is what a typical driving might look like. So on the left-hand side are those screens that I talked about. And so in this case, what you're seeing is actual video footage from our recent mission. This is an iceberg survey that we were doing in Moltke Glacier, just outside of the US Pituffik base. It's a Space Force base in Northwest Greenland. And on the right-hand side is the forward-looking sonar. That's that kind of wedge-shaped image there. And on the bottom is our bathymetric sonar, which is actually, in this case, pointed up, so it's mapping the ice surface. In the forward-looking sonar, anything that's bright is reflecting sonar waves back towards you, and anything that's dark is kind of off in the background, or is there's nothing there. But in this case, it's actually just things that have been blocked by that forward scattering sonar. So I'm going to go ahead and play that so you can kind of get a sense of what it's like to drive a vehicle under the ice. It's really interesting. It's you learn how to think with these multiple sensors to give you information. So we're processing visually what's going on with the camera data on the left-hand side, and then that forward-looking sonar. What it allows us to do is basically see up to 100 meters in front of the vehicle, which in this environment there's almost no light in most of the places that we work, or perhaps no light. When you're underneath an ice shelf, there's absolutely no light at all except the light that we bring with us on the front of the vehicle. And so we use the combination of these sensors both to take science data, but also to get ourselves into the environment and be able to do the science that we do with IceFin. So then I mean those new eyes is just kind of new ways of seeing these environments. This is what IceFin looks like on a typical day. So this is a video of her underneath the ice in McMurdo Sound. So you can actually see some of the processes happening in the background. We've got barnacles draining. We've got algae living up inside the bottom of the ice. It's this really dynamic environment. So now I'm going to show you kind of 2 vignettes, 2 stories of the work that we've been doing with IceFin and how it influences what we understand about climate projections and what we expect to be happening with Antarctica and Greenland moving forward. So this is the work done by this program called MELT, which is part of the International Thwaites Glacier Program. It was a really amazing collaboration between the British Antarctic Survey and through the National Environmental Research Council in the UK and the United States through the National Science Foundation. It is the largest campaign ever attempted. In fact, just last year was when the last of the ITGC field work completed. And so there were 9 teams, 5 different field-going teams going all over the glacier to understand it and use every technique that we know how to use to understand one system altogether, the one that's changing the fastest in this part of West Antarctica. And so the left-hand side is showing the colleagues, so the robotics engineers, the students, the scientists, our British colleagues, our colleagues from NYU, colleagues from Penn State. So just all across the United States, all across the world that got involved in this project. So why are we worried about Thwaites Glacier? Well, this video should show you, right? So one of the amazing things that we've been able to see is using remote sensing, so using satellite data, is how fast ice in Antarctica has changed. So this is data from 2014 all the way up until last year, showing the collapse of the ice shelf of Thwaites Glacier. What I like to refer to as a currently connected system of icebergs. So you can see as it's flowing off here that it starts to break up, and the grounding line, the place where the ice goes afloat into the ocean, is actually moving back incredibly, incredibly fast. And so the whole ice shelf is collapsing. And that's important because it affects how fast sea level rises. As you push this grounding line backwards by melting, you actually thin the glacier, but you allow it to move faster towards the ocean. And so as that happens, it changes the stresses, it changes how the glacier behaves. And so you get this warm ocean water eroding back underneath the ice that's then causing it to move faster. So you get these multiplied effects of how fast the glacier is moving and how fast it's melting. And that gives us sea level rise. Why does that affect us? This is an image from NOAA, by the way, a data set that probably won't exist if these cuts go forward, showing what a little over a meter of sea level rise, which is what we think might happen in the next 100 years from this particular system. That's the maximum, but what it would do just to San Francisco. So this is Antarctica, this one system contributing to the disruption of San Francisco. So all that light blue area is coastal land that's now been flooded by the ocean. And if it goes up to 3 meters, which we think is what the entire catchment of Thwaites Glacier might reflect, we get a significantly more loss of coastline. So this is rather extreme. It's not what we expect to happen tomorrow, but we're already seeing this slowly starting to happen. And so when we think about these places that are so far away, they can still have this very realistic impact on our daily life. So what is it like to work in Antarctica, this really distant place? This is a picture showing me and Andy doing a test deployment of IceFin. That hole that IceFin is through, it's about this wide, and it's going down through 600 meters of ice. So the Thwaites Glacier in this place is 600 meters. We're about 2 kilometers from that grounding line from the place that it starts floating on the ocean. So what we do then is we go out to this place. We flew first to the US station, then by several planes got out to the site, bored the hole through. We drop IceFin through the hole that's been bored for lots of instruments, but we're one of the packages, go down into the ice cavity, turn on all of these sensors, and take it on a journey, a 3-dimensional journey underneath the glacier. And that produces the data that I'm going to show you here in a moment. So what we can do is we go to this place, and then we make these kinds of data happen. So that colorized part of the graph here is the ocean temperature. And what you'll notice is that those dark colors are actually incredibly warm. So this temperature is called potential temperature, but basically it is the amount of temperature above the freezing point. So what this is showing is that the ocean water in this area is over 2 degrees warmer than it really should be. So it's over 2 degrees warmer than what it would take to melt ice in the first place. And so that's what's really scary about this environment. So this warm water is making it all the way back to the bottom of the glacier, and it's eroding it. You can also see that it's getting a little colder and a little fresher right beside the ice, and that's because that's the actual action of the warm water melting the ice. We can see things like crevasses. We can see how the ice is being shaped by the melting, and we can get this really detailed picture of what's happening underneath the glacier. And we drove through, did several different missions. So this is 2 different transects of this area with IceFin. And so we got data all the way back to the grounded point. And that's the first time that had ever been done for Thwaites or really for any other glacier system. And so what we learn here is that we can see that physics happening. We can see the melting of the ice. We can see the warm ocean coming back. But it's a little bit surprising. The grounding line environment's a little different than we might have expected. It doesn't exactly match our models. In fact, it suggests maybe it's a little bit more, it's a little bit different than what we expected. So this is a picture of us deploying the robot. And then this is a picture from the forward-looking sonar of the moment when we got to that grounded point, to the place where the ice, the ocean, and the seafloor meet for the very first time. So what does that look like from the vehicle? It presented here in glorious standard definition is some of our forward-looking camera video from underneath the glacier. So you can see that kind of particulate in the water, and then you're going to start to see the edge of the glacier right here. And at this point in the video, Icefind is basically in a place where we couldn't fit any more, we couldn't actually fit any further below the glacier. And right in front of that picture there is the edge of the glacier. So right where the ice is kind of resting on the ocean. And what this is doing is it's allowing us to see exactly how fast this process is going, this melting is going on at this really important place where the ice is first exposed to this warm ocean. And so that camera data is, what we really resonate with, but all of the rest of the sensors on the vehicle tell us about the degree of melting. And so all of that particulate in the water column is actually being kind of turned up because this is sediment-rich ice that's actually kind of melting away. And so those particulates are falling out of the ice and mixing into the ocean there. You can kind of see these rocks that are going to get dropped out. You can see the structure of the ice as well. And one of the things that is kind of crazy is this kind of snapshot shows is that we could actually use our eyes in this environment to do some measuring of the melting. You can actually see particles streaming out of the ice. So what does that teach us? We've got this new data set. We know exactly what's happening in the environment. But one of the things that we learned was a process we didn't really know about, which is that it's not just the ocean melting the glacier up, but in fact, how the ocean is affecting the cracks. So the weak spots in the glacier turn out to be a huge part of the story, not just from them being places where the ice is breaking and it can kind of break up, but actually as that warm water gets inside it, it actually melts the cracks out. So the ocean plus the cracks is actually making the ice sheet even weaker. And so this kind of multiplying factor means that the way the ice breaks and the way that the ocean melts actually kind of adds up to make it even worse. So this is kind of a fundamental discovery that we were able to make by getting the robot into this place 2 kilometers from the borehole where we put it through the ice. So it's the crevasses are melting the fastest, which is weakening the glacier even further. And that's kind of contributing to our forward projections of sea level rise. I just got back a little over a month ago from Greenland. So this is our team from Greenland. So led by myself and Dr. Peter Washam, who's a research scientist in my team, our lead engineer, Matt Meister, and then the host of characters there, students, engineers, even a colleague from formerly of the military who came as our polar bear guide. And we were working supported by NASA, also through logistics provided by the National Science Foundation, as well as a private organization called Heising-Simons Foundation. So we went up to Pituffik, Greenland, which is home of the Space Force. They're doing missile awareness and mapping potentially hazardous asteroids and all kinds of things coming into the Earth's atmosphere. But we were there to measure the changing climate in Greenland. So we were actually driving out across the sea ice. That mountain you can see on the right there is Mount Dundas. You're looking back at Dundas Village, as well as the base in this shot. It's just a transcendently beautiful place to be in northern Greenland. This is what it's like to do some of that work. So here's a video from our snow machines as we're driving out. We put about 1,000 miles on our snow machines this season, just driving out, getting our equipment out, taking data in this environment. Just absolutely spectacular. And so what were we doing there? We were looking at a couple systems of glaciers that have what are called outflow channels. So one of the really interesting things that happens in Greenland is you get both surface melting. So because Greenland is so much warmer and it's warming so quickly, there's melting and ablation that happens at the surface that forms liquid water. And if it can get down through cracks or through moulins, it can make it to the bed of the glacier. But the glacier itself is also melting under its own weight, and there's subglacial water sources as well. So you kind of have lakes and rivers rivers that form underneath the ice sheet. Those contribute to how fast the ice can move. And once that water kind of goes through a river and ends up at the mouth of the glacier, it can also drive some of the mixing that can cause further melting to these glaciers. So the picture on the right is kind of showing a cutaway from a figure that's showing kind of how this works. Is you've got a river of fresher water that's kind of melting its way underneath the glacier, comes out through the mouth, through this kind of hole in the front of the glacier, and then mixes the warming ocean water towards the ice shelf. So we were down there to try to look for these features. And in fact, for the first time, we're able to go find these kind of very small holes in the glacier, right? So for Rasmussen Glacier, which is the picture on the left here, you can see our tent that we work from, our snow machines, and ice fin kind of being built up there in the background. This is a 4-kilometer wide glacier that's about 250 to 300 meters thick. And we're looking for two 20-meter holes at the bottom of the glacier that we know should be there. And so we kind of went and kind of did a hole-in-one, if you will, to go and find that. So we're back here. So I'm going to show you what it's like to drive your entire research program well underneath a whole bunch of glaciers and then find a hole in a glacier and swim up the dang thing. And that's what we did. And so this forward-looking sonar is going to show you as we're driving into the channel. So just a reminder, anything that's bright is like a wall that's reflecting sonar back towards you. Anything that's dark is kind of a hole in this particular area. So you're going to see that as we kind of drive the robot here. So you can see it's kind of that cavern. And so we're actually driving the robot in this place. It's about 15 meters wide, drove back through this hole underneath this glacier to measure the outflow that's coming out and how it's affecting the bottom of the glacier. We actually went all the way back till this hole in the glacier was only 2 meters wide. So we really got very nervous. We were didn't want to lose the robot, and then we kind of back ourselves out, pull it back, and then we went back and did it again. So what that allows us to do is to measure this process of melting and ablation at the bottom of the glacier kind of for the first time. So this is showing you that data. I watched earlier, right? Show me the data. Let's look at that. So the star here in this picture on the left-hand side is the place where we put the robot into the ocean. The blue line is the ice surface, the bottom of the ice surface. That's measured from the sonars on the vehicle. And the brown at the bottom there is the topography of the base underneath. So that's the seafloor. The trajectory here that's kind of colored, you can see it kind of goes from this pinkish color to a darker brown. That is the traverse of the vehicle. So that's the path we actually took. So we drive up and down in the water to be able to map the ocean conditions there. And those hot spots, those dark colors, turns out to be the plume of material that's coming out from underneath the glacier. So this is the track that the vehicle took in a map projection on the right-hand side and the data that actually came back from it. Only one part of the data. We have about 10 science sensors on the vehicle at any time, all gathering data. So what that can look like is now shown here. So we're going to look at a 3D kind of projection of that. And we can plot, in this case, we're plotting temperature. So you can see this kind of warm water. It's very, very warm, and it's making it back to the glacier. So it's minus 0.6 degrees, which is well above the freezing point of water in this environment. And so we drive ice fin back, we get this data, and we can kind of rotate it around and look at it. Here's two other projections of that. So on the left hand is salinity, and on the right hand is turbidity. And turbidity is just a measure of scattering in the water column. So basically, how particulate rich is the water column there? That's important here because it actually tells us what's the material that's coming out from underneath the glacier, because it's churning up particles and taking that with it. The salinity, the darker values here are the saltier water, and the fresher water is just a little bit less salty. So the light color is less salty. So if you look at that at the trajectory on the left, you can see that there's warm, salty ocean water that's actually making it back into this channel. And then you can see kind of the hints of that plume coming out along the top part of that colorized transect. So it allows us to look at the melting, it allows us to look at the outflow. We can also measure how fast all this is happening, so we can measure the speed of the water column. We're going to measure its oxygen content. So we put all of these signals together in order to understand all of the dynamics that's happening. It's important to make these new observations because there's processes we don't even understand yet, and how these cuts might actually affect that. How does it work to get to Greenland or to Antarctica? So let's say I want to understand Greenland or Antarctica or Europa in this particular case. I can get funding or support, usually from the National Science Foundation. Much of our climate work, especially in the poles, is funded that way. So Greenland here, you might go directly. So you get your logistics funding and you get your science kind of coming from the National Science Foundation. But there's also a ton of benefits to that, right? From that science, those science results actually end up as projections, right? Estimates of flooding that might happen here, in this case in New York City, projections, and then class materials that might get into your local schools. From NASA is interested not only in the Earth science part of it, but also funds astrobiology, so the search for life beyond Earth. And it does that by helping us develop techniques and technologies that we can explore these extreme environments here on the Earth as kind of training grounds to do that, as well as letting us measure the physical processes in Antarctica and in Greenland that are similar to places like Europa or even to Mars. So they fund that through the Earth science, astrobiology, and planetary science programs. But then they also bring in money and work with NSF to provide the logistics to get those scientists there. So if you love climate research, National Science Foundation is funding a lot of it. If you love climate research, NASA's funding a lot of it. But this work done on the ground can also be a collaboration between NASA and NSF. And then that all ends up as the science that ends up in your classroom, or the science that ends up getting us a spacecraft to go to Europa and inspiring many generations of people, as well as trying to help us understand, climate risk and things like that. So it's very interconnected. So what does that look like for us right now? The planned NSF science cuts, or the planned NSF cuts in this budget are abysmal. It's a 55% cut. This is a recent article from the New York Times showing what's happened already before this budget came out, and the spending in polar programs, so getting people to Antarctica and funding the science of Antarctica and Greenland that is going to allow us to understand what sea level will do, is already had an 88% cut this year. It's crazy. We're only spent 22% of what we would spend in a normal year, and it's only going to get worse, right? This is our information on how the sea level is going to change in the future, and we're decided to just cut it in half. On the NASA side, this is the biggest science cut in history in NASA, and it is the single largest budget cut ever proposed for NASA since the Apollo program, since the dawn of NASA itself, right? So we want to do these big things. We want to understand our planet. We want to have the smartest, best people in the country or in the world working here and doing their jobs here. You don't get it by cutting science this way, right? When we wanted to go to the moon, we put a huge amount of money and time into that, and that built new scientific fields. It also got you Velcro. It got you ballpoint pens. It got you the camera that's in your cell phone, right? Those were things that were developed for the space program. And so what's happening here is we've decided that we're going to go back to Mars, but we're going to do so by cutting the science budget in half. How does that make any kind of sense? So this is sources from the Planetary Society. I encourage you to go to their website to see even more analysis on this. What I want to end with is that science is good business. So the economic impact of science cannot be underestimated. About 0.6 of the GDP of the US is spent annually on fundamental research that is outside of defense, but its impact is about 15% of the GDP. So we get huge valuation from this science. It's good business, and cutting it doesn't fix your other problems. Cutting 0.33% of your federal budget does nothing but undermine these amazing products that scientists do to make our lives better. These investments in science are about people. They're about the lives that we have, about making them better. And these cross-government collaborations made by healthy institutions working together is what makes all of that possible. So I just want to just end up here with the fact that humans do the science and the science benefits humans. We get to go to these amazing places. We live on this planet that's dynamic and changes us and affects us. And it could never be more precious than it is right now. So I encourage everybody to kind of think about what the science means for you and what we might look like if we decide not to invest in it. So thanks very much.
Thank you so much, Brittany. That was amazing. And thank you for, I mean, the way that you link this all back to the cuts at the end, it was masterful. Thank you so much. We started a little bit late, so we're going to have questions. We do have time for questions. We can go over a little bit. I just want to, our chat loves robots. So the fact
I love robots too.
I'm fully like not in the lingo, but I've been told that blorbo is a term of affection. So Icefin, new blorbo is a good thing. They love Icefin. People want to volunteer to be your field assistant the next time. I think people love the pictures you've been showing. But we have tons of amazing questions as well.
Yeah, sure.
I think so we had one from Charlie Brown, which is how much of Greenland is below sea level? Could it all be undercut by water in the same way that these glaciers are?
Yeah, so actually a lot of the change, at least the ocean, a lot of the ice that's already been in the ocean, that we've already lost it in Greenland. So there's anecdotal evidence, so from 100 years ago, that there were ice shelves, like I described, like the Ross Ice Shelf, that used to cover the Arctic. And since industrialization, we've basically lost almost all of them. There's really only two great ice shelves, I would say, left, Petermann Glacier and 79 North Glacier in Greenland. So there's really, and there's still some tidewater glaciers. But the difference is that a lot of the loss from the ocean warming part is underway. However, the rest of the ice that's above sea level is still being ablated, right? Is still being really directly affected by temperatures rising. So the story in Greenland right now is that we have these, we have a few systems left that are still in the ocean. So this ocean warming is really accelerating that. But the effect of temperature and atmospheric change is a pretty significant in Greenland right now. In Antarctica, the story is still a lot of the ocean, although the temperatures are in fact warming, and you're seeing kind of the chains, the loss of ice march its way down basically down the peninsula and getting closer and closer to the main part of Antarctica. And so right now, kind of the undercutting of the ocean drives a lot of the ice loss that we see. But it's a little bit different. And so there's about 7 meters of sea level rise locked up in glaciers and the ice sheet in Greenland, and well over 50 in Antarctica. So that's kind of the scary thing. We don't expect all that to happen tomorrow, but that's kind of what we're talking about here.
It's wild. Thank you for that. We have a ton of questions, all related to like the logistics and safety of Icefin, as in like her safety. So, questions like, does Icefin ever get stuck? Like, does the probe ever like cause a crevasse to fracture and it falls on it? Like, how sturdy is it? How safe is Icefin? Is she safe?
Sure. Well, so Icefin's job is to go to the hardest to get to places and bring back the data. So we have gotten them stuck. We've only ever lost one of them. So we're building our 5th, that's kind of our 6th vehicle right now. Right now, we always keep kind of two active platforms. So we're on version 5 that we're starting to develop now. So this season, like, we got it wedged into some sea ice. The ice geometry is super complex, and we just think our way through it. We've got a bunch of different sensors. We try to roll the vehicle to get it kind of brought out. But there's like a tether, that's attached to the back of the vehicle. But it's both our safety line and the most dangerous thing on the robot, because it can get stuck in the ice. And so our backup camera I mentioned, like I used to like laugh at people who had backup cameras because I was kind of old school. I love old cars and stuff. But man, a backup camera really changes your life. It turns out also on a robot, because we can see what the tether is doing behind us, and it's really.
And you
simple.
actually have reverse gear as well. Like
yeah, we can go. We're 5 degrees of freedom, so I didn't really mention that, but we can go forward, backwards. We can pitch. We can yaw. So we can basically move everywhere. The only thing we don't do is roll, and we just weight the vehicle with all the heavy stuff is on the bottom to make sure that it's kind of it's kind of roll stabilized. But yeah, so we can back up, and then we also pull it with the tether. So we kind of have all of that, and we use the tether as a sensor. Like we know if it's getting really taut, the vehicle's slowing down, that there's something wrong between us and the vehicle, and so we can kind of use all of that to get it unstuck. And so we put it into these scary places. We're smart about it. We try to avoid it. We try to think through like how to get to the places we're going in the least risky way. But it just happens that these are really hard places to get to. And as long as we get the data, that's what we came for, right? So the tether allows us to get all the data from the vehicle. So even if we do lose a vehicle, which is just devastating, they become kind of members of the family. But at least we get what it came there for, right? Which is this really, really crucial data.
Amazing. We have time for one more question, which is kind of off topic, but super interesting, which is, has your team met, I guess, in Greenland? Have you ever met Inuit people during your expeditions? Like, what is the attitude of local people towards this type of environmental research in their area?
Yeah, in fact, yes, we did. One of the cool things, so we were stationed, or we were working at the U.S. Bidufik Space Base, which is it's a U.S. kind of mostly asset, but it's also co-funded. The Canadians participate in it. We're there kind of with the permission of both Greenland and Denmark. There's Danish contractors, but there are also members of Greenlandic communities who work there on the base. And we were also there at the end during what's called Greenland Heritage Week, which is when they actually open the base up to anyone who in the area. And it's really, really small number of communities all along along the coast there. So it's really spread out, but we did get to actually meet, pardon me, folks who brought in dog sleds. We're out hunting, so there were teams of hunters. We got to meet folks who work who are from other parts of Greenland, who come up here to work as contractors. So, and your question is about what is their attitude towards it? I mean, they were really excited and interested, right? The Danish were really excited and interested. In fact, the U.S. military were excited and interested. So it was really kind of an amazing international experience to be there, and we've tried to just be as careful as we can and be as communicative as we can about the results that we get there. I've also worked in other parts of the Arctic using other techniques that aren't ICEFIN. Same thing. So we've worked with the indigenous communities in the northern Canada as well. And actually the thing that I think that strikes me the most is just how much more excited and interested and invested they are, in fact, than I would say most Americans are in the health of our environment. And so my hope is actually we can learn from them, not just about those environments, and hopefully kind of partner and give back to the communities there, but also we could learn the enthusiasm and the respect for that from them as well.
100%. That's a great line to end on. Thank you so much, Brittany.
It was a pleasure.
Also, you may find lots of other questions in the chat. If you have a chance to interact with the chat, they'd love it. Thank you so much. Professor Britney Schmidt, everyone. That was amazing. So we have, I'm on for the next hour. We have another speaker or two who I'm going to introduce. But beforehand, we're just going to remember why we're here. As you saw, Brittany just talked about how important it is to have accurate projections of, say, sea level rise, for example, for communities in the US and in other parts of the world. And more generally, also every American needs to know what the weather's going to be like. If you're a farmer, if you're just like biking to work, everyone needs to know these things. And so weather and climate is important to every American. And the US has been at the forefront of weather and climate science ever since its inception, and we have continued to be a leader of that over the past 80 years. And we've built this unparalleled network of models, climate models, weather forecast models, and observations. We've got these planes, balloons, floats, and boats, and this whole grouping of observational systems and satellites and models is unparalleled across the whole of the Earth, and we need to protect it. And this, because it really is a miracle. And sadly, what we've created is under threat. So recently there have been cuts to American science and weather forecasting and to our observational systems. And we've already lost so much. We heard from fired government employees a few days ago. We heard from directors of the National Weather Service who've already talked about the way that these cuts have been affecting the day-to-day lives of forecasters who are trying to bring us this crucial information. And this is potentially just the beginning of something much worse. So Britney also talked about this. There are proposed cuts that are on the desks of our Congress members right now, which we're scientists, we're told to provide evidence. We got evidence right here. These 3 QR codes are linking to the proposed budgets for NOAA, NSF, and NASA. And these are proposed cuts of 50% for NSF and NASA, and a 100% cut to the research arm of NOAA. So this is really existential stuff. And it doesn't have to be this way. We are asking you all to, if you feel so inclined, if you feel passionate about what you've seen today and you want to protect it, reach out to your representatives at wclivestream.com/act at the bottom. There was a little bit of discussion in the chat earlier, like, should I reach out to my representative if they're Republican? Should I just reach out to Democrats or people who care about climate? We should be reaching out to all of our representatives. So it doesn't matter. Every American needs actionable weather and climate science. And as Andy Dessler, who you may have heard a couple of days ago, as he said, for every person that phones, they're going to assume that there are 100 people who think exactly the same as you, who just haven't bothered to phone. So your voice really matters, and I encourage you to go and contact your representatives and tell them to save America's forecasts. So with that, we're going to go back to the science, and I am super excited actually to introduce John Morales. So let's bring him up on stage. John is a veteran meteorologist and hurricane specialist. He's worked in South Florida television weather forecasting for over 3 decades. And he's best known for his work at NBC6 in Miami, where he provides hurricane analysis and weather coverage for the whole region. We're taking this live stream is going all the way up to the start of hurricane season tomorrow, June 1st. And John is recognized for his expertise in tropical weather systems, in particular hurricanes, and he has been a trusted voice for South Florida residents during past hurricane seasons. I'm trying to embarrass, every speaker that we have with something complimentary about them. And John is no different for his life-saving work during the 2017 hurricane season. John was recognized with the John Coleman Broadcast Award at the National Tropical Weather Service Weather Conference. So John's going to be talking to us again today about navigating the 2025 hurricane season. The floor is yours, John.
Thanks, Andrew. It's an honor to be here. And, again, wclivestream.com/act to make it easy for you to contact your federal representatives, your electeds, as they say in those circles, to demand that, these cuts, which are not surgical in any way, they're with a sledgehammer, honestly, be reversed to save the science. Because as my subtitle says, attacks on science couldn't be happening at a worse time. And because hurricane season is starting now, it is putting lives at risk today and down the road too. Because, for example, many of the NOAA laboratories where we get to, learn the physics of hurricanes or improve on hurricane forecast models and such, the cuts there, like Andrew mentioned, are expected to be existential. So we don't know if we can even maintain these models or improve them going forward. So I thought I'd start by kind of presenting a little bit of how we've gotten here. I've done some reporting on this on TV, as Andrew said. My background does go back to NOAA and the National Weather Service. I was a forecaster, a meteorologist for the National Weather Service at the beginning of my career in the first 7 years. But for the last 34 or so years, I've been a broadcast meteorologist in the Spanish language first, and since 2009 for NBC in Miami. And as part of my work at NBC, not only have I presented the weather, I've been a chief meteorologist, but now I'm their hurricane specialist. And along the way, there's been some science reporting too. So I kind of want to start with this video to make us all think a little bit about how we've gotten here. Now, this was during COVID, all right? And I'm linking some of the questions and attacks on science that were starting during COVID to some of the attacks on climate science that we see today. Watch and listen.
It seems like every disaster movie starts with a scientist being ignored.
No, I want the review part. I really do.
Yeah, don't you see the danger shown inherent in what you're doing here?
In many parts of the world, and especially in the U.S., a penchant for anti-intellectualism in recent decades has consumed us like wildfire. Science fiction writer Isaac Asimov famously said that Americans suffer from a false notion that democracy means that my ignorance is just as good as your knowledge.
This is their new hoax.
When it comes to coronavirus, devaluing expertise and scientific knowledge has likely put us in a tight spot.
What's happening in big cities. We know that there was lots of people on talk radio, for example, and the anti-science community who were actively spewing this anti-science activity, even in the face of the outbreak.
They're scaring the living hell out of people, and I see it again as like, oh, let's bludgeon Trump with this new hoax.
So if skepticism or downright denial of science is causing problems with our current virus emergency, imagine the damage it has inflicted over the course of many years to what historically has been perceived as a more distant menace, the climate change crisis.
Some of the same organizations and some of the same people who reject scientific authority on climate change also reject medical authority on the pandemic.
Many aspects of human nature make it more difficult to comprehend the building climate threat, like not seeing it as a clear and present danger and simply being fixed in our ways.
We don't experience risk properly, we don't like to change, and we don't respect people telling us something that we don't want to hear.
But what if winning the battle against COVID-19 brings a renewed appreciation for science?
I'm hoping to be optimistic that we will be able to have less deaths than we're projecting. If that isn't object evidence that the science works, that we knew what we were talking about, nothing will.
It seems like, oops, let's see, next slide. There we go. I've written a lot about this. I invite you to the Bulletin of the Atomic Scientists. You can find it on thebulletin.org. And many of you in the audience probably know the history of this organization. They're the ones, by the way, that do the doomsday clock. It's on the upper right there, you know, how many seconds to midnight based on all the existential threats to humanity. And Bulletin of the Atomic Scientists considers that climate change is one of those existential threats. But along with writing about climate change, I also sometimes delve into other subjects. And this particular column I reposted last year on the role of the scientists in a post-truth world. You know, my conclusion is what you're reading there at the bottom. You know, how Americans are going to reckon with this is going to be one of the biggest challenges of our time. And people like me, you know, a scientist that can communicate could be crucial and key to be able to break through this. But we do need to meet people where they're at, right? We can't be just, you know, throwing textbooks at people's heads. We have to find ways to relate to them and make sure that we connect so that therefore they'll accept or be more accepting of the science. Now, here's another one, and we'll watch it first and discuss it later. Let's try this.
Well, good evening, everybody. I'll have your weather segment in just a second, but I want to show you this. Several months ago, I was part of an experiment. Now the results have been published.
Climate change is happening. Humans are causing it. and it is affecting how we live our lives. And so it only makes sense for us to share what we know.
Given how many years I've been communicating about climate during my weather segments, I thought I might be making a difference in improving our viewers' awareness of the burgeoning crisis. But I didn't really know for sure until we ran a controlled experiment in which we showed 600 people 2 versions of my weathercasts.
One was a typical weathercast that you would see on your TV in Miami. Then we did a separate weathercast that really tied what was going on with your weather to climate change and some of the climate trends that we're seeing.
Folks, we will continue to enhance the message that we need to act on climate.
The findings were remarkable. Based on the viewers' answers to a questionnaire, the ones watching me provide climate context to our Miami weather trends came away understanding climate change as more of a local problem.
And TV meteorologists are really making those connections between those changes in their weather and what's happening with climate change overall, where that's going, so that their communities can understand how this is really affecting them and what can be done about that.
You not only gave them important information, but you also stimulated desire among them to learn more.
Hi, John, you've muted yourself. We can't hear the video.
And help them to understand more about the world around them.
This study also included Chicago TV weathercasts, but now my colleagues are wondering if meteorologists involved in climate communications elsewhere are helping bring all Americans a greater understanding about the challenges we face in a warming world.
If that can happen, then you and your members of the broadcast meteorology community will have you will have done America an extraordinary service.
So the point of this is I'm showing you proof in the pudding here, right? In other words, I've talked about the role of the scientists in the post-truth world. And here is an experiment where we've been able to show that by providing climate context, the people that watch this were able to internalize and personalize the threat. And when you get people to do that, that's when they start to call for action, right?
Good evening, everybody.
Sorry about that. So this is where we're coming from. This is where we're at today. You've seen many of these headlines. Again, Andrew just mentioned this at the top of the hour as well. The all living former members of the National Weather Service indicating that they fear that there's going to be unnecessary loss of life this year due to these cuts to resources and staffing at NOAA and the National Weather Service. A headline from CNN that the U.S. Weather Service is crippled, and then another column from me on the Bulletin of the Atomic Scientists that basically we're all losers here when scientists and weather forecasters are being targeted. Hurricane season, of course, does start tomorrow. It lasts until November 30th in the Atlantic Basin. The peak of the season isn't for another couple of months. But you can get activity in June. You can get activity really outside of hurricane season too. But the peak generally is August, September, and October. And as we ramp up to that, we'll be watching very, very carefully as to what's out there. Let's talk a bit about weather observation. So, we've talked about cuts to NOAA or National Weather Service staffing. But let's talk about the cuts or the resulting cuts to the data. Now, the graphic on the left is, pretty busy as you see, but just look at the line at the very top, the row at the top, and you can look at the graphic on the right as well. So what are some of the tools that scientists use to monitor hurricanes? Well, satellites. Back in the old days, before satellites, ships were around. They could relay information. These days, we've got buoys and all over the place. Hurricane hunters, aircraft reconnaissance, radiosondes carried by balloons, weather balloons, which, by the way, parenthetically, I'll tell you that the information that comes from radiosondes is many times, multiple times more granular than the information that I can get from a satellite. I know that some in the audience understand that satellites can remotely sense some weather elements, including temperature and humidity and wind, for example. So it doesn't just, they don't just take pictures of clouds anymore. But a radiosonde does that basically every 3 meters, right? So it's much more granular, and it's just better. Radar and the automated surface observing system, those are the surface weather stations. All that is fed into observations, which feeds, and I don't know if, you can't see my cursor, feeds into numerical weather prediction. The observations, of course, also go to the different branches of the National Hurricane Center, like the Tropical Analysis Forecast Branch, or the, well, I'm going to blank on these right now, but the point is that all this information is needed, not just to have the models forecast the weather, but also have the hurricane specialists be properly informed. That in turn makes it down to the local weather forecast offices from the National Weather Service, and eventually to the emergency managers who are in charge of saving life and property across the different counties. The problem right now is that this is being degraded, all right? So think of coastal radars. There are many electronic technicians at National Weather Service offices who were fired early on during these cuts. Now there's a hiring freeze and you can't replace them. Those that weren't terminated were, strongly encouraged to leave with buyouts and early retirements. The bottom line is that you don't have the personnel to necessarily maintain these. And if these go down, they may be out for a while. The same applies to the hurricane hunters. Some of the maintenance people that maintain these aircraft are no longer there. And we're concerned about flights being canceled because of it. More importantly, there are mission specialists. These are meteorologists that fly on the NOAA hurricane hunters who were also cut and we're short those people too. So I'm very concerned about a situation in the Atlantic where we might see less scheduling of hurricane hunter aircraft, or perhaps short-fused cancellations of missions for lack of maintenance or lack of personnel that can go out there. Now, the lack of radiosondes is also heavily impacting numerical weather prediction. So our models are also being degraded. The accuracy, the verification statistics, if you will, of these models, whether it's the American GFS or the European or the AI model, they're all seeing lesser degraded performance at the present than they had at the beginning of the year. Now, can we project that out through the entire hurricane season, or is this just a blip? I don't know, right? So let's be fair. I don't know the answer as to whether this short-term trend is going to continue throughout hurricane season. But the trend is there, and I think it's very concerning. One of the things that I'm particularly petrified about, to be honest, is that we're going to have the chance for, I'm not forecasting this to happen, folks, okay? But there is a possibility that we're going to have an Otis type of nightmare scenario develop in the Atlantic. So in Otis, what happened was the National Hurricane Center thought the storm was of a certain intensity. They were basing that information off of satellites. There were no hurricane hunter aircraft flying in there for reasons that go beyond the scope of this webinar, of this stream. I can tell you that in the Eastern Pacific, they fly much less. There are much less recon flights in the Eastern Pacific than there are in the Atlantic. By the time the hurricane hunter got to Otis, it wasn't a tropical storm. It was a Category 3 hurricane, much to the surprise of the specialists at the National Hurricane Center. So there was no data when the system was rapidly intensifying, and my goodness, it was extremely rapid. It was extreme rapid intensification when it was going through that phase. No data. Hurricane Center was flying blind. They, frankly, and they'll tell you this themselves, they botched the forecast. They called for basically a strong tropical storm, low-end hurricane to hit Acapulco, And Acapulco got hit by a Category 5 hurricane. And there was greater loss of life and greater amount of property damage because of it. And the underlying reason for missing that forecast was the lack of data, because the planes were not flying in there until it was too late. And I feared that that could happen in the Atlantic this year. Again, there's many more planes. And in fairness, it's not just the NOAA planes. There's the aircraft from the Air Force Reserve Unit, right? The 53rd Weather Reconnaissance Squadron that does fly into the hurricane. So, and as far as I know, the Air Force is not being affected by these cuts. But NOAA has 3 aircraft, and it's a substantial part of the mission. And I think it could be impacted this year, and I'm fearful for that. I am sure others during this live stream have covered this, but I'll cover it again. Here's just an example of a morning in May, earlier this month, in which you can see the huge gaps, particularly in the upper Midwest and Northern Plains, of missing radiosonde data because balloons were simply not released there because they just don't have the personnel to do it. Every once in a while, you know, there's other reasons for it. It's too stormy to release a balloon, right? But generally speaking, we're seeing this pattern very often now where there are big gaps in data. And don't you think that it doesn't matter what's happening in Colorado, the Dakotas, Nebraska, Iowa, and Wisconsin in relation to what goes on in the Atlantic? Because the weather, the jet stream, goes from west to east. Just about all weather in the mid-latitudes goes from west to east. So what's happening upstream, in other words, what's happening across North America, impacts conditions across the Atlantic. And it's not just the mid-latitude section of the Atlantic. It can drop down into the subtropics or potentially tropics. So we need to know. We have the need for all this data, not just for me to look at the actual sounding that's coming from, I don't know, Lincoln, Nebraska, right? But to be able to feed that into a computer forecast model that's going to crunch out a forecast that now, as you can see on the image on the right, appears to not be as accurate as it was just a couple of months ago, right? So the American GFS accuracy, as measured by 500 millibar heights in those locations between 20 and 80 north, has been degraded. And yes, the American model amongst these 3 is the worst. It is the least accurate, but it's clearly showing some degradation. If you look at the European model in blue, their numerical physics-based model, I think it's also showing some degradation. And even the new artificial intelligence model, it may have not as pronounced, but shows just slight degradation since then. So throughout my career, people have known me as a non-alarmist guy. I may not sound non-alarmist today, but I've got reasons for it. As a just the facts guy. They've known me for my hurricane acumen, and they've known me to be extremely confident in my presentations. I'm going to show you this presentation from Hurricane Dorian in 2019. Dorian, Cat 5, moved painfully slowly through the northwest Bahamas, flattened that region with a humongous storm surge. And of course, those winds, you know, sustained 165 and higher. And the hurricane was crawling westbound, getting closer and closer to Florida. People were starting to get worried. I could tell by looking at my social media feeds. So I decided to say this.
Listen, I've been on this, you know, since 8 o'clock this morning on social media, and there is a lot of anxiety out there because you don't see it turning, right? When is it going to turn? John, it's not turning. It's coming straight to us. It's going to turn, all right? The turn was never forecast to be on Sunday. The turn isn't even on Monday morning. The turn will come Monday afternoon, Monday evening, into Tuesday.
So I ask myself and I ask you, will I be able to stand in front of the screen this year and say things with this level of confidence and forecast with this level of confidence. I have my doubts. What we're seeing, these cuts that are being made, without rhyme or reason, it's fine to cut. It's fine to make things efficient, but not with a sledgehammer, right? This is going to impact us this hurricane season. This is why National Weather Service directors wrote that op-ed, because they're fearful that lives will be lost. It could be from a hurricane, could be from tornadoes, could be from severe thunderstorms. I don't know. Flash floods, big killer in this country, right? But I am telling you that I, as a seasoned 40-year veteran meteorologist, feel less confident this year in forecasting hurricanes than I've been in recent memory. I mean, I'd have to probably go back to the 1990s, the last time I felt, nervous about a forecast. And it's because of these cuts, and it's the reason these cuts need to be reversed, because it matters to everybody. And listen, it's not just about the lives, okay? Hurricanes take lives, but hurricanes also ruin lives. Oftentimes, it takes decades for families to recover from hurricanes, if they ever do. And this is, it disproportionately happens to those that are financially challenged. It disproportionately happens to people of color. It disproportionately happens to Latinos como yo, right? And unfortunately, if people are going to be surprised by a stronger hurricane, or they're not going to evacuate because they're not getting the right information, or they're simply not going to be properly prepared to save life and property, I just don't understand. I fail to understand how that makes America great in any way, shape, or form. All right, so hurricanes globally are getting stronger. It's not that we're seeing a greater count of tropical storms. There aren't more tropical storms or more hurricanes around the globe, all right? The sum of the tropical cyclones is not a greater number. What we are seeing is that the storms that do form have a greater propensity of becoming catastrophic. There is a greater proportion of tropical cyclones reaching category 4 and 5 intensity. Category 4, like Maria. Category 5, like Dorian. Another category 4 would be Helene. Milton was a 3 when it made landfall, but at one point it was a 5. And I can just keep naming, Irma and Harvey and all these other storms, Katrina, right? All these other hurricanes that just in the last 5, 10 years, 15, 20 years have been impacting the United States and our neighboring countries. And because of attribution science, which is peer-reviewed, we know that warmer waters have led to these very recent hurricanes ending up stronger than they would have been without the waters heated by the changing climate. We're just coming off a couple of record years in terms of sea surface temperatures all around the planet, including the Atlantic. And these hurricanes, Helene, Milton, and Beryl, were all impacted by that and all made stronger by waters that wouldn't have been as hot if it wasn't for the changing climate. Now, I'm saying that very categorically, right? I'm not giving you a probability, and perhaps I should, I should be more scientific and tell you that extremely likely, as opposed to just categorically telling you that they were made stronger by climate change. But here's a way of looking at that. All right, here's Milton's path across the southern Gulf of Mexico as it made its way towards first the Yucatan Peninsula, and then just barely missed them, and then on towards Florida. And this product from Climate Central, again, peer-reviewed science here, all right, allows for you seeing what is the likelihood of the temperatures being observed at that location due to climate change. In other words, in the dark reds and reds, conditions were made 100 to 800 times. Those temperatures were made 100 to 800 times more likely to happen due to the climate emergency. All right, so that's how you interpret this chart. Excuse me. And I mean, obviously, major hurricanes cause more damage than Cat 1 and 2 hurricanes or tropical storms. And you can get damage from a tropical storm, especially from rain. You can get it from a Cat 1 or a Cat 2. But when you're talking about Cat 3 or higher, that's where the big costs are. So the stronger the storm, the bigger the cost. I know this is a complicated graph, but boy, I always like to show it. This comes from Kerry Emanuel. He is a climate scientist at MIT who specializes in hurricanes. And we're going to talk Hurricane Maria briefly here. Maria became, for me, the most difficult, the hardest part of my career was the day on the eve of Hurricane Maria that I had to announce to my fellow Puerto Ricans that a hurricane of this magnitude was about to strike them. And it was the first time in over 90 years that Puerto Rico was struck by such an intense hurricane. Now, this chart is logarithmic, so make sure you realize that you go from 10 to 100 here on the left, okay? Here's the wind speed of Maria when it was at 17 degrees north and 64 degrees west. That is just south of St. Croix. And I'm telling you, just about every hurricane that passes that latitude and longitude goes into Puerto Rico, okay? So basically, what we're looking at is what is the return period, or what was the return period of a hurricane like Maria, Cat 4, which flattened Puerto Rico, and they're still trying to recover from that, right? Based on the 20th century climate, the return period looks to be about once every 200, maybe 250 years, right? What would the return period of Maria be towards the end of the present century in the climate we are creating, that mankind is creating, unless we reverse our injection of greenhouse gases into the atmosphere? The return period would be one every 20 or once every 25 years. And the rhetorical question for everybody in the audience is, can a society be resilient enough to stand up to, 2 Marias in 20 years? I'm not sure. And I can tell you that, again, there's many communities in the Caribbean in particular, in the Bahamas with Hurricane Floyd, which was over 20 years ago. They're still trying to recover from that. And Puerto Rico is still. All right. We don't have a lot of time left. I just want to go through this briefly just to talk about this season's outlook, the outlook for this hurricane season. Listen, a lot of the narrative out there seems to be, it's not going to be that bad. We've come off these incredible years. It's not going to be that bad because the water is not as hot. And you're right, the water is not as hot. But man, it's pretty close. I mean, look at it. So this is 2025. Here's the record from 2024. Here's 2023, and basically right along the line of 25. And then here's all the other 30 years, right down here. And here's the average. I mean, the average is way, way, way down. So this is across the world. Sea surface temperatures, yeah, they're not record setting, but they're top 3. Here's the North Atlantic. Again, top 3 of the last 30 years. Here's the Gulf of Mexico. I mean, the Gulf is boiling again. I mean, the Gulf looks like 2024 again, when we had Milton and we had Helene and we had Debbie, right? Just to mention 3, and Beryl as well. We had all these landfalling hurricanes in the U.S. So I would listen to NOAA, which if you add their numbers, NOAA says there's a 90% chance of an at or above average season for 2025. And that's the way I would look at it. The El Nino, La Nina might have something to do with that too. Don't have time to get into that. And then here are some of the outlooks from the numerous entities that put out seasonal predictions for hurricane season. You average these out. By the way, here's the NOAA prediction on the left. Here's Colorado State, the legacy entity that predicts for hurricane season. You average all these out, comes out to a little bit over 8 hurricanes. The average number of hurricanes a year is 7. So basically, the average of all these entities is for an above normal year. So that, folks, concludes my presentation. And I thank you for your attention. And don't forget to contact your representatives.
Thank you, John, for taking us through all of that material. That was amazing. Thank you. We have some questions in the chat. I think maybe just quickly we can do this one, which is, so if hurricanes are strengthening with time, are we going to eventually need to start calling things Category 6?
Okay, it's a good question. By the way, I have a bit of cold, and I realized that I muted myself for coughing, and then I forgot to unmute myself, and you were not listening to the report earlier. My apologies. Okay. So there's been some chatter about this Category 6 business. I'll frame it this way. People in Puerto Rico are upset because they saw such catastrophic damage, they could not believe that it was just a Category 4, right? But when you read the Saffir-Simpson scale's description of what a Cat 4 does and what a Cat 5 does, both descriptions start with the word catastrophic. A 6 would be also catastrophic. There's nothing above catastrophic. I mean, you get to 4 or 5 or 6 if we ever came up with one, and it would be catastrophic. So I don't necessarily see that happening. I think the scientific community is not on board with that, and we probably won't see that happening anytime soon.
Yeah, it makes a lot of sense though. Like if there's already so much damage, it becomes immaterial, whether we call it 6 or 7 or something. People are already suffering so much.
Right.
There are a few questions, which I think I'll put one up, but they all kind of revolve around this idea of, so if the US is losing radio sonde coverage and weather balloons and things like this, where could you look? Like, is it possible to look to other places, either like the private sector or European models here, to try and get more certainty, or is there really no replacement for what we have here in the US?
Well, I mean, the problem is that all these global models, or even the specialized hurricane models, they all use the data from all over the world. Because if you remember from Lorenz, the butterfly effect, right? I mean, if a butterfly flaps its wings in Japan, you can feel, right? That is true. What goes on anywhere in the atmosphere, anywhere across the northern hemisphere, has impacts downstream. And therefore, the European model's accuracy is being impacted by the lack of weather balloons in the US. So it's not just the American model, it's the European one too. There are some private entities that generate models, especially now with AI, which can be less expensive to run these models. It's not as intensive as the traditional numerical models are. But of course, those are proprietary, and you don't always get to see them. So I can't necessarily run to them.
And I think we have time for one more question, which is, so you talked about incorporating a climate connection into your weather forecasts. So talking about this is being made X% worse or something. We have this question from Manda, which says, would broadcast corporations support climate change connections as part of their weather forecast reports, given the political climate amongst other factors?
It's really interesting. Weather is a big ratings driver for newscasts, both local and at the local level and nationally. And that's why, and I know probably very few of the people in this audience actually watch shows like ABC, World News or NBC Nightly News or whatever. But when you watch those shows, you'll see how much weather content they have. They don't always connect it to climate. And studies show that Americans very infrequently see reporting on climate. I would say, given the current political environment, where there is an absolute fear of the regime, I think it's unlikely that we're going to see this go in the right direction, at least on the short term.
Great. Thank you, John, for answering all those questions. If you hang around, there are a few questions back up in the chat. We don't have time to go through all of them, but let's thank John again for really a fantastic talk. Thank you so much.
Thanks.
Yeah, so we are in hour 80 of the 100-hour live stream to Save America's Forecast. That means we are 80% of the way through. That was hard. I'm pretty sleepy. And so I just want to thank you guys for sticking around. I'm going to introduce one more speaker in a minute, and then I'm going to head off. But I will see you guys at 3 a.m. Eastern time for some late night programming. Be sure to stick around till then. But before I do that, let's just quickly come together. Let's remind ourselves. Let's really be cognizant of why we're here again. And the reason is, as John has just showed us, that weather is super impactful to Americans and to people around the world. So he was talking about the impacts of even a Category 4 hurricane in Puerto Rico, for example. We really need the confidence to be able to predict these things in advance. And like John was saying, it's really questionable with the cuts that we're experiencing at the moment, whether weather forecasters, broadcast meteorologists are going to be able to continue to provide this confidence and this assurance to the public. And we've already experienced a lot of these cuts already. We had the fired NOAA panel a few days ago, or I forget when it was. This thing is really blurred, but a day or two ago, where we had people who were supporting NOAA in various different ways. Either it was research scientists or communicators who were fired abruptly, and that was done by executive order. But we also now have proposed budget cuts, which are going to Congress. So these are proposed budget cuts to NOAA, to NSF, to NASA. You can look at the more details in these QR codes here, but just to give you the too long didn't read, these are on the desks of our congressmen and women right now. These are 50% cuts to NSF and NASA's Earth science budgets, and this is a 100% cut to the research arm of NOAA, and that is truly gargantuan. And for all of you who's been following along and thinking about things like the Argo program, for example, that the U.S. funds about 50% of this Argo program, which sends robots into the ocean and measures things like ocean temperatures, for example. That would be severely underfunded under these proposed cuts. And we would also have drastic cuts into to funding for undergraduates and students who are trying to get into weather and climate. We need a workforce who is climate and weather literate, who can really help us through. And this is severely under threat. So we're going to encourage you now to call your representatives. So we have this link down at the bottom, wclivestream.com/act. And once you go there, it's going to redirect you to this website called 5calls.com. And if you put in your zip code, it'll tell you the names of your congresspeople that you can phone, and it'll give you their numbers, and it'll give you a script to read. You may get put through to their staff office. You'll probably get put through to their staff office, but they'll log it, and they'll know that if you're speaking out, there are probably 100 more people like you who are also speaking out. I just want to give you an update on how many people we actually have who have filled out this, who've done the 5 calls so far. So you can go to the app. And it's probably not going to show up on my screen very well, but if you go to the 5 Calls app, you can look at this issue, you can look at information, and we have 6,886 people who have already called to support weather and climate science and to encourage their representatives to vote no on these cuts. That is truly incredible. You guys are amazing. And I think we have an unofficial goal of trying to get to 10K calls by the end of this live stream. If you can help us make that happen, that would be incredible. So thank you very much. I'm going to introduce our next speaker now, who is Kristina Dahl, Kristina is the Vice President for Science at Climate Central, where she leads the organization's scientific activities and designs analyses that help people connect their lived experiences to climate change. Previously, she served as the principal climate scientist at the Union of Concerned Scientists, researching various climate impacts, including the effect of extreme heat on outdoor workers and the connection between emissions and wildfires. Dr. Dahl holds a PhD in paleoclimate from MIT, and this is the thing we're embarrassing you with, or giving you a big compliment over, is you were named in 2023 the Time 100 Big Next Innovator. So we've had an amazing session so far, and this talk is going to be no different. Kristina, take it away.
Thank you so much, Andrew, and thank you to all the organizers of this incredible event. It's just amazing to hear that you've got over 6,000 people who have already clicked through and made those 5 calls is just so inspiring. Thank you. So the title of my talk today is Mud Models and the Making of a Climate Story. And what I wanted to do is highlight for everyone just how much federal funding and federal data sets have enabled me to have a career that I feel really excited about, and that I think when we look at not just my contributions to science, but these collective contributions to science really do impact all of our lives and impact sort of human understanding of this big, beautiful planet that we live on. So I'll be sharing sort of highlights from my 25 years as a climate researcher. It's hard to believe it's been that long. As Andrew mentioned, I did my graduate work at the MIT Woods Hole Joint Program, where I studied paleoclimate, which is the history of Earth's climate. And then after graduate school, I thought, you know, it's interesting to think about climate from thousands of years ago, but there's a really serious climate problem happening right now. And so I switched gears, and for the past 20 years have been researching kind of climate science and climate impacts. So I'll be sharing some of the federal sources of funding and data sets that have really enabled me to do the kind of research that I do. And I hope that by tuning in tonight, you get a sense of what a scientist does and how a scientist relies on these resources that we all ultimately benefit from. Okay, so hoping that everyone is on board with this graph who's tuned in tonight. Understanding Earth's climate is critical in this moment. This is a graph showing global temperature change since the year 1880 or so. This doesn't even include the last few years, which have been even higher records. So over this time period, we've seen about 1.3 degrees Celsius of warming. We're seeing unprecedented rates of warming. We're already seeing the effects of this warming play out. And while I was aware of this as a college student in the late 90s, it was still, at least in the public eye, a very controversial issue at the time. And so one of the interests that I developed in college was paleoclimate, or trying to understand the history of Earth's climate so that we could put our current climate into context. So we know today's causes of climate change, largely the production of electricity or power sector. Transportation is a big one as well. Generally burning of fossil fuels. And there are, of course, other contributions too, like agriculture and our buildings and building materials, etc. But paleoclimate asks, what was Earth's climate like in the past, thousands or millions of years ago, before we had this human influence on the climate? And there are a lot of different ways that paleoclimatologists try to understand the past climate. So I think all of us are probably familiar with tree rings. A tree grows a little bit each year and puts on an additional ring. And you can run your finger along a tree trunk like this one and essentially count back in time how old that tree was and think about how, what the climate was like, what the place was like when that tree was a little baby. And geologists do this in similar ways. So my specialty as a paleoclimate person was looking at the sediments from the bottom of an ocean. And generally the way this works is kind of like a tree. A little layer of sediment builds up on the ocean floor year after year after year, and you can take a core through that sediment And it is, again, it's like a timeline of Earth's history. And the thing, like a tree, you know, the oldest trees on the planet live a couple thousand years, but mud has been accumulating on the bottom of the ocean for thousands, millions of years. And so these sediment cores that we take really enable us to, you know, like running your finger along a tree trunk, to run your finger down this core of mud and analyze what's in that mud. And it can tell you about the conditions of the ocean, the atmosphere, the planet at the time that the sediment formed. The way that we gather these sediment cores is on big ships like this one. This is the research vessel Atlantis, which is based out of Woods Hole, Massachusetts. You may be familiar with it because it is the home of Alvin, which is the deep sea submersible that discovered the Titanic many decades ago. But Atlantis is also used to take sediment cores. So this is the method that we use to get those cores. You basically drop a big pipe down using a very heavy weight at the top of it. You slam it down to the bottom of the ocean, sinks down, you bring it back up, and voila, you have a record of Earth's history. This is what those cores look like. You can see even in this one, some black bands and green bands and more brown bands, and all of the stuff in these sediment cores can tell us about our past climate. So scientists use look at the organic chemicals within these, they look at the fossils within them, and we've developed all these really interesting ways to try to get at past climate change. So this is one record of climate that we don't see as often, but this is showing change in global average temperature from basically year 0 to year 2000. So here we're looking at a 2,000-year-long paleoclimate record. And you can see that climate was mostly stable until about mid-1800s or so. And then we see the rise in warmth that is caused by human climate change. We can even go back farther if we use different paleoclimate records. This one, I'm letting you in on a secret, paleoclimatologists like to flip their x-axis. So you got to kind of wrap your brain around this one a little bit differently, where the present is on the left at 0, and we're going back in time thousands of years ago, 800, 900,000 years ago as we go to the right. And you can see these big shifts in global temperature. These represent our ice ages, when Earth was warmer or cooler. And generally, these records are produced by, often like single sediment cores or a single ice core, and sometimes, a pool of a few, but essentially telling the record of climate at a specific place. But when I was in graduate school, I wanted to do something a little bit different. And I wanted to ask this question: can we reconstruct wind patterns from thousands or millions of years ago using sediments from the ocean? And when I was thinking of patterns, I was thinking not just of a single sediment core, but essentially I wanted to create like a wind map of the world, or of a part of the world, like you might see in the newspaper or in a weather forecast. So looking across space to try to understand shifting wind patterns over time. But the problem was that no one at my institution, at Woods Hole Oceanographic Institution, had funding to do that work. Not my advisor, not anyone in my department, not anyone at MIT. And so there wasn't a real easy way for me to try to do this, even though my advisor and I thought it was a really cool idea. And so I applied for a small grant for exploratory research, or a sugar grant, as they were called at the time, from the National Science Foundation. And it was small, like $5,000, $10,000, just enough to cover the cost of analyzing samples and shipping core samples around the world, because there were people in Germany who had what I wanted. And so it was small, but I was able to do just what I was hoping to do because of this NSF grant. So my focus was on trying to reconstruct the history of winds associated with the Indian monsoon. So this is a map of the Arabian Sea region. And you can see this red arrow here. These are summer monsoon winds that blow toward the continent. You can also see that there is this green wind system that comes from the Arabian Peninsula and a blue wind direction that comes from the continent. And each of these wind systems blows over different types of plants. As you can imagine, there are different kind of growing ecological zones in these regions. And as the winds blow over the plants, they ablate or pick off little bits of the leaves. And the chemicals from those leaves get captured in the sediment. And then you can actually analyze the chemistry of those leaf wax particles to try to understand where the winds were coming from. So all of these compounds blow from different directions into the Arabian Sea, and the goal was to create a map that would tell us how the boundaries between these winds shift over time. So this was a real trip. I went back, this was one of my first scientific papers from 2006. It's online amazingly, because I think I still have a few print copies from when we used to do that. So what I was able to do is I took samples from all of these sediment cores all around the Arabian Sea to try to get a sense of whether we could even do this work. Could we create a map of wind patterns? And the answer was yes. So what we found is that across the Arabian Sea, these plant wax chemicals had different chemical traces that we could actually identify. And you could see this line that, like, this is crazy. I hand drew this in the scientific paper. Somehow it got published. Kind of cool. But this line shows the boundary between those winds that blow toward the Indian continent for the monsoon and the winds that come off the Arabian Peninsula. And as climate changes and as the summer monsoon winds get stronger or less strong, this boundary line shifts around in time. And so I was able to answer this question. Can we reconstruct wind patterns from thousands or millions of years ago? Yes. And I was able to answer this question simply because I got a grant from the National Science Foundation. So small grant, big impact on my career and ability to do the work that I wanted to do. Okay, another project that I was involved in graduate school asked this question: can changes in polar climate affect the tropics? This was a super hot topic in the early aughts. Truthfully, I can't even remember why. So many other hot topics have come and gone in the climate space, but this was a big one. And there really, again, wasn't anyone at my institution who was running the kinds of climate models that I needed to try to answer this question. And so I had the great fortune of being able to go down to the Geophysical Fluid Dynamics Laboratory, which is part of NOAA. It's located in Princeton, New Jersey, right off of Highway 1, an unassuming building with tons and tons of brilliant climate modelers housed within it. This is actually one of the birthplaces of climate modeling in the United States. And they had run some climate model experiments, and they didn't have any graduate students to analyze the data. So it was like a match made in heaven, right? I was eager for the data. They were eager for someone to analyze it. And so I spent a lot of time learning actually how to code and how to analyze climate data because of the graciousness of the scientists at GFDL. This, just to bring home the fact that this was a birthplace of climate modeling, in 1980, Suki Manabe and Ron Stauffer out of GFDL published the results of one of the very first climate models. And they did these awesome experiments where they had a very simple model of the climate, and they increased the amount of CO2 in the atmosphere 4 times and looked at things like how mean water temperature around the world would increase, and were able to show the impact of increased CO2 on a lot of different global climate parameters. I was working with a much newer model that they had, but one that was super powerful at the time. So just to give you a sense of what these models look like, these are maps that show on the top observations of wintertime or December, January, February precipitation or rainfall. And on the bottom, observed June, July, August precipitation. And you can see this band along the tropics, this green stripe. Oh, I guess I can use my mouse and show you actually. There we go. This is called the ITCZ, or the Intertropical Convergence Zone, and it moves north and south depending on the season. And we can actually reconstruct this ITCZ with our climate models. Now, remember, this was a climate model that was built, this is 25 years ago. So models have come a long way even since then. But you can see the ITCZ in this model. This was the GFDL model that I was looking at. So these again, just winter and summertime precipitation. So it was super exciting as a graduate student to get my hands on all this GFDL data. And what we did with this model is we asked the question, if you melt a bunch of Greenland ice and create a patch of low salinity or relatively fresh water in the ocean, that's that blue patch up near Greenland in this map right here, what happens in the tropics? And the answer that we found was that the tropical Atlantic region gets warmer. So this is the anomaly, or the change in the sea surface temperature. And here's the change in the air temperature. And this was interesting because there were times in Earth's past when there were these pulses of meltwater to the North Atlantic that slowed down ocean circulation. But understanding the impact of that change in circulation on the rest of the planet was a really open question. And so we were able to show with this modeling study that when you melt water, freshen up the North Atlantic, slow down that circulation in the ocean, you actually can get warming in certain parts of the planet. And some of you may know that this is actually a pretty hot topic right now in climate science, because there are some studies that suggest that this is starting to happen. And so it's been really interesting to watch that play out now with this hindsight from what I learned from being able to be at GFDL 25 years ago. So again, can changes in polar climates affect the tropics? Yes. And we know that thanks to the models that have been run at NOAA's Geophysical Fluid Dynamics Laboratory. This is a place that is under direct threat with federal cuts to science right now. After graduate school, I moved on to start looking at present day climate science and climate impacts. So to highlight a few of the questions that I've been working on over the last 10 or 15 years, the first was, when and where will US communities be chronically flooded from sea level rise? And this chronically flooded is kind of a different and new way to look at things. So as global warming progresses, we know that the sea level globally, on average, will rise, and more coastal communities will become inundated, right? They'll be permanently underwater. But long before they're permanently underwater, they're going to see much more frequent flooding at high tides. And it's this that we called chronic flooding or chronic inundation. So you may still have some dry days, but if you're seeing 10, 20, 50 floods per year, essentially that part of your community is unusable. So just a little schematic of what this chronic inundation and sea level rise look like. Top portion shows conditions today with sea level high tide line being here in the dark band. And the extra high tides, these are like king tides. They might happen once a month or a few times a year, being in this light blue band. And you can see today, these extra high tides and high tides, they're rarely flooding coastal communities. But with future sea level rise, we're raising the level of the high tide. And by default, then we're raising the level of those extra high tides. And so more and more, these extra high tides are going to start impinging on our communities. And we defined chronic inundation as flooding that happens 26 times or more per year, because that works out to about every other week. And don't know about you, but if my backyard was flooded every other week, it would probably not be a great place for my kids and then their neighborhood friends to play. So to map this chronic inundation across the United States communities, we used a bunch of publicly available data from NOAA. So first off, we used tide gauge records to understand when and how these extra high tides happen. We used digital elevation models from NOAA that tell us the height of the land at every point along the coast. It's incredible. It's like, I think the models that we used have an elevation measurement on average about every 10 feet, right? We're talking thousands of miles of coastline. And NOAA makes these publicly available. They've done a bunch of work to clean them up and condition them so that they're ready for sea level rise research. It's amazing. And then we applied a set of sea level rise projections to these tide gauge records and to these elevation models to see what would be inundated in the future. And once again, NOAA was critical here. So we used a set of sea level rise projections that were developed at NOAA and in conjunction with other federal agencies as part of the National Climate Assessment, which, like, don't even get me started about the National Climate Assessment and the importance of that. But that is a huge federal cross-agency effort, congressionally mandated, that is also under threat right now. So here are the kinds of maps that we were able to generate with all of this amazing NOAA data. This is a map of Miami Beach in the year 2060 under a medium sea level rise projection. All of these dark blue areas are areas that would be flooding 26 times per year or more, right? Huge areas of a very densely populated place. Here's the same sort of map looking at the Tampa, St. Petersburg area. So you can see, again, huge swaths of our coast are at risk of this chronic inundation. So just to recap here, this work would not have been possible without the federal free data sets that NOAA provides to researchers and to the public. The story that I've most been working on over the last couple of years or the question I've mostly been working on is this one. Can we tell stories about climate change's influence on daily weather? And this is a big part of my work as the VP for Science at Climate Central. And I do want to note that this work was well underway before I moved over to Climate Central 6 or 7 months ago. And so the things that I'm going to show you aren't directly my research, but the people on my team are actively working and building these sorts of things. And so I want to give full credit where credit is due to my amazing team at Climate Central for this. This work relies on attribution science. Now, attribution science quantifies the role human-caused climate change is playing in changing environmental hazards and their consequences. This is a field of science that has just blossomed over the last 15 years or so. So that whereas we used to have to say as scientists that, oh, no one heat wave was caused by climate change, we can now actually say, yes, this heat wave was made more likely or made more severe by climate change. And what we're doing at Climate Central, and this may look familiar because I think John Morales, just before my talk, may have shown some similar things. We've developed a climate shift index, which is a global temperature map that updates daily and shows you how much more or less likely temperatures are because of climate change wherever you are on the planet. This climate shift index goes from a -5, so showing climate change made things 5 times less likely, to a +5. Climate change made those temperatures 5 times more likely. And you can flick through dates, so you can look at today, you can look up to a week or so in the future, you can go back in the past and look at, your birthday or whatever day it was hot outside unexpectedly. This data, like I said, we break into 5 different categories on the positive end, so that when a place has a climate shift index of 5, we can say climate change is having an exceptional influence on conditions today. Those conditions were made 5 times more likely, but we also report every degree. We're not simply reporting where climate change has made things exceptionally much hotter. We also report places where we say we can't really detect the influence of climate change. Maybe that day is hot, but it would have been hot even without climate change. You can zoom in with our tools and look at your specific area, specific days. You can download screenshots. We get a lot of TV meteorologists using this kind of information. And this information would not be available without NOAA's Global Forecast System model. So this is an amazing weather forecasting data set that is publicly available. And it's what lets us look at conditions today and going ahead a few days into the future. And that's because we have good data sets on what temperature was like a week ago or 2 weeks ago or a year ago. But those data sets are preliminary until they're inspected and cleaned up and released in a final format. And so there's a bit of a delay. If you want to know officially what the temperature is today, there's no real clear way to do that. We have good data for the past, we have projections for the future. And so what we do is we rely on this GFS model to look at today's temperatures, and then we have a complicated system of updating it when the data is made final. We also do this for sea surface temperatures now. So this is a map of our Climate Shift Index Ocean tool, which shows how much more or less likely sea surface temperatures are because of climate change. So similar to our air temperature map, but for the ocean. And here, this is drawing directly from NOAA's OISST data set. So optimum interpolation sea surface temperature data. Again, free stream of data to researchers. This OISST data lets us look at the strength of hurricanes. So this is a map showing the path of Hurricane Milton last October. And we were able to say and to see that Hurricane Milton passed over sea surface temperatures that were at least 200 times more likely to be those high temperatures than they would be without climate change. This year, we are rolling out hurricane intensity attribution so that you won't be able to you'll be able to see, yes, sea surface temperatures probably strengthen this hurricane. We will also be able to tell you by how much. And so we'll come back to Climate Central's tools when you see your first hurricane of the season, and you'll see these gorgeous landing pages for every storm that will lay those data out. So we are getting those hurricane storm tracks from the National Hurricane Center, a part of NOAA. So I hope this has given you a sense of, over the 25 years of my climate research career, it has really been brought to me by the National Science Foundation, the Geophysical Fluid Dynamics Laboratory, by tide gauge data, by digital elevation models, by the Global Forecast System, by the OISST data set for sea surface temperature, the National Hurricane Center. And this is just a sampling. There's all kinds of federal data that's at risk, not just for weather and climate, but for things like public health, reporting on heat-related emergency department visits, reporting on rates of heat-related illness in our communities. All this data is at risk. So with that, I will wrap up. Thank you for tuning in to this part of the Weather and Climate live stream. I'm hoping we have some time for questions, but in hoping that you take a moment to make some calls to your elected officials to tell them how important this information is. Thanks.
Thank you, Christy. Thank you for taking us along your professional journey and doing such an excellent job of showing us how federal funding and federal facilities and the products produced by them were just key, seemingly every step of the way. I myself am a federal research scientist at the GFDL, so I was delighted to see the role that GFDL played in your own work. And I'm curious, just on a personal note, who you collaborated with when you were there.
Yeah, so I actually got to work with Ron Stauffer of the paper, the famous Minabe and Stauffer 1980 paper. And I worked with Tony Broccoli, who is now at Rutgers University. But Tony was, it was an amazing experience. I would go down from Woods Hole and he would get out a notepad and he would write in his beautiful handwriting sort of all the Unix commands that I would need to access all their data. And Tony basically on paper taught me to program. It was amazing.
Yeah, incredible. And both of those guys that you mentioned, just legends at GFDL who, we still talk about a lot. And also great to learn more about sediment cores. And I think your early work on paleowind kind of blew people's mind. There were a lot of people in the chat that just, had the emoji of the top coming off their heads and paleowind, can you believe it? So just, that's an amazing, this live stream has been full of amazing science tidbits, and that was, yet another one.
Awesome.
And, and we've heard in previous talks about ice cores, we heard just earlier from Kim Cobb about corals. And again, looking at the layers and those things like the layers in the tree rings to probe the past. And we've got some questions on that in the chat, which we'll come to. So anyway, awesome to just have the sediment cores as yet another example of a layered proxy through which we do that. So maybe let's come to a couple of those questions now. So there's a couple related to the cores. So here's one. In mud samples, how do you delineate one year to the next?
Yeah, this is a great question. It's really challenging. So there are some places on the planet. One that comes to mind is the northern coast of Venezuela, where there's a lot of sediment that gets deposited every year. So you might get a layer of sediment like this big in 1 year, but there are more places in the world where you're getting just a teeny tiny, like a millimeter per year of sediment building up. And so it's very difficult in most places to go year by year like you would in a tree ring, for example. And so we would generally rely on things like carbon dating. So you'll look at the fossils in a sediment core and use carbon dating to see how old they are. And then use that to try to understand, okay, if this fossil in the mud is 10,000 years old, okay, this sample I'm going to say is 10,000, probably plus or minus 100 years, right? So it's pretty rare to find a place where you can go year by year in a sediment core, but a few of them do exist around the planet.
Gotcha. So a bit different than the tree rings. And then a kind of similar one, which maybe you spoke to a little bit, what kind of resolution do you get with these mud cores? And you can mention that maybe there's a lot of variability, but is there sort of a typical kind of resolution that you might find or that you worked with specifically in your work? Yeah,
I'm gonna have to confess this was 20 years ago, so I can't give you a good number there, but yeah, I mean, it is rare to get something that you can see like annual bands in. So, generally the dates we're working with are like plus or minus 100 or even 1,000 years in some cases. But some cool work you can do with mud cores, like you can actually see like paleo hurricanes in coastal environments, and you can see like if there was a big, like a glacial lake that burst, you can see all the sediment that gets deposited from that. Some of the coring work that I did in graduate school in Indonesia, we'd bring the cores up and you could see layers of ash from volcanic eruptions that happened hundreds of years ago. So sometimes you get these nice like markers in the sediment that you're like, okay, that must have been the 1860 eruption of whatever volcano.
Very cool. We have a sort of basic climate dynamics question here that I think arose from you showing the precip patterns in the ITCZ. I think this is a kind of a profound question that many have tried to answer, but maybe I'll pose it to you and just see how you would put it. Why does the ITCZ hover north of the equator? So many have tried to answer this simple question.
Yeah, this is a really challenging question. And I would say what has captivated me even more is like just the seasonal migration of the ITCZ, which happens because the winds in the northern hemisphere versus the southern, compared to the southern hemisphere, vary in strength. And so that's why you get this kind of north-south movement of the ITCZ over time. I've always kind of suspected, but don't have a great theory about it, that the ITCZ has hovered north because there's a lot more land in the northern hemisphere. So I don't know if there's good research to back that up. Not something I've looked into lately, but would be an interesting question to look into.
Cool. Thank you.
I don't know. Maybe someone in the chat knows. Maybe you know as a moderator.
And I think then with respect to the sea level work that you talked about, there's kind of a general question in terms of the impacts. With respect to that sea level rise that you were showing, how many millions of Americans will be impacted? Obviously, that's a pretty general question, but maybe you can focus that a little bit with respect to the work that Climate Central is doing.
Yeah, it's millions. So I've done some work, and so has Climate Central, looking at how many people live in areas that are at risk from sea level rise. I am trying to remember the stats from some of our stuff, but I honestly can't give you a perfect number. But I can follow up in the chat later with some stats. But if you go to some of the sea level rise tools at Climate Central, try checking out Climate Central's Coastal Risk Finder. And you can explore how many people in different communities are affected. But something that's interesting about coastal communities is that as a nation, we are very highly concentrated along our coasts. Something like 1 in 5 people in the US, something like that, lives in a coastal community. And so even if someone's home isn't directly impacted by sea level rise, the loss of land within a community, the loss of roads, the loss of a school, the loss of a hospital has these ripple effects throughout a community. So when I think of how many millions of Americans will be impacted, yeah, there's like, okay, the people immediately impacted, but then there's this whole like outer tier of people that realistically we all fall into who will be affected by this.
Yeah, so concentric circles of impactedness.
Yeah.
And I think you spoke to this a bit, but maybe you can elaborate. How will your efforts at Climate Central be impacted by the cuts? So you talked a lot about the various data sets that you used. Are those the primary ways? Are there other ways that the cuts are being talked about might impact your work?
Yeah, so Climate Central we don't have any federal funding. Our funding comes from private donors and foundations. So thankfully we're not at risk there, but we are really reliant on these federal data sets. And so we, interestingly, for our sea surface temperature work, we had a preview of what it would be like to be without that NOAA temperature data set. Because when Hurricane Helene happened last year and affected Asheville, North Carolina, that's where NCEI is based. And that's like the data warehouse of NOAA. And there were several days, maybe in a couple of weeks, when the sea surface temperature data wasn't coming out. Still out there getting collected, but there wasn't any reporting. And so all of a sudden, this brand new sea surface temperature tool we had just launched was like devoid of data. And so we quickly scrambled and found a different global sea surface temperature data set from the UK that our programmers somehow amazingly were able to slot into our systems. So we now have that for sea surface temperature as a backup system if and when we have outages in the NOAA data. Similarly, for our temperature data for the global forecast system, there are other European models that we could potentially be relying on, but it would require rebuilding a bunch of our systems to try to incorporate those.
So that kind of fits with the theme we've been hearing throughout the live stream, that there had to be sort of pivots, perhaps more rapid than we would like, and other countries and other data producers would really have to step up.
Yeah, I will say though, like as we will be launching these hurricane attribution tools this summer, and that data from the National Hurricane Center I do worry about, because groups like the hurricane hunters, these like crazy people who fly planes into hurricanes, that data then gets put into the forecast for where a hurricane is going to be and how strong it's going to be. And so there's no other program I know of that's like that, that's gathering that data and feeding it back into the predicted track and intensity of a hurricane. And it's the kind of data that like you just can't get any other way.
Yeah, and we heard a bit about that from John Morales, who mentioned that, the uniqueness of the hurricane hunters. And we heard from a real-life hurricane hunter last night, Jeff Masters, who told us his harrowing tale of flying into Hurricane Hugo. And for folks who didn't get to hear that, I think all of us organizers and moderators were on the edge of our seats, backstage and in the audience. And so you can find the link on our YouTube channel for those interested. Christy, I think that's all the time we have for your segment. Thank you so much for participating and sharing your journey with us.
Yeah, thanks so much for tuning in, everybody. Take care.
Great. So we are still in the middle of prime time, and a couple more great presentations in this block. But again, this is just a time to step back and remind ourselves why we're here. We're in our 81st hour of a 100-hour weather and climate live stream, featuring talks from hundreds of scientists, weather and climate scientists, articulating what they do and the value of it to the public, getting together to do this. And as a federal scientist and as a federal employee, I can't encourage folks to take particular actions, but the other hosts have, and they will in the future. And there's resources that you can find at our website, wclivestream.com. And so with that, I'd like to welcome our next guest, Daniel Swain. And Daniel Swain, you may know of him through his online presence via Weather West, an effort via several platforms to answer questions and educate the public about weather events, particularly those impacting the American West. And Daniel, if I'm remembering correctly, about 10 years ago when I was a graduate student at UC Berkeley, on the West Coast, we experienced this ridiculously resilient ridge. And I think I remember you covering that. Is that right?
You remember correctly. That was actually one of the persistent multi-year ridge in California, and the historically severe drought that it produced were the subject of a good chunk of my PhD work, and ultimately were sort of a catalyst for some of the weather and climate communication that I do today via Weather West and otherwise.
I remember that. And you were a graduate student at the time, is that right?
I was, yes. This was sort of a 2013, 2014 era. I was a PhD student at Stanford at the time, and Noah Diffenbaugh's group there. Yes. And made a conscious decision in coordination with my PhD advisor at the time to sort of tackle some scientific questions that were sort of timely and relevant in the news. And that sort of what was sort of the first experience I had really directly doing science that was motivated in part by the questions that people were asking in the wider world outside of just science, but then using, of course, scientific methods to quantify the answers.
Yeah, fantastic. So at the same time, I was an atmospheric science PhD student at UC Berkeley, living through this event like the rest of California and the Bay Area, and we all had so many questions. And at a certain point, in our group meetings, we started to hear about this grad student at Stanford who was, putting all this stuff up on the web, doing this great analysis, and answering people's questions. So anyway, it's great to kind of reconnect with you here and see you, continue along this journey.
Yes, and thank you for being a host, and thanks everybody for joining scientists talking about weather and climate and science policy on a Saturday night. This really has been a pretty remarkable event. I've been watching as much of it as I can, a significant portion of it, in fact, so far, and it has genuinely been an incredible sequence, both from a true science perspective and from the perspective of scientists really doing a good job reaching outside of their niche and outside of the academic bubble. So I actually think this has overall been already a really good example of scientists doing a good job doing the kinds of things that I try and do in addition to my own research in engaging the public, which is part of my official role now with University of California Agriculture and Natural Resources. So I'm grateful to have that role and to be here this evening.
Excellent. So I think the time we're going to have with you is going to be a little bit different, and it's going to be kind of an Ask Me Anything format. And so here we're really, folks watching and with your fingertips on the keyboard, now's the time to light up the chat with your questions for Daniel. We refer to this ridiculously resilient ridge. Anyone who remembers that, or even for folks who are just wondering what that is, you could ask about that. And Daniel, while folks are getting their questions ready, maybe you have a few things you'd like to say to kind of get the conversation going.
Yeah. For those, some may already know me from my not so pseudonymous online Weather West persona or otherwise, but I am a weather and a climate scientist. So unlike many folks who have spoken so far this week who have a background in weather or climate, we've heard from both meteorologists and weather scientists and climate scientists, and some folks like myself who span that gap. I really do think about climate change as a climate scientist today, very much looking back to my meteorology roots. So I think about climate change in the context of weather in aggregate, if you will. And a lot of what I study are the extremes of weather as they relate to climate or not, as the case may be, and how they are changing in a warming world. So thinking about climate change through the lens specifically of extreme weather, so storms and floods and droughts and things like that, and also weather adjacent extremes and hazards, you could call them, like wildfire, for example, and extreme wildfire weather, which has become a particularly hot topic, literally and figuratively in recent years. So today, this evening, my hope is to encourage folks to ask truly anything that they are interested in hearing about in terms of weather or climate change, and how the two are related, as well as things like wildfire and related hazards. And I just wanted to, before we start answering some of those questions that I can already see are coming in, point out a couple of things. One is that I do not proclaim to be the world expert in any of the specific topics that may or may not arise tonight. It's quite likely that someone on this live stream was in fact the world expert on the specific subtopics. But part of my role and my job is to synthesize and to draw upon, in many cases, quite directly, the work of the people who have so far appeared on this live stream. So I want to emphasize just how collaborative science is in general, but also how close-knit the weather and the climate communities are. I mean, I either personally know or have recognized the work of and have read many papers of literally everybody. I mean, of the hundreds of people who have been here, that's the community. And it's been kind of amazing to see everybody actually appear in a single event. I don't think that's ever happened before, to my knowledge. But just to point out, I'm going to try and answer as broad a range of questions as possible. I may or may not be able to answer some of the ones that come through. I'm probably not the world expert in all of the answers, but part of my role is learning the answers that have been come to through decades of research, as the case may be, through weather and climate modeling, through observational science, through theory, much of which has been conducted literally by the people you've seen on this live stream so far. And I would also add, and I think part of the value of having these conversations, as I am, as we're having here, as I'm having in this Ask Me Anything session now, and as I do in general, is to just point out that that the scientists are people too, and that may sound obvious to some of the audience, but I actually, we often hear these public opinion surveys where many people today cannot name a living scientist, any scientist at all. Even though some of the meteorologists they see on the morning news, for example, are scientists, but it doesn't occur to people necessarily. So just pointing out that, sometimes it's, I try to put myself out there partly to just point out that, when I'm speaking off the cuff, I'm just a regular person too, who happens to know a fair bit about weather and climate, because it's sort of what I've devoted my life and my career to studying and understanding. So with that, I'll quit the monologue and we can probably start taking some questions.
Awesome. And Daniel, I really appreciate you emphasizing that last point, because I think that's a sort of a side benefit or an additional benefit of this program, is just for the public just to see us as human beings, see our faces, get to know us a little bit. And for us, weather and climate scientists, to come up from behind the curtain, so to speak, and just be known to the public. So definitely appreciate that sentiment.
And I would add one more thing briefly, is that I
Please.
am not a federal scientist, and I am happy to answer a range of questions that may or may not relate to the physics or thermodynamics of the atmosphere directly, but perhaps to the current situation in the US as well.
Good, and those questions are coming in the chat, so we'll get to those. So let's see. So maybe we'll start with some. I see a few questions about LA. I'd love to get to those, especially I myself am an LA native. And I think, Daniel, we both spent a lot of time in California. And obviously there's been a lot of extreme weather there in particular, and even just this year. So we should definitely get to that. Maybe we'll start with a general question here, just to kind of set the stage. Is there a difference between the terms extreme weather and natural disaster?
Well, this is a good one. And it's something that I've been schooled in myself a bit by hazard and disaster researchers, actually, which is that even the term natural disaster, I think, has fallen a bit out of favor. And one of the reasons for that is actually been talked about. I don't know if it's been framed this way, but it's actually been talked about by a number of speakers in this live stream so far, which is that certainly there are disasters. We've seen many of them. And we know that disasters, at least from a financial perspective, they're becoming much costlier. Some forms of disasters have fortunately become less deadly over time, but we are certainly seeing greater and greater losses associated with disasters. But the key here is that a natural hazard, so the specific extreme event that we're talking about, the flood, the tornado, the wildfire, whatever it might be, does not a disaster make. And you can sort of go back to the old saying, if a tree falls in the forest and no one's there to see it, did it in fact actually fall? Well, it did fall, but if nobody was there to witness it, we won't know about it because it didn't cause anybody any problems. And the same thing is true of any other natural hazard. If there's a hurricane spinning out there in the open Atlantic Ocean, as long as all the ships stay away, it hasn't harmed anybody. It doesn't cause any damage. It doesn't cause any death. And so it could be a historically intense Category 5+ storm and spinning out there that we call them the fish storms sometimes. And it just makes for a pretty satellite picture. Unfortunately, it doesn't harm anybody. Whereas if that same storm, for example, had approached Miami, or another hurricane vulnerable city in the world, it could have been an utter catastrophe, a disaster, because a disaster is informed both really by three things: the physical hazards, so the storm, whatever the physical event might be, the exposure, essentially what is there. If the hurricane hits an unpopulated stretch of coast, that I guess that's great. If it hits a major city, there's a lot of exposure. There's a lot of buildings, people, infrastructure in the way. And there's the vulnerability. Okay, maybe there are lots of structures, maybe there are lots of people, but maybe it's a very well prepared place. Maybe the buildings are built to a very high design standard. There are lots of good evacuation policies. The evacuation, the drill. There's some damage, but it's not too bad. So the disaster is the product of all of those things: the hazard, the vulnerability, the exposure. And the notion is that only one of these is natural, ostensibly, which is the original hazard itself. And arguably, even the hazard, as we know, in a warming climate, is increasingly being influenced by human activities. So even that is not fully natural. So that's why natural disaster has sort of fallen out in just favor of simply just disasters. And in terms of the extreme weather question, I think I've sort of answered that part already. Extreme weather is one class of natural hazards that go into creating potentially a disaster if the exposure and the vulnerability are also present in that case.
Awesome. Great answer. Maybe we'll turn to California now, and several questions relevant there that I think are also relevant to other parts of the country. We'll start with this. Standard LA will be an air conditioning only kind of life coming soon.
That's an interesting question. So full disclosure, I do not currently live in LA, but I did for a time, and I lived on the west side of LA, not too far from UCLA campus, in a very poorly ventilated bottom floor apartment that did not have any sort of active cooling in it when I moved in. It turned out it ended up being a particularly hot summer, the first summer I was there, and after a lot of literally sleepless nights, like I was just going through the night and not sleeping, I realized I had to do something. And so I installed a window unit in the bedroom with the permission with the landlord. But just by means of a personal anecdote, that everybody in the building, that building included some people who had lived there for 30 or 40 years. So long-time residents in the exact same place, like in the same unit of the same building. And they had been complaining that the last few years, just the number of hot and even humid, it can get kind of humid on the coast side of LA during a heat wave, is just something they had never remembered in their lifetime of living there. And, you hear those anecdotes, right? People's personal experiences, anecdotes, they may or may not be in alignment with the broader data. Sometimes I call them anecdata, but sometimes the anecdata do align with what the statistics show. And this is indeed one of those cases where a greater and greater fraction of the urban megalopolis that is LA, that extends all the way from, the Santa Monica Pier really to the Inland Empire. And there's a strong gradient of temperature already, just there always has been. The Inland Empire is very hot consistently and dry, and then the coast is a lot moister and cooler. You get more fog. But the number of times that you get those heat waves and those warm overnight temperatures has already begun to expand, closer and closer to the coast more and more frequently. And so the thing is, a lot of folks inland, not everybody, and this is a problem, but higher fraction of folks living inland Empire, San Fernando Valley, inland valleys, where it was historically hotter, lived in homes or apartments with air conditioning, either built into them originally or added later. A lot of folks on the west side do not. And so this is becoming a thing where there is an expansion of the need for air conditioning, just to make it through the night in some cases. And actually, today I live in Colorado along the Rocky Mountain Front Range. And the same thing is happening, where this is a place in the world where very few residential structures had air conditioning 50 years ago. And a lot of the structures were built more than 50 years ago. A lot of them are brick buildings. Don't see as many of those in California for earthquake reasons, but they're very well insulated, which is great if you're trying to retain heat, not so great if you're trying to shed heat at night when you're trying to sleep. So all of a sudden now, all the new builds are putting in air conditioning. Anytime anybody does a retrofit, they're adding air conditioning. And there's a reason for this, is that you didn't used to have very many 95 plus degree days. They might happen once or twice in a summer, and then the night would cool off and it would be chilly by midnight and you'd be fine. Just open the windows. But increasingly, there are a lot of 95 to 100 degree days. There are a lot of nights where it doesn't get below 80 degrees, which is pretty warm. So I think we're seeing this. Yes, we're seeing this in LA. We're seeing this in other places too. I think air conditioning only city, it might be pushing it, but the need for air conditioning has certainly grown, affecting more people across a wider footprint for a longer period during the year. And that's also a problem for a lot of the folks who, there's a substantial unhoused population in LA, as there are in a lot of major American cities. And, usually there's little or no access to active cooling for those people, or people who work outdoors in a lot of cases, or even some cases indoors. And like in some of these large shipping warehouses, this has become a really big problem, where lack of air conditioning can be 120 degrees inside of some of these buildings on a heat wave. So it has been a problem historically. It's probably going to be an even larger problem. And, it's something I've personally experienced in realizing that the building I was living in was not designed for the climate of circa 2018 Los Angeles.
Very good. Yeah. And amazing how your lived experience, both in LA and Colorado, manifests these trends. So another question kind of in the same vein, related to the fires. And I suppose, I don't think we could have concluded this podcast without touching on this subject, since it was just earlier this year. Many of us knew people affected by the fires. I certainly did. And there's also a NASA laboratory, the Jet Propulsion Laboratory, located essentially, just about next to the epicenter of one of those fires that had to evacuate. And many of the scientists there were impacted. So a lot of questions we could ask. We could probably talk about this for a little while, but maybe we'll just start with this question from Dessler 2. Did weather contribute to the recent LA fires?
Well, weather certainly did. There's a 100% chance that it did, and in multiple ways. There's a somewhat separate question of whether climate change did, to which the answer I think is yes, but I'll get into that as well because it's a little more complicated. But in terms of weather, there is this notion of fire weather, and in particular extreme fire weather, and it's been around for a long time. And this has been something that was discussed certainly in wildfire management, fire studies circles for decades. But it's really gained, I think, a lot more public recognition, unfortunately, due to a lot of really terrible, catastrophic fire events that have occurred, not just in the US and California, but really around the world the last 20 years, in particular in the last decade. It sort of came to prominence, actually, perhaps maybe even first in Australia, originally, where the public awareness, the various Black Sunday fire events. But in any case, the wildfire is very much affected by ambient environmental conditions. And a major part of ambient environmental conditions is what is the weather doing? Is it hot, dry, and windy? Is it cool and damp? Because obviously, you can imagine in the extremes, if it's exceptionally hot, dry, and windy, you can have exceptional rates of fire spread. You can have increasingly extreme and even exotic fire behavior. So you can have fires that not only literally burn at a higher temperature, not only move faster, in a linear sense across the landscape, not only are more likely to ignite in the first place also, but then start to exhibit self-reinforcing vicious cycle feedbacks to a greater extent the more extreme the ambient environmental conditions. So for those of you who have experienced wildfire in its most extreme form, you may know that very large wildfires can do things like create essentially their own local to moderate scale, medium scale weather conditions through the form of generating fire-like thunderstorm-like clouds, or even literally thunderstorms, clouds, the smoke plumes that start generating their own lightning, and in very extreme cases, even their own tornadic-like vortices. Of course, you can imagine what it's like if a wildfire that's burning intensely is creating its own lightning, sparking new fires, and creating these spinning columns of air that can cause damage in their own right. That's the most extreme example, but the more intense the fire, the more likely it is it does something like that, something kind of wild. And in the case of LA, the fire conditions that we saw leading up to the event, these were actually very well predicted by the National Weather Service. This is something I really want to highlight. The Oxnard office, which serves the LA metro area in Southern California, they issued what's known as a particularly dangerous situation, a PDS red flag warning, which is essentially a meteorological warning that fire conditions will be so extreme that they are on the upper tier of what has ever been observed historically. And if there is a fire in a particularly fortuitous, I guess, or problematic location, it will likely be uncontrollable. The language is literally, wildfires are likely to be uncontrollable, meaning that the weather conditions are expected to be so extreme that even the best prepared wildland firefighting force in the world, which is what California and LA County have, will be unable to stop it while weather conditions persist in that state. That was the prediction that was explicitly made a couple of days before the catastrophic LA fires in January. And the conditions were literally the driest period on record leading up to early January that we've ever seen in Southern California, followed immediately by some of the strongest winds we've seen in January, these strong, dry, in some cases pretty violent downslope windstorm, with wind gusts to 100 miles an hour and pretty widespread gusts over hurricane. Hurricane force gusts can be a bit of a misnomer. In any case, winds of gusts 70, 80, even 100 miles an hour locally. Firestorm conditions. And this was evidenced by some of the footage we ended up seeing from people's Ring doorbell cameras of this blizzard of embers with branches on fire flying past the camera. That's the kind of conditions. That's fire weather, extremely low humidity, extremely strong winds, and to a certain extent, warm temperature. Although honestly, in the short term, it's often the humidity and the winds that matter more. In the longer term, the other environmental condition that matters is how dry is vegetation. And we know that because in the weeks and months leading up to the LA fires, we saw the driest conditions on record. That's starting to get more to a blend of weather and climate, because we're talking about a longer time scale, multiple months, potentially, where it was unusually warm and unusually dry. And then looking even farther back, in Southern California, a lot of what was burning in these fires was grass and brush, often called chaparral in the Southern California environment. But it was not really forest. It wasn't primarily trees, for example. And the reason I bring that up is if you look even farther back, the fact that Southern California had 2 unusually wet winters in a row immediately preceding this event. If you look farther, that's definitely in the realm of climate, since it's a couple years ago. That actually allowed for abundant growth of grass and brush. So unusually abundant vegetation and biomass, potential fuel, if you will, for the fires to come. Then we had the record dry period that dried it out to a greater extent than we had ever seen before in early January. And then we had this really strong downslope windstorm. And to their credit, the Weather Service in Southern California said, "Yikes! That is a scary trifecta. We're going to issue the strongest warning we possibly can." And of course, we know what ended up happening. So that's how weather and short-term climate affected these events, and in general, how it can sort of affect fire. In terms of climate change, what do we not think climate change was involved with? Probably the winds. There's not really any evidence that climate change increased the winds. We don't have a great theory for how the Santa Ana winds may or may not change in a warming climate, but there's certainly no evidence that the climate change has increased the wind magnitude or frequency. Precipitation, we have certainly seen a trend towards later and drier starts to the rainy season in Southern California. There are modest hints that's likely to continue, although there's a lot of uncertainty at regional scale, seasonal scale precipitation in California. So that's a kind of a maybe. But the definite yes appears to be in the exceptional dryness in from fall through early winter. So the combined effect of very thirsty, evaporatively demanding atmosphere. We've heard a lot about the vapor pressure deficit in previous talks. The warm temperatures, and then perhaps the low precipitation, and then perhaps also this 1-2 punch, the sequence from really wet to really dry. So that's how weather contributed, and that's why there is at least a partial contribution by climate change to this event, although we also can't say that climate change caused the event. We can certainly say from an attribution perspective that climate change played a role, and there's various groups still working out exactly what that number looks like, but it's a positive number, I can tell you that much.
Very thorough answer. Thank you. And you mentioned that the stage was sort of set by these wet winters that had happened a couple years prior. And if memory serves, that a lot of these rain events in the prior years were due to atmospheric rivers, which bring a lot of, when there's a wet winter in California, often they are responsible. And so there's a question also from Dessler too, this guy must be an expert or something, about atmospheric rivers and what's going to happen to them. We know that they hit the west coast of the US, but they also hit other parts of the world. And indeed, they've been found to hit Antarctica and bring a lot of moisture and precipitation to Antarctica. So maybe you could remind viewers what they are and answer Dessler 2's question.
Yeah, atmospheric rivers are these narrow bands of highly concentrated atmospheric water vapor transport. Sometimes the meteorologists will say these are similar to or the same as the warm conveyor belt in a mid-latitude or extratropical cyclone. Then others will say, well, they're not quite the same thing, but it's the same general idea. It's a concentrated plume of moist air moving quickly. So really it's the product of wind speed and the amount of moisture in the air above your head in some vertically integrated sense. So water moving quickly in the air above your head in a somewhat concentrated form. Called atmospheric rivers partly because they are very narrow and transient features, and they kind of wind around. Think of what the Mississippi River looks like from an airplane or from space. It's very sinuous and windy. Atmospheric rivers can look like that, quite literally, if you look down on them from space, from an Earth orbiting satellite or something. And they're responsible for a great majority of all of the northward water vapor flux and a fair bit of the moist static energy flux really on Earth. Most of this occurs not sort of in the mean flow, but in these occasional episodic bursts of very strong, I should say poleward, because they do exist in both hemispheres, and it's toward the Arctic in the northern hemisphere and the Antarctic, of course, in the southern hemisphere. And this is one reason why they come into play when you talk about the Arctic and Antarctic, actually, is because they do sometimes, and increasingly actually, make it into the very high latitudes and drop. When they make it into high latitudes, they're usually bringing both very moist air and air that is a lot warmer than usual for the polar regions. So this is the kind of events that can result in a heavy rain event, even on the Greenland ice sheet or on the Antarctic ice sheet. In fact, we've seen some rain events on these ice sheets. And obviously, if it's an ice sheet, in the long run, rain is not the typical form of precipitation you're getting there. And yet, we've seen pretty significant events recently. So they are important for Arctic and Antarctic climate. We actually hear about them more often day to day as they affect places where more people live in the temperate latitudes. And we hear about them a lot in California, but they're actually common in general over ocean basins globally. And when we talk about land, they're most common on the west coasts of mid-latitude continents. And if that sounds a little bit specific, it's because we generally, in the Earth's temperate latitudes, have winds that steer storms from west to east in both hemispheres. And the atmospheric rivers form mainly over ocean basins because that's where their moisture source is. And so where are they going to make landfall? If they're moving from west to east and they form over the oceans, on the eastern edge of the basins generally. And so that's one reason why in these regions, in what are known as Mediterranean climate zones, so we have them in California, we have them in parts of the actual Mediterranean, of course, the southwestern Cape of South Africa, parts of southwestern Australia, Chile, they can be a really critical part of the water supply. So atmospheric rivers in a place like California are both responsible for a majority in many years of all of the beneficial water that falls from the sky in the form of rain and mountain snow and replenishes soils and reservoirs and forests and farmland and all of that. And also for something like 98% of all the big floods. So they're a blessing or a curse, depending on the context, depending how intense they are. In a warming climate, one of the most high confidence things we know about atmospheric rivers is that in a given location, it's a little bit tricky whether we actually see more or fewer of them, much like hurricanes, by the way, where there's actually still sign uncertainty, plus minus, whether the more or fewer hurricanes overall. But also, much like hurricanes, scientists who study them are quite confident that they will intensify. So we may or may not see more or fewer of them, but the ones we do see will be more intense, with stronger water vapor fluxes in the air above your head and more extreme precipitation associated with them, and yes, greater flood risk associated with them. And this is true essentially everywhere on Earth where they occur. Now, where we've seen this effect emerge so far does depend on where we are. In California, it's a little bit unclear. Other regions globally, we've already seen this signal emerge, but we do expect in California and in general atmospheric rivers to intensify, to produce more extreme precipitation, to be associated with greater flood risk, even if we don't see more of them in a particular place, or perhaps even see fewer of them. That would be one potential outcome, is that some places see fewer but more intense atmospheric rivers in a warming world.
Gotcha. Thank you. So maybe we'll zoom out from the West Coast and to the broader U.S. here, and maybe this will be the last weather question. Then we'll move on to kind of policy and the broader situation we find ourselves in today. But this one is: can you list out the top 5 or 10 weather area hotspots you think would have outsized weather impacts in the next handful of years for the broader U.S.? So we've talked a lot about what might happen to California with respect to certain phenomena, but what other places in the U.S. are on your radar for extreme weather?
You know, one tricky part is that we don't have very good predictability of extremes more than sort of on a sub-seasonal predictive scale. So we've actually heard from some folks who are experts in sub-seasonal climate prediction in this live stream so far. There, we're talking about weeks to maybe a month or two in advance. We can kind of squint a little bit and get kind of a signal. When it comes to individual weather extremes, though, beyond that, we really don't have a lot of predictability in sometimes what is called the predictive gray zone. So we have really good weather forecasts, as many folks have talked about, great weather forecasts out 3 and 5 days, decent ones out to a week or so, and then some indication of what's going to happen, sort of tilt in the odds type probabilities, 1, 2, 3, 4 weeks out, and maybe sometimes seasonally. But then when we get a year or two out, we can make some predictions about things like El Nino potentially and La Nina, so these very broad global ocean atmosphere patterns. And on a decadal prediction perspective, we're starting to have some ability to do that. In fact, the WMO and ECMWF just put out a pretty alarming prediction this past week showing that there's a very high likelihood that in the next 5 years, the Earth will once again experience another record warm year. But that's a very fuzzy prediction. It's a global prediction, and it's literally trying to predict global mean temperature, which, as I like to say, is a very useful but not real number. It's a great heuristic. It's a useful number statistically. It's also a number that no human, no tree, no society, city, country on Earth will ever actually experience, because it's a statistic. It's an average. And that average is composed of a lot of diverse data points within it. So with that caveat, that this is not so much a prediction based on how the next few years are going to be different than the last few years, but in general, we do know that the risks associated with coastal flooding, particularly with hurricanes, has gone up a lot along a lot of portions of the eastern seaboard and the Gulf Coast. And that is unfortunately likely to be a pattern that continues. We've seen that wildfire hazards, the hazard truly has gotten worse, as well as the exposure and the vulnerability in many cases, which that's a dangerous trifecta for, as we talked about earlier, disaster risk overall. We're seeing a large increase in wildfire losses and risks, not just in the places where we have come to expect them, in places like LA, where that manifested pretty catastrophically already this year, but also in places where people are less accustomed. And keep in mind that the deadliest wildfire in modern American history still occurred on the island of Maui a couple of years ago on the Hawaiian Islands. And, by the way, to wildfire researchers, that did not come entirely as a surprise. But I think for the folks who live there, for many people watching from afar who may have only visited Hawaii, perhaps, that was shocking. Just this winter, Japan and South Korea both saw their worst wildfires on record. And South Korea experienced a wildfire earlier this winter that burned halfway across the Korean peninsula and caused a lot of death and a lot of destruction for the first time in their recorded history. So, that's an example from outside the US, but it's just an illustration that the wildfire hazard is not always where you necessarily would expect it. It might be where the forest ecologists and the wildfire scientists expect it, but it comes to a surprise for a lot of people who've been living in these places. So wildfire is the other one. And then the last one is, we've been, and this is an interesting topic because we understand it less well in terms of climate change than we do wildfire and hurricane risks, which we know certainly that the upper tail of both hurricane risk and wildfire risk is going to increase as temperatures rise, is the severe convective kind of hazard. So that means really severe thunderstorms, including things like giant hail and tornadoes. And we don't understand those as well as we do other natural hazards in a warming climate, although there is growing evidence that probably the most upper end events in many places will probably become more severe, even if we don't know if they'll happen more frequently. You may sense a pattern in this kind of projection. But even if we just talk about a climate that is not changing and the number of people who live in these hail zones and the tornado risk zones, there's been such a large increase in the population in the regions that are highly vulnerable to giant hail and tornadoes in this country that has emerged as a major hazard, a huge driver of economic losses. And this year already, it's another bad year between the LA fires and a number of deadly and devastating tornado and hail outbreaks. This has been a very costly disaster year already in the US. Although apparently we won't be keeping track of that officially moving forward. So those are three things that I think about. There's some climate change in there. There's some population expansion component in there, which is a good illustration of how the disasters we're seeing are the product of multiple moving parts.
Great. So maybe zooming out a bit, so we have a question here about how to deal with skeptics or people in denial about climate change. And this question has come up, many times, and I think other speakers have spoken to it. But I think your point of view as someone who studies extreme weather might be of particular interest. I think some of us have the impression that extreme weather is one of the phenomena that kind of tends to push people, away from denial and towards some acceptance, since these events are so newsworthy and so striking and often just completely record-breaking. But as someone who studies this in detail, perhaps you could speak to that.
Yeah, I mean, at this point, I'll put it this way. It is important to be specific when we're talking about extreme weather. So I still don't love when we say that extreme weather is getting worse in a warming climate, because it really does depend on what we're talking about. Are blizzards getting worse? Are extreme cold snaps getting worse? No. Are tornadoes getting worse? That's a maybe, but we don't know. Are heat waves getting worse? Yeah. Are extreme fire weather events getting worse? Definitely. Are heavy downpours and associated flash flooding getting worse? Pretty unambiguously at this point. And hurricanes, we have a strong theoretical expectation that the observational data in the real world increasingly matches, which is that they are going to become more intense, even if they don't necessarily become more frequent. So it does depend on the hazard. And the two kinds of extreme weather phenomena that we have the highest confidence in at this point are, as you'd expect, extreme heat waves and also extreme downpours, because you've heard a lot about the Clausius-Clapeyron relation, that 7% per degree centigrade, 3 or 4% per degree Fahrenheit increase in the water vapor holding capacity of the atmosphere. Well, it's pretty hard to not see an increase in the ceiling of how intense your precipitation events can get. Although increasingly, that same increase in the ceiling also is raising the ceiling on how extremely dry it can be and how large that vapor pressure deficit can be. So increasingly now we're like, well, actually extreme aridity and extreme wildfire risk is starting to look like a similar level of high confidence. So when it comes to the most extreme fire weather events, the most extreme heat events, the most extreme downpours, those are the sorts of things we have a lot of confidence in. Things like hurricanes and perhaps sort of an intermediate confidence, severe thunderstorms, tornadoes, kind of low confidence. And there's a few things that are probably becoming less severe and extreme, extreme cold snaps or something. Although it doesn't necessarily mean that they're getting less disruptive, by the way. Just look at what happened in Texas. That appears to have been something that happened despite the long-term warming trend rather than because of climate change. And yet it was an enormous disaster for that part of the country partly because it was such an extreme departure from what we had been experiencing recently. Ended up being every bit as much as cold as we've seen recently. Same thing with the pretty wild Gulf of Mexico snows this past winter. And I think that, so the evidence is there. I mean, the fact in that case, the data are what the data are. And they clearly show an increase in a lot of those kinds of extreme events, although not all of them. In terms of having that conversation with people, I do, this is where I think I have a bit of an advantage as a meteorologist who came into climate science from that side, and whose public audience largely, I think, still follows me for the weather more than the climate. I write the Weather West blog, I run the Weather West YouTube channel, where sometimes I have conversations just like this one, where I'll ask questions live from an audience. But, I talk a lot about the weather, honestly, day to day. And day to day, it's not, climate change is not always a big piece of that. But when climate change is a big piece of it, which is sometimes is, and increasingly is, then I will have that conversation in the context of talking about day-to-day weather. So normalizing climate change as something that is actually integrated into our daily experience is something you can do partly by having those conversations with people about their daily experience. And I think that, sometimes people even take the weather for granted. People don't even think about how the weather is, something that affects them day to day. And I think perhaps that's one of the reasons why we've sort of come to this moment in the United States, where there is this sense that why do we need a National Weather Service? Why do we need NOAA? Why is it so important that these critical public utilities continue to be world leading? They continue to function using tax dollars to return many-fold dollars to the public and private sector from that initial investment. Why is this even important? Why is this even desirable or needed in the first place? And I think part of this comes to the fact that the thing I find very funny is that, talking about the weather is the quintessential small talk, right? It's something you might engage with your taxi driver, somebody who serves you a coffee or something, because it's viewed as this neutral topic. But in this moment, it's something we actually need to be talking about a lot more, I think. And it's also something that is anything but neutral or boring. It is inherently dynamic. That's why many of us are in the field in the first place. But it is also salient to so many societal issues, not the least of which is climate change. Climate change matters largely because it shifts the envelope of weather. There's the meteorologist in me speaking again. And I think all of these reasons are reasons, it's both a tactic for having these conversations, using weather as a point of entry in these conversations for maybe otherwise skeptical audiences, but it also illustrates why it's so important to be having these conversations that we're having during this event and hopefully beyond this event, surrounding why not just day-to-day weather operations are so important, which they are. The National Weather Service is a national treasure. It saves lives. It saves the economy. I don't know how many billions of dollars a year. It's been quantified. It's a lot of billions of dollars per year for the cost of approximately a cup of coffee per taxpayer. But the other side of this is the research that got us there in the first place was also taxpayer funded, and the research that's keeping us there, that's keeping us ahead to the best of our ability of a changing world, is also sponsored by your tax dollars. It's operated by NOAA and by NASA and by research funded by the National Science Foundation for the public benefit for all of us. So I think it's all part and parcel in that same conversation, I think.
Yeah. Wonderful, Daniel. Thank you for ending up there. That's just where I hope this conversation would end up, by zooming out and thinking about the impact of these cuts on weather and climate and how it's all related. And your perspective as a meteorologist who's kind of interfacing with climate, I think is invaluable for this series.
Well,
so with that, I think
for having
time is
me.
up. I thank you so much for being here. Great. And so that's going to bring us to our last keynote for this evening. And again, you are watching the Weather and Climate live stream. 100 hours. We're now at hour 82 of Weather and Climate scientists bringing their science directly to you, the public, who funds their work, to share the excitement of science, the curiosity of science, and the value of science, in the hopes that you will feel that and pass that on. And so next up, we have Zeke Hausfather. He is a man who has worn many hats, studying climate science itself, and in particular temperature data sets, also thinking about energy solutions, policy related to that. He's worked at a number of institutions, including the Breakthrough Institute, Carbon Brief, Berkeley Earth, and currently at Stripe. And Zeke, I just have to tell you that I'm a physicist by training and got into climate science by teeing a course taught by Rich Muller, Physics for Future Presidents, and this was in the early 2010s as he was putting together the Berkeley Earth surface temperature data set. And one of my classmates in Berkeley physics was Robert Rohde, who I'm guessing
yes. Yeah, and to be fair, Robert is the one who actually put together the Berkeley Earth global temperature data set. Rich was a great leader of that project, but as is often the case in academia, it was the postdoc who did all the work, or the PhD student back then.
Yeah, that's right. And I remember Rich acknowledging that and saying that that Robert had cleaned the Herculean stables by getting all that data in order. So anyways, and Zeke has also been a great communicator of climate science on multiple angles through his work at Carbon Brief and articles and papers that he's published. And indeed, he does have a rad name. And with that, we'll turn it over to you, Zeke, to tell us about the last few years and the acceleration of global warming.
Thanks so much. So there's sort of two related debates that have been happening in the broader climate science community over the last year and a half, 2 years or so. One is why 2023, 2024, and now the first 5 months of 2025 have been so anomalously hot, so much warmer than we've seen in previous years. And the second is, and this is a related debate, is there broader evidence that the rate of global warming, which had been fairly linear at about just under 0.2 C per decade since 1970, is that rate accelerating? And if so, why? Neither of these questions is fully answered now. And I should give some caveats before I dive into this, that some of this is, my own research, my own opinions. I'll try to share some of the other views on this as well. But I think there's growing consensus on a few of these points, and I hope to cover them in the talk. So yeah, with that, I'll dive in, and we'll definitely try to leave lots of time at the end for questions.
Great.
Okay. So I'm sure a version of this plot has been shown at least 100 times so far in this live stream. But this is the Berkeley Earth version of the global surface temperature record. It's more or less the same as what NASA, NOAA, Hadley, Copernicus, everyone else gets. And it's worth noting that, both the last 2 years, 2023, and 2024 are quite a bit above any previous point in the instrumental record. And the red line, which is sort of a locally linear regression moving average, shows sort of a notable tick up after 2015 in this data set. And so when we first started getting into record territory, I remember it was the summer of 2023. There was some news coverage of the warmest single day ever recorded in July, which looking back was a rather quaint record. But it really was September of 2023 when a lot of us started being a little shocked. September 2023 was the warmest September on record, not just by a bit, but by a huge amount, by 0.5 degrees centigrade, warmer than any September that had previously occurred. And that was kind of shocking. That's not something we expect to see very often, and certainly not something that we see in climate models. And so that, and then the persistent warmth after that, led to a lot of debate within the community of exactly what was going on here. So here's just a view of the average temperature of the entire planet for every month. You can see August 2023, which is that thin red line there, as well as 2024, which was equally hot, as well as the other months. And this year is the solid black line. We're a little cooler than we were last year for most months, barring January. It seems pretty unlikely at this point that 2025 will be the warmest year on record, but it still is quite close to what we've seen in 2023 and 2024. We can also look at this in terms of temperature anomalies. So this is change in temperature relative to a pre-industrial period, 1850 to 1900 in this particular case. And again, you can see 2023 ticking up, the thin red line there, starting around June, being exceptionally warm, and then 2024 remaining exceptionally warm over the entire period. And then 2025 to date, following a little bit below what we saw last year. There's been a number of different estimates of where 2025 as a whole will end up. The sort of central estimate right now is roughly tying 2023, so as the second warmest year on record, maybe slightly above. But obviously, we only have 5 months of data, so it's a little unclear exactly where it's going to end up at this point, and there's some pretty big uncertainties. But it certainly is going to be one of the top 3 warmest years, barring a giant volcanic eruption next month or something really unprecedented in recent history. And so when we put this together and we look at annual temperatures, we see some hints in the surface temperature record of an acceleration in warming. So this is just showing the linear trend from 1970 to 2008, which, as I mentioned, was roughly at 0.18 C per decade. And then if we look at the last 15 years, we see approximately twice that rate of warming. Now, we shouldn't overinterpret short-term trends too much. And this is sort of just at the threshold of sort of 95% confidence interval statistical significance difference in trends, because over a shorter period, you have bigger error bars in trends. If you try to remove the effects of short-term variability, like El Nino, La Nina, it becomes highly significant. That being said, removing short-term variability from the temperature record is more of an art than a science, in that there's not a single best way to do it. And so there's been a couple papers published on that so far, including a recent preprint by Stefan Rahmstorf and Grant Foster that argue for much more significant acceleration using that approach. But there's some conflicting views in the community about how cleanly one can really remove El Nino and other short-term influences. So if we only had this data, if we only had the surface temperature record, the debate around acceleration would be a little ambiguous. Certainly growing evidence, but not crystal clear yet that there is necessarily an acceleration. However, we don't just have surface temperatures. We can measure other things. So we can measure what's happening in the oceans. So the bottom left chart is ocean heat content, which has shown an acceleration, particularly in the IEP record in the last decade. We have Earth's energy imbalance, which is in the bottom right, which has shown a pretty clear acceleration. And we have model simulations that are fed by the most recent forcings data. So there's a new paper that'll be coming out in a month or two. We have a preprint released in the SSD by Piers Forster and colleagues. And in it, we argue that the rate of human-induced warming over the last decade is now about 0.27 C per decade, which is a full 50% increase relative to what we saw in previous decades. And so that's pretty significant. And so the fact that we don't just have surface temperatures, we have all of these different lines of evidence that suggest an increase in the rate of warming, is strong evidence, in my view, that there is a real acceleration that we've seen in recent years. That being said, just because there's an acceleration doesn't necessarily mean it's not something that climate scientists more broadly expected. You know, we have been running climate models since the early 70s, and these days our climate models include a lot of different factors, some of which, as I'll discuss later in this presentation, have been contributing to this recent acceleration in warming. And so if we look at the amount of warming that our models project, most of them have some near-term acceleration, varying amounts depending on the simulation. So in the upper left here, we just have observations, and this is an average of 5 different groups: Berkeley Earth, GISTEP, NOAA, HAD-CREW, and ERA5 that's used by the World Meteorological Organization. And if we extend the linear trend since 1970, you get that red dashed line. So that's sort of the historical rate of warming that's a little below 0.2 C per decade. The upper right is the sort of best estimate of future warming in the IPCC report, the most recent AIR6, or 6th assessment report, in a scenario that's roughly analogous to current policies, the SSP2 4.5 scenario that ends up a little bit below 3C warming by the end of the century. And so in that scenario, there's about a 25% increase in the rate of warming in the IPCC projections compared to what we've seen historically since 1970. If we look at the latest generation of climate models, the CMIP6 ensemble, there's actually closer to a 50% increase in the rate of warming, slightly below 45 or so percent increase in the rate of warming in CMIP6 models in the future compared to historical observed rate of warming since 1970. Now, I and a few other scientists have argued that some of these CMIP6 models might be running a little too hot, which is why one of the reasons why the IPCC's estimate is a little lower than the sort of average across all the latest climate models. And you know, folks who are interested in that can find more details in a piece in Nature that we put out 2 years ago now on sort of the hot model problem. And then finally, there was a paper that got a lot of attention 2 years ago by Dr. James Hansen. And he and colleagues argued that we'd see a roughly 50% increase in the rate of warming, which is shown by that shaded area in the bottom right. And so generally speaking, no one really expects the historical rate of warming since 1970 to continue unchanged. And so the fact that we have seen an apparent speed of warming doesn't necessarily mean it's worse than we thought. It doesn't necessarily mean that we're outside the range of what our models expect. And so it's important to keep that in mind. So why has warming apparently accelerated over the last 15 years or so compared to the rate we've seen since 1970? Well, we talk a lot about carbon dioxide and its role in climate change, and I'm sure you've been hearing much about that over the last few days. But it's important to emphasize that CO2 is the main driver of warming, but not the only one. There's a lot of different factors that come together to result in the observed temperatures that we've seen for the surface of the planet. And so this graph, based on some work that Chris Smith did, tries to sort of disaggregate all the different drivers of recent warming. So the black line there is observed temperatures. The sort of yellow line and shaded area is the 5th and 95th percent confidence interval if you run a simulation, in this case using the FAIR climate model with all the forcings. And then all the other lines are sort of a breakdown of what if we just had greenhouse gases and nothing else? What if we just had natural factors like solar cycle changes and volcanic eruptions? What if we just had other anthropogenic changes like changes in surface albedo or tropospheric ozone emissions? And what I would point out here is that the rate of warming, or the contribution of greenhouse gases to warming, has been steadily increasing. And actually, it's a bit higher than what we'd expect to see based on observations. And the reason for that is what's happening at the bottom of this graph. The blue area there labeled aerosols is not spray cans. The climate scientists love the term aerosols. It confuses, in my experience, everyone else, because what we refer to as aerosols is not what the general public often does. But here we mean little particles that are suspended in the air. And this is primarily sulfur dioxide. That's the big one here. Black carbon, organic carbon, ammonia. There's a few other things that have small effects, but this is 90% plus of this effect is coming from sulfur dioxide. And the effect of this is to actually pretty strongly cool the planet if we were just emitting aerosols and nothing else. And so effectively what this means is that our aerosol emissions have been masking some of the warming that we would have otherwise experienced from our emissions of greenhouse gases. And the amount of warming that's been masked is highly uncertain. Our best estimate, and this is similar to the IPCC best estimate, is around 0.5 degrees C of warming has been masked by our emissions of sulfur dioxide and other aerosols. But the range could be as little as 0.2 C or as big as 1.1 C. And this magnitude of aerosol cooling is itself related to some of the big questions like climate sensitivity that climate scientists struggle with. So this is a fairly complicated graph, but this is essentially taking the previous graph that I just showed you and saying, what is driving the rate of warming in each decade based on these simulations? And if we do that, if we see, essentially take the derivative of this and say on a decadal timescale, say what is driving decadal warming, we get this figure. And so what's happening here is that the orange is CO2. So the rate of warming from CO2 has been increasing over time, which makes sense because our emissions of CO2 have been increasing over time, except for the last decade or so where it's roughly plateaued, which corresponds to a period where CO2 emissions have plateaued. Now, the rate of warming plateauing means the world is still warming, just at a linear rate. It's not necessarily accelerating. Similarly, methane, the rate of warming for methane declined a bit leading up into the 2000s, has increased a bit in recent years as methane emissions have ticked back up. And then the purple area here is actually an interesting one. So there's other greenhouse gases besides CO2 and methane, particularly halocarbons, so chlorofluorocarbons, HFCs. Many of these were restricted in the Montreal Protocol in the 1980s because they were causing damage to the ozone layer. And so we actually see a decrease in the rate of warming associated with other greenhouse gases, which is primarily halocarbons. And the net effect of this, if you add together CO2, CH4, and other greenhouse gases, is to have a roughly flat rate of warming since the early 1980s or so, late 1970s, on a decadal basis, of a little below 0.2 C per decade. So again, about 0.18 C per decade, which is roughly what we've seen in the observations. Other anthropogenic hasn't changed that much. The big interesting thing that we see in this graph, however, is aerosols. So in the early part of the century, aerosols reduced the overall rate of warming because aerosol emissions were increasing. Over the last decade, really, the last 15 years or so, we've seen a big switch as the amount of aerosols we're emitting, the amount of sulfur dioxide in particular we're emitting, has declined. And so that's led to a faster rate of warming because some of the warming from previous emissions of CO2 and other greenhouse gases that was being masked by aerosols is no longer being masked. So aerosols cause cooling, but they're causing less cooling, which means the rate of warming is increasing. And so at least in this simulation, pretty much all the increase in the rate of warming over the last 15 years is attributable to reductions in aerosol emissions. Here's just another way to look at that same data zoomed in over the last decade. So if we look at 2015 temperature in this model, and again, this is looking at the human or the sort of modeled long-term average temperature, not the temperature for that individual year. So this would exclude things like El Nino, short-term variability. We see that 2015 was about 1.1 C. There's about 0.14 C warming over that decade from CO2 emissions, about 0.08 C warming, so 0.08 of a degree C warming from unmasking of aerosol cooling due to declining aerosol emissions. And then other greenhouse gases and natural factors had fairly small influences. So in this particular decade, about half of the warming, or sorry, a third of the warming the world experienced was associated with aerosol unmasking. So we can also zoom in on that particular line of how aerosols have changed over time. And we see that until the 2000s or so, there was an increase in cooling associated with aerosols. And it's really after 2007, 2008 that we saw a decrease in cooling from aerosols associated with declines in emissions. Now, aerosols have multiple different effects on the climate. There's a direct effect where aerosols can either scatter incoming sunlight, particles like sulfur dioxide, for example, are quite reflective, or they can absorb incoming sunlight in the case of black carbon. That's the smaller line here. So the cooling from aerosol direct effects is relatively modest. It's probably only a bit more than 1/10 of a degree C. Where we really see the big effects from aerosols and the big uncertainties in aerosols and models is in the indirect effects. And this is primarily the effect of aerosols on cloud formation, because it turns out that it's hard to form clouds if you don't have little particles in the atmosphere. And if you add more particles, you can get higher amounts of cloud cover, which themselves are reflective in the low atmosphere where these aerosols are concentrated. And so by increasing cloud cover, you reflect more light back to space and have a cooling influence. And so this is sort of a breakdown of how aerosol direct and indirect effects have changed over time and how that's affected the climate. Now, as I mentioned earlier, most of the aerosol forcing is coming from sulfur dioxide. And sorry, the sun is chasing me through the window as it sets. And sulfur dioxide emissions are approximately 90% of the aerosol cooling worldwide, and they've changed a fair bit in recent decades. You can see that they really peaked globally in the late 1970s and then declined modestly through 2010 or so. And a lot of that decline was due to really big drops in the US, which is this light blue area, and the EU and UK, associated with things like the Clean Air Act, the installation of scrubbers and coal-fired power plants because of concerns around acid rain, and other actions to reduce solar emissions. At the same time, Chinese sulfur dioxide emissions were increasing dramatically up through the early 2000s as China added a massive amount of coal capacity and steel mills, iron mills, other industrial activities that released sulfur dioxide. Now, what's been interesting over the last 15 years, and I think this has been a little underappreciated by folks, is just how dramatic a decline there's been in Chinese air pollution. Sulfur dioxide is one of the main precursors to PM 2.5, so it's also one of the things that's most responsible for the horrific, gray soup air quality that used to be present frequently over many Chinese cities. But since 2007 or so, China's cut their sulfur dioxide emissions by approximately 70%, which is a pretty massive decline in 15 years. And so that itself has had a big effect on overall global aerosol cooling, and I'll get into that in a little bit. The other interesting thing that's happened in recent years is in the sort of black area down here at the bottom, which is emissions from shipping and aviation. There's actually not that much sulfur emissions from aviation, so this is mostly shipping. Shipping has historically used fairly high sulfur fuels because they're far enough from shore that the health impacts are smaller. But starting in 2020, the International Maritime Organization introduced some new rules requiring a reduction of approximately 80% in the sulfur content of marine fuels, primarily focused on reducing air pollution impacts in coastal areas and in ports. And they estimated that that regulation would save on the order of 200,000, or sorry, I think 60,000 to 200,000 lives per year. So a pretty substantial impact in terms of public health. But that caused a pretty big drop in sulfur emissions in 2020 specifically. That's persisted since then. It actually ends up being closer to a 60% drop than an 80% drop in shipping, but it's still pretty significant. Here's just another version of that graph breaking down what's happened in China in red, in shipping in dark blue, and then for all the rest of global emissions around the world, which is in light blue. And so overall, global emissions outside of China and shipping fell pretty dramatically from the 70s through the early 2000s or 2010s. But since 2010, the really big drops have happened in China and in international shipping. So let's talk about the shipping side first. There's been a number of different studies published in the last 2 years on the effects of these new regulations, the low sulfur fuel regulations on the global climate. The main way that scientists look at this is through its effect on global average radiative forcing, which is a measure of essentially how much heat is being trapped in the Earth system in watts per meter squared. There have been 8 studies that I surveyed in this analysis, and I think only 8 that provided radiative forcing estimates that I've been able to find, at least through March of this year. Of these, the vast majority found an estimate of around 0.1 to 0.15 watts per meter squared effects of this new regulation. The new Hansen study has a much bigger effect of 0.5 watts per meter squared, though it is a bit of an outlier compared to the rest. And these studies are primarily using fairly sophisticated Earth system models to assess the regional impacts of sulfur changes over the ocean where shipping lanes are located. Hansen's estimate is a bit more based on sort of some cloud cover and albedo changes in those regions. So it's a bit of a different approach than the other ones. Now, if we plug all of those different estimates into a climate model and sort of treat them all equally and then account for the uncertainties in aerosol effects, we get something that looks like this. So overall, a single central estimate or 50th percentile estimate of about 0.4 of degrees C warming associated with the shipping regulations. But if you use Hansen's estimate on the high end, you could get up to 0.15 C. So a fairly big range, though much of that is dominated by the Hansen et al. Estimate. If you excluded that, everything else would probably be in the lower third or so of this graph from all the other published studies. Now, if we look at Chinese SO2 emissions reductions since 2007, we similarly see a pretty big effect. So by 2024, it's about 0.06 of degrees C. So a central estimate that's actually a little bit higher than the shipping one. And, you know, this is also roughly what a new paper that's still a preprint, but it should be published shortly by Bjorn Samstedt and colleagues get. They found 0.07 of degrees C cooling associated with Chinese aerosol declines. So similar central estimate, and again, a fairly big range associated with aerosol uncertainties. And then let's add all these together. So I didn't show a graph for other global emissions, but there has been a decline in other global SO2 emissions. So if we analyze those, we get this light blue wedge at the bottom. These are all the central estimates of each of these. If we add Chinese SO2 emission reductions, we get the red. And if we look at international shipping, we get the dark blue. And so if we add all of these together, we see about 0.15 C additional warming since 2005, really 2007, which would be approximately a quarter of the warming the world has experienced since that time would be associated with aerosol declines. These declines are not necessarily completely outside of the range that our future scenarios that we use to run climate models expect. So the black line here is the observed SO2 emissions globally. And then this is a fairly wide range across all the SSPs, but it's roughly in line or a little bit below the SSP 4.5 scenario, which is roughly analogous to a current policy scenario. And similar to what we'd expect in some of the deep mitigation scenarios like SSP 1.9. It is quite possible, if these trends continue, that we could see faster sulfur declines than in particularly the sort of SSP 4.5 scenario, which could potentially mean we might end up with a little bit more warming this century than that scenario expects. But we'll see. It's close enough now. It's hard to read too much into that. Okay, so I want to leave time for questions, but I'll quickly touch on this question of the last 2 years specifically. Because so far, this broad discussion about acceleration is really focused on the last 15 years. If we look at just the last 2 years and why they're so anomalous, so this is an analysis that Gavin Schmidt at NASA did with me in the most recent WMO State of the Climate report. The upper left graph shows annual global temperatures relative to pre-industrial. The red is sort of a 20-year locally linear regression. The bottom left is the residuals, so how the difference between the gray and the red lines in the upper left. And then on the right side is sort of our best attempt to explain those residuals. So in 2023, it was about 0.18 C warmer than we expected. And so if we look at the effects of El Nino on temperature that year, of shipping aerosols on temperature based on the analyses I showed earlier, of East Asian aerosols, which have a big effect since 2007, but didn't change that much after 2020 or after 2022. The Hunga Tonga volcanic eruption, which was an unusual eruption that put a lot of water vapor in the stratosphere, but also put the most sulfur dioxide in the stratosphere of any volcano since Pinatubo, and changes in the solar cycle, which has ticked up a bit more than expected in the last few years. And so if you add all of these together, you get about 0.09 of degrees C warming relative to expectation. Relative to the long-term trend, I should say. And we actually saw about double that. So there's still a bit of a gap in our understanding of why 2023 was so warm. If we do the same analysis for 2024, we have a much bigger effect of El Nino on temperatures, in part because 2024 was the year after El Nino peaked, where we generally see the biggest response in surface temperatures. The other bars are roughly the same, though there's a bigger solar cycle impact. And we do pretty darn well in explaining the anomaly. And the anomaly that year was 0.26 C above expectations, and these factors collectively explain 0.23 C. This is just another variation of that graph that my colleague Robert Rohde at Berkeley Earth put together. But but looking at the effects of carbon dioxide, CH4, and other gases on surface temperatures, the effects of El Nino over time, the effects of the solar cycle. This is looking at 6 different studies of that particular Hunga Tonga eruption, though it's worth mentioning that the 2 studies showing positive warming don't account for the sulfur dioxide emissions from the volcano, so they're somewhat incomplete. And then on the right is, a range of estimates of the shipping regulations that I showed earlier, excluding the Hansen one because it wasn't out when Robert published this. So yeah, that is pretty much what I have, and happy to take some time to answer questions.
Great. Thank you, Zeke, for speaking to such a timely phenomena, something that we've all been hearing and thinking a lot about. And I think even for me, I think I also didn't appreciate the role that aerosols have played in the trend over the last 10 years. For those of us working with climate modeling and working with CMIP6 data, the historical runs, of course, only go up to 2014. And so that's kind of where our present day thinking stops. And maybe it was a little hard to imagine that, in the 10 years since then, the trends look different, but it seems like the trends look different.
Yeah,
So-
I mean, that Chinese figure in particular of a 70% decline in emissions in the last 12 years or so is pretty stunning.
That is pretty stunning. Yeah, it'd be maybe helpful, or maybe there already is, some kind of short articles or notes just kind of pointing that out. That's a big deal. In fact, one of the questions we had from the chat was, what drove that reduction, or what policies, did they put in place, or was it just not policies, but just the evolution of their economy that did that?
It was mostly policy driven, actually. So around 2008 was the Beijing Olympics, which drew a lot of global attention to air pollution problems in China. Shortly after that, there was a documentary called Under the Dome that came out in China. That was sort of their version of An Inconvenient Truth. That was all about air pollution. It got watched almost 1 billion times before the censors ultimately decided to get rid of it. So there's just a growing awakening and sort of political pressure, excuse me, in that period that led to a lot more enforcement. So historically in China, coal power plants were required to install sulfur scrubbers, but they'd only run them when the regulator came to visit and not run them the rest of the time because there's a parasitic load, it reduces the overall energy output of the plant. And so they really just started cracking down, both requiring scrubbers and a lot of things that hadn't historically had them, and ensuring that scrubbers were actually run. Not that much of the decline in sulfur, in fact, very little, was actually a result of replacing coal or other sulfur-intensive fuels with clean energy alternatives. And part of that is that coal use in China is still growing, even though they're installing huge amounts of renewables to meet new demand. The only exception there is that there has been a fairly big push in electrification for things like buses, lorries, that has reduced diesel fuel and reduced sulfur emissions there.
So you said coal energy production is still growing in China.
It's roughly plateaued for the last decade, but it hasn't decreased.
Right. So the growth in solar is not displacing existing coal
yet.
It's just
it might this year. There actually is. There've been some interesting articles recently that Chinese emissions are pretty strongly down in the first quarter of the year.
Oh wow. Okay.
Even accounting for economic output. So it seeus like there is finally evidence that the rate of clean energy installation is itself pushing down emissions, but we'll see. I mean, many of us have been burned before by predicting the peak of emissions before it actually happened.
Yeah, but sounds like a very rapidly evolving situation over there in particular, and I find it useful to keep that in mind as we think about trends and how to attribute them. There's a couple questions here about, so we've talked a lot about you showed time series of temperature and sulfur emissions, and there's a couple of questions here about the role of the pandemic. So one can see what I imagine is the COVID dip on your graphs. Did COVID have an impact on the rate of warming, and any idea where we would be climate-wise if COVID hadn't happened?
Yeah, so there certainly is a little bit of a COVID dip in the sulfur emissions, though it's a little hard to tell because it also occurred. COVID occurred at the same time the International Maritime Organization rules went into effect for shipping. And so if you look at the non-shipping emissions, the dip is considerably smaller. I mean, COVID, for all of its disruption of industrial activity and society in general didn't actually have that big an effect on our emissions. I think CO2 emissions declined 7% in 2020 compared to the previous year, and then picked right back up 2 years later, even the next year in most countries. And so it was a very temporary phenomenon. And I don't think if we hadn't had COVID, it would have changed things all that much in terms of these pictures. Certainly, the declines that have persisted through present have persisted because of broader changes like clean air regulations in China or shipping regulations, not because of persistent effects of COVID.
Gotcha. And there was a related question, I think, about flights in particular. And so maybe you'd have a similar answer there.
Flights are actually, aviation in general is not a big source of at least sulfur dioxide emissions. There is contrails produced by aviation that has some radiative forcing effect, but it's actually not that big compared to everything else we're talking about here. Aviation, I think, is 3% of global CO2 emissions. Contrail forcing is highly uncertain, but some of the estimates are roughly of magnitude with the CO2 forcing from aviation. But it's a much smaller effect than what we're seeing with these big sulfur declines. And again, the reduction in aviation was pretty short-lived.
Yeah. And then a question from the same person about volcanoes. Is that something that can be seen perhaps in the aerosol forcing?
Yeah. So this is anthropogenic aerosol forcings that we're looking at here. So the sulfur dioxide emissions that are being used to run these model simulations are not including volcanoes. So if you look at this chart, the green line there is the volcanoes. And there you see a pretty big dip in global temperatures associated with Pinatubo. You also see a decline in observed temperatures, though it's a little complicated because there was a pretty strong El Nino event that happened shortly after Pinatubo erupted. And so you actually have a bit less cooling in the observational record than you have in model simulations because of that. Because models don't get the phasing of El Nino and La Nina events the same as observations do, because they're emergent properties of the climate system and are kind of chaotic. But yes, volcanoes have a big effect on cooling from aerosol emissions. They actually differ a fair bit from the tropospheric aerosols, the human emissions of aerosols that we're talking about here, in that human emissions of sulfur dioxide in particular are very short-lived. So in the course of days to weeks, sulfur emissions from power plants or ships fall out of the atmosphere. So you have to continue emitting it to keep that sulfur cooling present. Volcanoes, because they put it in the upper atmosphere, it lasts for an order of 2 to 3 years before you lose most of the sulfur emissions before they fall out and precipitate out in the lower atmosphere. And so because of that, you end up with about a 50x multiplier in the cooling effect of sulfur dioxide from stratospheric volcanic eruptions compared to human emissions in the lower atmosphere, because it's just so much longer lived.
And is that factor of 50 basically the lifetime?
Primarily the lifetime. Like, there's some slight differences in forcing effects being in the troposphere versus the stratosphere. It's less indirect effects in the stratosphere, potentially larger direct effects in the stratosphere, but it's primarily differences in lifetime.
Yeah, gotcha. Cool. There's a couple questions here related more to the temperature data sets. And so this is referring to, I think, the temperature time series you showed at the beginning. Yep. And I think the question is asking, when we're talking about thermometer measurements, back in the 1850s, how do those compare to measurements now? And I'm guessing that's both in terms of the instruments themselves and also the spatial coverage, all the things that Berkeley Earth folks had to worry about.
Yeah, so we've definitely changed the way we've measured temperatures a lot over time. And most of the uncertainty, or at least much of the uncertainty in observational temperature records, is associated with how we account for changes in measurement technique. Back in the 1800s and early 1900s, we would have sailing ships and throw buckets over the side of those ships and pull the buckets up with a rope and then stick a mercury thermometer into those buckets and take the measurements down in the ship's log. The problem is, while you're pulling the bucket up the side of the ship, some of the water is evaporating off the top, and that's actually cooling the temperature of the water in the bucket. And so it turns out that ships with taller deck heights measure cooler temperatures because there's more evaporative cooling, because it takes them longer to pull it up. So even stuff like that ends up mattering a bit. the way we take weather station land temperatures has changed a bit less. Mercury thermometers were really the norm until the last 30 years or so, when we replaced most of them with electric thermistors. There's changes in a little bit in sort of housing practices for thermometers, but by 1850, these were outdoor measurements. It's not like some of the stuff going back to the 1600s where it's unconditioned indoor areas that are challenging to be representative. The bigger issue when we go further into the deep past, particularly before 1900, is spatial coverage. We've done a huge amount of work as a community to try to reconstruct global temperatures further back. We've collected data from old ship logs, from old, weather station archives that hadn't been digitized before. And so the amount of stations we're using has increased. Back when I started working on this in 2010, groups were using about 7,000 weather stations around the world. Today, that's up to about 50,000. So there's been a real increase in the amount of data available, which has helped in the uncertainties in the early period. But as you can see in this graph, the uncertainties, which are those sort of black vertical bars, are significantly higher, in the early period, the order of, plus or minus 0.1 C or so, compared to very, very small uncertainties, less than 0.04 degrees C in more recent years when we have better coverage. There's also a pretty big uncertainty around World War II because we lost 90% of all the ocean temperature data in World War II for somewhat obvious reasons. And so that particular period has long been one that has been an area of active research to try to better account for all the disruptions then.
Great. And then another one, a little bit more of a sociological question relating to the Berkeley Earth analysis. So there's a sort of a question or a claim here that Berkeley Earth started as a skeptic analysis and convinced the originator that the warming is real. So perhaps as someone who's involved with that, you could comment on that.
I think it was probably more opportunistic framing than reality. Like I think, and you knew Rich from the class you took with them, Richard Miller, the founder of Berkeley Earth. He was an emeritus physicist, and in many ways sort of a walking embodiment of the emeritus physicist stereotype, for better or worse. So he was broadly skeptical of a lot of things. I don't think he thought that global warming wasn't occurring. I do think he was a little surprised at just how similar the Berkeley results were to those of NASA and NOAA, particularly given that we sort of built our own homogenization scheme from the ground up. Homogenization being how you account for changes in measurement techniques over time, or station moves, time of observation changes, all the various things that mess up the record. But it certainly led to a series of very useful headlines of, I think Rich even had an op-ed in the Wall Street Journal saying, I was skeptical about climate change and now I'm not. And so having a group of physicists, including, a Nobel Prize winner and a few other folks doing their own analysis, I think certainly at the time when skeptics were a lot more ascendant on these issues, was a useful counterpoint.
Yeah, in fact, in the early mid 2010s, Rich came and gave a talk to the Earth and Planetary Science folks, about the data set, and was more interested in talking about the different features and how interesting they were and how you could make a regression against CO2, and so did not present himself as a skeptic, at least to that audience. Mm-hmm. All right, what else do we got here? So here's a question that I think has been asked of a number of other folks, but given the work that you've done, Zeke, kind of across the climate policy energy interface, this might be interesting to ask you. What is the most encouraging change that you've noticed in the public's understanding of climate change in recent years?
So I think broadly speaking, there's less debate that I encounter around, is climate change real? And a lot more debate around people's preferred solutions, be it nuclear or carbon capture or solar, wind, that sort of thing. I'm a little cautious saying that because I think there are some signs, at least in the last year or so, that might be reversing as the issue becomes even more polarized. But again, the US is sort of not the world. And if you go to other countries, if you go to the UK, if you go to Germany, if you go to Canada, these issues are a little less politically polarized than they are in the US. So I think, I certainly spend a lot less time arguing with skeptics than I did 10, 15 years ago. Actually probably spend a bit more time arguing with folks who are more on the doomy end of the equation, who think that, it's hopeless. We're going to have runaway global warming, which is equally disempowering, right? If you think there's no hope, then you're not going to do the things needed to actually solve the problem. But yeah, I think that's definitely something I've seen. I think the other thing is that just people are starting to realize that there are jobs, there's careers, there's real money in solving this problem. The world spent $2.1 trillion last year on clean energy writ large, heat pumps, electric vehicles, wind, solar, etc. And that's up from 600 million 7-8 years ago. If the trend continues this year, we'll actually spend more on mitigating climate change than all the global military spending combined, which I think is would be a pretty good milestone to have.
Did you say 600 million to 2.1 trillion?
Yep. That's the latest numbers from IEA and Bloomberg New Energy Finance.
Skipping the billion. That's amazing.
Or sorry, 600. Yeah, I misspoke.
Billion. There you go. Okay.
600 billion to 2.1 trillion. Yeah.
There you go. Okay. So a factor of several, not of several thousand. Good.
Yes. Yeah.
Great. Well, thank you so much, Zeke, for sharing your perspective and this analysis on the temperature trends of the last several years. Appreciate you being here.
Yeah. Thanks so much. Great to be here.
Awesome. All right. So that brings us to the end of the keynote session in the evening, transitioning more into to the late night. And here's our director, Margaret. And so we're still going to have a number of great talks. The next person up is Mitch Bushuk, a good personal friend of mine from the same laboratory. But before we do that, we have to reset the stream, and Margaret will tell you where to find us so we can keep this party going.
All right, let's all thank Nodder for some awesome hosting. It is stream reset time, and you will be rewarded with some really cool conversation about the Arctic next. But we do have to reset the stream. You can rejoin at wclivestream.com/watch, and we will be kicking things off in another minute. And for those of you Rider fans out there, if you make it to the new link, you may see Rider if you're lucky. So let's head over to wclivestream.com/watch, where we will dive into Arctic sea ice.